Hey everyone and welcome back to PrepFusion. I'm Anish and I have got another Diwali gift for all of you guys. So this will be the fourth Diwali gift. So if you haven't watched the previous Diwali gifts, go back and watch this video. There Himanshu has told about the special Diwali gifts that you will get from PrepFusion. So this gift is regarding engineering mathematics. So today I will be uploading the complete marathon on vector calculus. This will be a comprehensive marathon on vector calculus which will be covering everything. So what will be covered? It will be we will cover basics of vector algebra, which we generally tend to skip. Many educators tend to skip. We will not skip it. We will study about basics of vector algebra. Then we will understand the gradient, divergence and curl of different vector functions, and obviously integral vector calculus, the Stokes theorem, the Gauss theorem, and all other theorems, right? So those things we learn in this comprehensive vector calculus lecture. So this will not always stay public. So I have a few demands from all of you guys. If you guys can like this video, right? If you guys can get this video, this is not a high demand. I hope you can get it like 150 likes. Then in the next 48 hours, okay? In the next 48 hours, if you guys can get this video to 150 likes, then this will remain, else this will go private, okay? And obviously I will post this about this on LinkedIn, so you can go there and repost this, repost my post and share my post, okay? So yeah, these are my only demands regarding this marathon, and I hope you enjoy the marathon. Happy learning. Finish this vector calculus differentiation part, okay? Within the two lectures, this and the next lecture, and then we'll start with integral calculus. So we'll study in a systematic manner and we'll try to cover most topics in as little time as possible. But what do I need? I need the effort from your side. You need to practice questions by yourself, okay? So like I will solve every question, and in front of you that won't be of much use to you. Unless and until you are solving the questions by yourself, then only you will be able to understand that how much you understood the topic instead of me. I will anyways, I'm a teacher, so I will anyway like solve any questions, right? But you have to understand whether you are grasping that concept or not, which I am delivering. That is more important. So overview of vector calculus, what we'll learn in this chapter. So first we learned about vector algebra. Sometimes few questions come from this. Previously few questions used to come from this, but now the question has been reduced. So very little questions come from this. I will write few questions, right? Because vector algebra is the 11th and 12th path, basic basic things, right? Scalar triple product, vector triple product, all those things. Then we have vector calculus, and inside vector calculus we have differentiation and integration. So currently we'll cover this first, and then we'll cover this integration, okay? So first I will try to cover this differentiation part. So but before going into the differentiation part, we have to understand few basic terms. So how much more basic we need to understand? Yes, we need to understand a lot of basic terms. So first is this function. I hope you are familiar with this function. This is a function of x, y and z, where x plus y plus z, like f of x, y, z is equals to x plus y plus z. Now this is a scalar point function. Why is this called a scalar point function? Because this doesn't have any direction associated with it, okay? This is just a scalar point function. So this is also known as a simple scalar function. It is also known as a 3D scalar function, okay? And sometimes they also call this as scalar field. Sometimes 3D scalar function, sometimes scalar field, all these things. What are the examples? Temperature, work done. Does temperature has any direction? No. Work done? No. Potential energy, all these things doesn't have any direction. Voltage source, does it have any direction? Whether it is plus minus or minus plus, only that thing we have to take care of. So positive or negative, it doesn't have any direction associated with it. Now let's understand what is a vector point function. So vector point function is just the same thing only. It is a function of x, y, z, but it also has a direction associated with it. So the examples are electrical magnetic field. When we will study EMFT, there we will understand. Electrical students can understand this. Then position, velocity, acceleration, all these things, right? It has direction associated with it. So this is also sometimes called as 3D scalar field. I will change this color. Just yeah,
this is not called 3D scalar field. This is called as 3D vector function or vector field. So, or sometimes 3D field also this is called as. So 3D vector function or vector field. So these are the basic terms that you need to know, right? I hope you already understand this because this is self-explanatory, but sometimes you get confused, right? The difference between scalar point function and a vector point function. So let's do one question. So we have to plot the following vector point function where my function xyz is equals to x but also has a direction associated with it. So how to draw this? So I know, right? J cap is along the what y direction. So let's first draw the obviously the axis, coordinate axis. If I draw the coordinate axis, this is x, this is y. Okay, so now can you tell me what will be the case? So if I am going in this x direction, right? So if I am increasing my x, okay, if I am increasing my x, what is happening? My y direction component is increasing. So obviously it will look something like this. As I'm increasing my x, let me put it like this. Y direction component is increasing, and if I am decreasing my x, the y direction component is decreasing, minus x, right? So this is like plus j, plus 2j, plus 3j, plus 4j, like that. Again, this is minus j, minus 2j, minus 3j, minus 4j. Okay, so I hope you get the point, right? This is somewhat like y equals to x line if you like see this carefully, but obviously I have vector lines, right? This is known as vector field lines. These are known as vector field lines. So this is the brief difference between a scalar function and a vector function. If it was a scalar function, it would have been y equals to x, so it would have been simply like a straight line. Okay, instead of it being a straight line, now each of these points, right, has direction associated with it. So I'll just write here 1 2 3 4. This will be 1, this will be 2, this will be 3, and so on, right? This is minus 1, this is 1, this is also minus 1, this is minus 2, this is minus 3, minus 2, minus 3. Okay, so yeah, this is how you plot a vector field. Now let's first understand few basic terms about vector calculus, few more. So first one is the del or Nepla operator. This you will use everywhere in vector calculus, so you have to, like, this will be in your brain forever. So what is the del operator? Del operator is simply a vector, right? It is a vector. Remember, del operator is a vector. And what is it? It is simply partial differentiation with respect to x in the I direction, partial differentiation with respect to y in the j direction, partial differentiation with respect to z in the k direction. Just simple thing. Just remember this. That's it. How to operate this, we'll understand in the next few slides. Next is the Laplacian operator. So this, like, is a scalar. This is used in civil or mechanical, I don't remember exactly. In those cases, the Laplacian operator is used. In our cases also, EMFT, we sometimes use the Laplacian operator. So that's why you have to study this. Okay, so basically, sorry, not field, scalar, this is scalar. So basically, if I apply a dot product with the same del operator, right, del dot del, what will happen? This I cap component, this will become twice, right? So this is d square by dx square. Again, this j cap component will be d square by dy square, and this k cap will be d square by dz square. Simply I'm taking the dot product of the del operator, okay, with itself. Then I'm getting this. So this is also used. So what are the operations of del operator? So first, with respect to a scalar point function, if I operate the del operator, then this will be called as del phi, and this is also known as the gradient. This is also known as the gradient of phi. Okay, they are also known as the gradient of phi. and in this, right, we'll use the, sorry, this is actually, yeah, gradient. I have to write this gradient. I forgot to write gradient of scalar function. Gradient. Yeah, gradient of scalar point function, and this is like denoted like this. Next, if I want to apply to a vector point function, then I have two options. I can either take the dot of that vector point function, or I can take the cross of that. So if I take the dot with it, it is known as the divergence of vector point function, that we learn in the next lecture. And if I take the cross with it, it will be called as curl of the vector point function. These two operators we'll learn in the next lecture. In this lecture, we'll learn about gradient of this scalar f of a scalar point function, and we'll learn the directional derivative, which is the application of gradient. So like this here, right, this is also denoted like divergence of a, okay, and this is denoted like curl of a. I don't have enough space. Okay, so this is how they are denoted. So for now, we'll study, just hold on, we'll study the gradient of phi, right? Let's move ahead. So first start with the example. Can you find the gradient of this function xyz? So how to find the gradient? So basically, if I want to find the gradient of this function, right, at 1 comma 1 comma 1, obviously I have to use that operator, right? And just remember, whatever we get out of this function, right, we will get a vector. Okay, we'll get a vector, not a scalar. So yeah, we'll get a vector after this function, right? So that also is important. This will be a vector. This will be scalar. Okay, if I can write here scalar, and this will be a vector again. If I have space, I don't have space, so I can write this in the bottom half, right? Yeah, this just hold on a second. Yeah, scalar, and this will be vector. Okay, this will be scalar, and this will be vector. So the result that we'll get, right, so after doing the operating the divergence of vector point function, we'll get a vector, a scalar. After doing the curl of a vector point function, we'll get a vector, and after doing the gradient of a vector, scalar point function, we'll get a vector. So, and what is the significance, we'll understand later on. So first, compute the gradient of this function. How to compute the gradient? So if I want to compute the gradient of this function, what I will do, I will write it like this: del of f x y z. So first I have to differentiate with respect to x in and put it in the I cap. So if I differentiate with respect to x, I will get 2x, and I will keep that component in the I cap direction. Then I will differentiate with respect to y, it is 2y, and I will keep that in the j cap direction. Then I will differentiate with respect to z, and I will get 2z, and then I will keep that in the k cap direction. Okay, then I'll keep that in the k cap direction. Now I have to find the gradient of f at point P. So P is 1 comma 1 comma 1. So if I put 1 comma 1 comma 1, 2 I cap plus 2 j cap plus 2 k cap. So basically, this is my gradient of f, and this is my answer to this question. So if they are asking us to find gradient of a f function at 1 comma 1 comma, you just put the point after you compute the grad of f in generalized manner. So now let's understand few basic terminologies. So whenever you are computing the gradient of f, there is a confusion. What is the confusion about? About level curves and surfaces. So what do you mean by level curves? So the level curve of f xy are curves in the xy plane along which f has a constant value. So this, let me write this: xy equals to c, xy as f of xy, right? Let me write this if I have space here. F of xy. Now if I write this as f of xy, if I write this as f of xy equals to c, that means that I have level curves, right? That means I have level curves. What do we make? Now you put c equals to 1. You put c equals to 1, you will get some curve like this. C equals to 1, you get some curve like this. This is simply a hyperbola. Now you put c equals to 2, what will happen? Now at x equals to under root 2 and x equals to under root 2 and y equals to under root 2 will be a valid point. So this point will be shifted up, right? This point will be shifted up when my x and y are equal. This point will be shifted up. So now at c equals to, so I will write this. This is c equals to 1. Now at c equals to 2, your curve will look something like this. It will shift up and here it will shift down. You can plot it in Desmos anywhere, right? Anywhere you can plot, you will see, you will observe the same thing only. This is c equals to 2. And if you go along, right? If you go on, again it will keep on increasing. So what is happening? I'm just varying the c. Okay, the type of the curve that I'm getting is similar lines. Shape of the curves are similar only, just like the position are changing. Okay, so these are basically my level curves, because the curves that are formed in the xy plane along which f has a constant value. So these are the curves that are formed in the xy plane. Here also I will get curve if my c is negative. If my c is negative, here also I will get the curve, right? So the curves that are formed in the xy plane along the along which f has a constant value are known as level curves. Okay, so what are these? These are the level curves of f of xy. Simple. Now what are level surfaces? I won't be able to show because this is covering the xy plane, and level surfaces will cover the xyz plane. That is impossible for me to show in 2D plane. So basically the level surfaces are surfaces in the xyz space on which the f has a constant value. Simply think like a sphere, right? Think like a sphere. So I have a sphere here, then that sphere will keep on increasing its value, right? X square plus y square equals z square equals to c. X square plus y square plus z square equals to 1, equals to 2, equals to 3. The radius is increasing, right? So these spheres will also totally cover the 3D plane. Spheres will totally cover the 3D plane that are known as basically level surfaces. Okay, so I have written this point over here that level curves is a way to collapse the graph of a scalar valued function in 2D plot. So basically if you see here I have multiple functions, right? Like multiple this sphere. So now if I make z as a function of x and y and c as any value constant, then I will be able to get a cross section of that. Okay, so like level curves are used on that way. So if you are not able to get this, that's fine, because we have to use this concept just for finding the gradient. Okay, so it's just like a 3D visualization thing. So yeah, let's start with gradient of a scalar function. So the gradient of a scalar function f of xyz equals to c, like first of all it has to be differentiable function, right? Differentiable point function, then only we will be able to find the gradient of a scalar function. Now if you observe here, you have been given f of xyz equals to c. So what is this? This is like a what? Level surface, right? F of xyz equals to c. So in generally you will be given like this, because you will be given a level surface. Why is it that the case? What is the importance? We'll understand later on. So basically this is a level surface. If you observe this carefully, now if this is a level surface, then what will be the gradient? The gradient, also written as grad of phi, equals to what? Del phi. Now like if you want to find the gradient, right? So first of all you have to represent this in terms of phi. Now what is phi? Because this is not exactly like, how will I find gradient of f of xyz? This is c, right? This is changing. So what we do, we convert this into a level surface. So basically what we do, we write phi of xyz, take a new function, okay, which is f of xyz minus c. Okay, we can do it other way also, c minus f of xyz. Then whatever we get, right, that will be something else. Now if I compute the gradient of this function, now if I compute the gradient of this function phi, I will simply get my answer, right? So basically what will happen over here, it will be grad of phi, not grad of f, sorry, xyz minus 0. Okay, now why do we do it like this? When we will go to the significance, there we will understand. Now what is my grad of phi? So wait, just hold on a second, right here. So basically my grad of phi xyz will be very simple. It will be del phi upon del x, so, and I direction plus del phi, okay, I'm just wasting too much time, upon del y in the j direction plus del phi upon del z in the k direction. Okay, so this is my gradient. Now why do we do it like this? We'll understand just in a bit. Now let's understand few properties about gradient of function. So let's take an example, right? Let's take an example that gradient of function f of xyz will be perpendicular to the level surface. Okay, so that's why we did it like this. The gradient of this function is defined like this only, and it will always be perpendicular. Now why is that the case? So let's take an example. Obviously I won't have time to prove it, but let's take a basic example. Let's take f of xy, two variable thing only, so that we will be able to understand this clearly. Y square, x square plus y square. So this is equation of what? Circle, right? This is equation of circle, and f of xy equals to this, equals to c. Okay, equals to c. So can I plot this now? Can I plot this? So this is x, y, and this, like this is the, let's say this is c equals to 1, right? It is 1. If I put c equals to 4, this will be radius 2, and if I put c equals to 3, radius will keep on increasing. Now what is the gradient of this function? Now if I compute the gradient, of phi, like let me write phi equals to x square plus y square minus c equals to 0. Actually this is equals to 0, right? So now if I compute the gradient, it will be simply what? 2x I cap plus 2y j cap. Okay, so its direction is what? It is always, its angle is what? Can you compute the angle? Angle of gradient of phi, it is tan inverse y upon x, that is y upon x, right? So if I'm at this point, let's say I'm at this point, right? X equals to 1 comma 1. Okay, this is like the, let's say this is the, like x square plus y square equals to 2. So x equals to 1 comma 1. Okay, so this is c equals to 2. Write it in different color. Okay, and let's say this is some value c equals to 4, not 4, let me take this as 8. So now if I am at this point, what is the angle of this gradient? It is 45 degrees, right? So it will obviously cross this, and like what will be the magnitude? Magnitude will be 2x square plus 2y square, and I know x square plus y square is a constant which is equals to 2. So 2 times 2 under root 2, 2 times 2 under root, it will be 2 only. So magnitude will be 1, magnitude will be 2, and direction will be along this direction. Again, if I'm at this place, right, this will be what? This will be 2 comma 2. Again the angle will be 45 degrees and it will be along this direction. Now if I keep on going, so what will happen? I can connect this vector, right? I can connect this vector. Okay, so the gradient at this point, right, whenever y equals to x, for y equals to x, right, what is happening? It is always perpendicular. And you compute for any other place, right? Any other place, you will see that it will be always be perpendicular about the circle. Okay, about the circle. So obviously from here we get the significant thing that gradient of any function will be the perpendicular along the level surface. So as I'm increasing the level surface. Now another important point to note here is, what do I do here, right? What does this mean? This means this is perpendicular. And what is the direction of this? The direction is in the direction where the function is increasing, right? Function is increasing, because I took it like this: phi equals to x square plus y square minus c. Now if I take my phi equals to c minus x square plus y square, that is also equals to 0, then I will see that it will be in the opposite direction. Thus everything will be in the negative, right? If this is negative, then this will be in the opposite direction. That is it. So here I've written few key points, that del of phi is known as gradient, which is known as a g vector, equals to the magnitude into the direction. So this is how a vector is represented. Now what is this magnitude called? This magnitude is called the rate of change of level surface in the normal direction. So it is the amount by which it change in the normal direction, right? Because here it's changing. We'll understand more about this in the next few slides. You can observe, right, how much amount is being changed here, okay, along the level surface. How much am I changing? So that is the what the magnitude says us. I am going from this point to this point, so how much am I changing along the level surface? What is the rate of change along the level surface? That is what this magnitude signifies. Okay, then this, right, this in the vector form represents a normal vector at point P on the level surface in 3 dimension. Basically here we can observe, right, this is in the vector format 2x I cap plus 2y j cap. So if this is in the vector format, so you can observe that this will be in the normal direction to the curve. Okay, and this point, maximum rate of change of level surface in any arbitrary direction, I will come to this after understanding the concept of directional derivative. And this is the unit normal vector at point P on level surface in 3 dimension. Okay, and when phi is greater than 0. Why I have written phi greater than 0? I will tell you. Phi greater than 0 means this also. Phi greater than 0 means my direction is in the positive direction. Where level surface is increasing. Now where is level surface increasing? If I observe, if I go in this direction, right, the level surfaces are increasing. So my direction of this phi will be this. Now we'll do an example. There the direction will be opposite, and there the where the level surface is decreasing, the direction of this grad of phi will be on that direction. We'll see with example. We'll understand. Don't worry. If you're not able to understand these points, it's okay. We'll understand this later on. So this, I hope you understand all this definition, right? This is just the unit normal vector along which my level surface is increasing. Okay, normal to the level surfaces. So these are the few significant points. Now let's solve this, and here we'll understand this better. So here we have to find the gradient to the surface x equals to c. So if x equals to c, what does it mean? So basically they haven't given us any boundation about y and z. So basically this y and z will move along everywhere, right? So my y can go from minus infinity to plus infinity, and z can also go from minus infinity to plus infinity. Only x has the boundation. X equals to c has the boundation. So what is this? This is simply what? This is the simple yz plane, right? This is a simple yz plane. Okay, so I can what I can do? I can write my f of x y z equals to x equals to c. So I have to find the gradient of this. So I will choose my phi. First case, I will choose my phi as f of x y z equals to x minus c equals to 0. Okay, this I will choose. Now if I compute the gradient of this, what will happen? I'll only get this, right, I cap. So this is a unit vector in the direction of x axis, right? Okay. So basically what is this vector telling us? So basically this is telling us this is also a normal vector, because this is normal to the what? Phi equals to 0 surface, right? If I put phi equals to 0, this will be normal vector phi equals to 0 in what? In phi greater than 0 direction. We'll understand when we will plot this. Okay, so let's plot this, right? So this, I can plot this vector. This is simple I cap, constant I cap. So I cap is in this direction, I cap. Now can I plot my level surfaces? What is it? Is simply the yz plane, right? Y is varying from minus infinity to plus infinity, z is varying from minus infinity to plus infinity. So if I can draw my plot side, okay, this is a very bad plot. And now what is happening? This, let's say this is x equals to 0. Now if I further increase, right, this is x equals to 1, and if I further get to another point, right, this is x equals to 2. So what I'm observing, as I'm increasing my x, okay, like the level surfaces are increasing, in like the phi is also increasing, right? Like yeah, phi is greater than 0 here. So if I'm moving in this direction, then phi is greater than 0. If phi is greater than 0, if I'm moving in this direction, basically x is increasing, right? X is greater than 0, or x is greater than c, you can say. If I'm moving in this direction, if x is greater than c, what does it mean? Basically x minus c greater than 0, that means my phi greater than 0, because x minus c I assumed as like phi. So obviously if I'm moving in this direction, in the positive x direction, basically if I'm moving in the I cap direction, positive x direction, then my phi is greater than 0. So you can observe, right, this I cap is getting related to this. Okay, so obviously if I'm moving in the phi, like this vector, what does this vector represent? This vector represents a normal vector, because this vector is normal to this level surfaces, and or you can say normal vector to phi equals to 0. Phi equal to 0 means x equals to c. Simply all these surfaces saying the same thing in phi greater than 0 direction, because I'm moving in this direction, that's why. So normal vector can be of two types. It can be either in this direction minus I cap or plus I cap. You have to specify the direction as well. So but normal vector is in this direction, that means phi greater than 0, or in the increasing, right? Phi is increasing, I can say phi is increasing. So I hope you got this point. Okay, so now let's take another example. Let's do it for the second case. So what is the second case? Second case is, if I choose phi equals to, I will do the opposite, c minus x equals to 0. Both are equals to 0, but I have chosen c minus x. Now if I compute the gradient, what will happen? If I compute the gradient, this will be minus I cap instead of plus I cap. Now what does this specify? This specifies the same thing only, but in a different manner. So I'll just reduce the size of this a bit. Normal vector phi equal to 0 in phi greater than 0 direction, but this time, right, phi less than 0 will be happening. We'll just see with example. Less than 0 direction, basically in the decreasing. This time phi will be decreasing. Okay, so basically let's draw the curves again. This time what will happen? I will draw the opposite, right? If I draw like these three curves only, if I draw these three curves only, okay, I have to reduce the size of all this also. If I take this side, here anyway is gone. Okay, so now what is happening? Now my vector is this, right? If I just extend this, if I can extend this, yeah, I can extend this, right? Okay, this is done. If I can extend this, this will be simply in this direction, right? Minus j cap, not j cap, sorry, minus I cap. So my this grad of phi is in this minus I cap direction. Now if I'm increasing here, okay, what is happening? If I'm going in this direction, if I'm moving in this direction, this means my x is greater than c, my x is increasing, or I can say my x minus c is greater than 0. Now what I can say, this, right? This means minus of phi this time, because I have defined my phi as different, c minus x. C minus x is greater than 0 or phi is less than 0. So definitely my phi is decreasing, okay, as I'm going in this direction. So if I move in this direction now, okay, in this direction, then what will happen? I will get a vector where my phi is increasing. So here my phi will be increasing. So I will do one thing. Okay, I made a mistake over here. This will be phi greater than 0 only. So I always get a vector, that's my mistake. I always get a vector that is in the phi greater than 0 direction. In the phi greater than 0 direction. So where my phi is increasing. Sorry for that. So in this point, what is happening? If I'm moving in this direction, my phi is decreasing, right? Phi is decreasing in this direction. Now, if I'm moving in this direction, in the opposite direction, what will happen? I'll just copy this. What I will do, this will be a bit difficult from my end. Still I will try. Okay, this is difficult. Move all these things. This will be present over here only. If I move all this, right? And this will be here. Yeah, so what I will do, I will just move these, right, along this, behind this, so that will be more prominent to you. So now I am moving in what? X less than c. Just hold on. Now I'm moving backwards, right? So this will be equals to what? This will be equals to x equals to minus 2. This will be x equals to minus 1. And okay, let me just change the z to here in this. Now what is happening? Here what is happening? My x is less than c, right? I'm moving in this direction, obviously in the negative direction. X is less than c. Obviously if x is less than c, that means x minus c is less than 0. Or I can say, I can write it in different manner, that c minus x is greater than 0. So c has been fixed, right? C has been fixed. Let's say c equals to 1, but I'm decreasing my x. So if I keep on decreasing my x, I will get this surfaces, right? I will get this surfaces. So c is fixed, I'm decreasing my x. So I'm going in the negative direction. So c minus x, what is this equals to? This equals to phi. Phi greater than 0. So obviously, again, in which direction I'm getting this? I'm getting this vector where my phi is greater than 0. That direction, right? Normal to that direction. So I'm getting a normal vector to phi equals to 0 surface in phi greater than 0 direction. Okay, if I will always get this. So this thing you have to remember. Okay, so you will always get a normal vector to phi equals to 0 in phi greater than 0 direction. This is the most important part. So from this you can understand what direction we are getting. I hope you cleared this point, right? I will quickly summarize later on whatever we learned. So yeah, I hope we got this point. Now let's solve this question. Let's solve few questions. So you have to find the normal plane to the surface this. Now which gives us the normal plane. So again, if you remember, if you find the gradient of this, then we will get a vector that is normal to this plane, okay, in phi greater than 0 direction. So we generally plot for phi greater than 0 direction normal vector, so we will compute for that only. So in general sense, what I will do, I will equate my phi, I will write this in phi equals to x square plus y square plus z square minus 4 equals to 0. So now we'll compute grad of phi, right? If I compute grad of phi, it will be 2x I cap plus 2y j cap plus 2z k cap, okay. And what is this? This is like a normal vector, right? So if I put the points at P, this will be 2i cap plus 2j cap plus 2k cap. So this is looking like what? A normal vector. If you draw a sphere and from the origin it goes like this, so it is like a normal vector. So whatever we got a correct thing only. So find the normal plane to the surface. So we have find this, right? So yeah, this is a normal vector to the phi equal to 0 surface at point P. I will write here, this is normal vector to phi equal to 0 surface, or what, phi equal to 0 or x square plus y square plus z square equals to 4, the same thing in phi greater than 0 direction. Just hold on a second, phi greater than 0 direction. Now if they have asked us to find the unit vector, so they have only asked us the plane, so generally what will happen, they may ask us the unit vector also. So what will be the unit vector? It will be a grad of phi in P. Obviously it will be simply I cap plus j cap plus k cap by root 3, okay. So this will be the answer. You just divide by the magnitude. So yeah, let's find the normal unit vector to the surface. So basically the same question they have asked, just the surface has been changed. So what you do is simply compute the gradient. So now if you compute the gradient, this will be 2x y cube. Now I am directly computing it without writing anything. So slowly we have to directly compute 2x y cube z. So I am differentiating with respect to x, plus then I will differentiate with respect to y, plus then I am differentiating with respect to z. So this will be x square y cube k cap, okay. And then obviously you put the values. So del phi of P to be 2i plus 3j plus k. So now if you compute the the unit vector, so unit vector will be a cap del of phi P. So this will be what? This will be simply 2i cap plus 3j cap plus k cap divided by 4 plus 9, that is 13, plus 1, so it is under root 14, right? So your answer will be under root 14. So here I have given few properties of del operator. You can put this in your short notes. You have to remember this. So you have to remember this. Okay. So if I have two functions, scalar point functions f and g, and if I want to compute the gradient of both of this in addition or subtraction, I can individually compute. Okay, or I can add and then compute. Similar thing. Next, if they are in dot product, right? Obviously, simple multiplication. If I multiplied them, then simply apply the what do you say? The product rule. This is simply the product rule, right? If you remember, for differentiation. So here also this works. What do? You compute the gradient of one function, then you keep the one as it is on the outside, then you compute the gradient of the other function, then you keep as it is on the outside. And then if you want to compute the gradient of a quotient, right, you just simply follow the quotient rule. So this gradient, this del operator, the gradient simply follows the rules of differentiation. So this is also known as the quotient rule, if you remember. Okay, so these three things you have to remember. Okay, if you want to compute gradient pretty quickly for two functions. Now let's come to the next concept of directional derivative. So what is a directional derivative? So first of all, we'll understand directional derivative of a level surface. So if I have a level surface and I have a scalar function like this, then the directional derivative in the direction of m. So we will be given a different vector as well in the direction of f. The directional derivative of that function in a particular direction. So in a particular direction, how much is that level function changing? Okay, so if I move in a particular direction, how quickly will my function change? So that is what this directional derivative means. So basically, if I move in a particular direction, if I move in a particular direction along my level surface, then how much will my function change? How much I will write, just hold on a second. Oh no, how much will I just have to function change to go more left actually. So now we're talking about a particular direction. So this is the significance basically of directional derivative. So I hope you got the definition. Like, this is very simple. So what you have to do, you have to compute the grad of phi, right, at point P. Then you take the dot product of this unit vector in the m direction. So you will be given a vector m about which you have to compute the directional derivative. You will compute the unit vector for it, and then you will find the answer. So am will be the unit vector and phi is simply the level surface. Okay, so like let's say I have been given a simple function z equals to f of xy. Okay, so it is a surface like thing. So if I keep on cutting the cross section, so if I'm increasing in the z direction, right, according to xy, so my z is changing according to xy like this. Okay, this is z equals to xy. This is the surface. Okay, z is changing like this, xy. So now let's say I am talking about this direction, right? My m direction is in along this direction. Okay, some weird direction like this, and my point P is up here. This is my point P. Okay, P is simply any point x, y and z. Now if I move, this is my m vector. Now if I move in the same direction, m direction, from this point P, okay, how much will my function change? That is basically what this direction derivative computes. Okay, so all the physical significance, although it's not that important because we're just studying mathematics, but still, just to give you some flavor, we can understand this, right? If I'm lying in this point, f equals to x, y, and z, and if I'm moving in this direction, then how much will my function change? Okay, that is what my directional derivative like computes, evaluates. So let's solve few example. So there are few steps that you need to follow to compute the directional derivative, or you can solve it like yourself also. So I will tell you how to solve it. So first, the question is find the directional derivative of f equals to 3xyz at 2, 1, 0 in the direction of this. So you have been given the direction and you have been given the function as well, scalar point function. So for directional derivative, you have to have two things. So first thing is two things, scalar point function and then the direction. So for directional derivative, these two things are important. For dd, two things are important. These two things are important. Okay, so obviously whenever you're computing dd, you have to have these two things. Now step one is you convert this into a scalar, not scalar, basically level surface. So you compute phi, and this is equals to what? This is equals to 3xyz, and c is 0 in this case, so c is 0 only. So c is equal to 3xyz, which is equals to 0. Okay, now what do? You compute the gradient of this. So gradient of this at point P. So first you compute the gradient. It will be simply 3yz I cap plus 3xz j cap plus 3yz k cap. Now what do? You find the gradient at point P. So either you can put the value of points xyz here, or you can put it at the end. But it is recommended, if they have given the point, you can put it here to simplify the computations. So gradient of phi at point P equals to, now x equals to 2, and wherever z is present, right, it will simply vanish. So this will be vanished. Okay, everywhere z is present. What did I do? Okay, this is wrong. This is wrong. This will not be z. This will be xy. So wherever z is present, that will be simply vanished because 0 is getting multiplied. So only I will be left with this, and this is 3 times 2 times 1, which is 6k cap. Okay, 6k cap. So we got our gradient function. Next, what we'll do, we'll find our, like, we have to find the projection of this in the direction of aim cap. That is what dot product geometrically means, right? Physical significance. We have learned this in the first lecture, 0th lecture. So, or you can understand how to find the dd, we have to take the dot product. So to take the dot product, we have to find the unit vector in this direction. So they have given us the direction, we have to find the unit vector. So we have to compute am cap. So what will be my am cap? Simply just divide it by magnitude. So this is 2i plus 2j minus k cap divided by 3. The magnitude is 3. So now I will take the dot product. So if I take the dot product, what will happen? Dot product with this, it will be, so dd will be del phi at p dot am, which is only the k component will be present, that will be minus 2 k cap. Okay, so it will be so not k cap, sorry, it will simply minus 2, right? So it is changing in negative, so it is decreasing. If I move in this direction, my level surface is decreasing, right? So that is the significance of dd. So here I have given you few properties about dd. So like this is how you compute dd, or you can, what you can do, you can put these points at the last stage here. But obviously you saw, right, how much simpler the function became, the vector point function became, right? If I just replaced with x, y, and z. So if z is 0, this will be 6k cap only. So here what you can see, my dd is basically grad of phi dot am cap, and which is also can be written as magnitude of grad of phi into magnitude of am cap. What is the magnitude of am cap? It is a unit vector, so magnitude will be 1 only. So magnitude is 1. So this vanished and it is simply cos theta. Cos theta is the angle between grad of phi and the direction in which I am moving. So obviously this can vary, this cos theta can vary between what range? It can vary between -1 to 1, right? Now can you tell me what is the maximum value? Just hold on a second. -1 to 1. This is simply P. So can you tell me what is the maximum value? Maximum value will be simply when this cos theta is 1, right? 1. So here this is the maximum value. And I told you, right, this magnitude of grad of phi, I already computed it previously. So what does it represent? This represents the maximum rate of change of the level surface in any arbitrary direction. Not in any arbitrary direction. Basically it is the direction of my gradient function, basically in the perpendicular direction, whatever is the direction of the gradient of this. So this happens when the angle theta becomes 0. And when does theta become 0? When my unit vector along the gradient, that is del phi, is equals to unit vector in which the direction I have been given to, in which I am computing my directional derivative. So unit vector along this will be same, the angle will be 0, direction will be same, angle will be 0, and my directional derivative will be maximum, basically in the perpendicular direction of the level surface. So if I am in the perpendicular direction of the level surface, then this will be in the maximum. Now if phi is increasing, this will be maximum. If phi is decreasing, it will be minimum, because this will become -1, that is theta equals to 180. So if they are both are in opposite direction, it will be minimum, right? So this is what this means. And what is this? So the definition of this can also be written like the direction of the gradient function can also be written direction of fastest increase of phi. Okay, so the normal vector will be the fastest increase of phi. So this is also used in machine learning. So direction of fastest increase of phi. So this is known as the A cap of gradient of phi. Okay, so these are the definitions. I told you, right? I have written it previously that magnitude is also defined as maximum rate of change of level surface in any direction, basically in the direction normal to the level surface. So this can also be stated as a definition. So they can also ask you, can you find the maximum rate of change of the level surface? So what you have to do at this point? So what you have to do? You have to simply compute the gradient and take the magnitude, and that will be my maximum change of level surface. Okay, so direction they won't give you. So let's do this question, and from here we'll understand. So we have been given a function f equals to xy yz plus zx, and find the following. So first we have to find the maximum value of directional derivative. What will be the maximum value of directional derivative? When the direction in which I'm computing my directional derivative is same as the direction of the gradient of that function. So basically in the normal direction. So hidden, they have, like in hidden terms, they have given me the direction also. Then they have asked us to find the value of directional derivative at point 1, 2, 3. So basically in terms of xyz we have to find, then I have to simply put the value of xyz and I will be able to compute this. So what I will do? So first I will compute the gradient of phi. Gradient of phi will be simply, this will be z, y plus z I cap plus y plus z, then this will be simply z plus x j cap, then this will be z plus x, then this will be what is this, zx, then okay, I'm just lost in some thoughts, y plus x k cap. So what will be the maximum dd max? Dd max is simply the magnitude of this. Here I have written, right, dd max is the magnitude, because cos theta becomes 1. So what will happen here? I will take the magnitude, so it will be right over here. It is the magnitude of gradient of phi. So it will be y plus z whole square, just hold on, plus x plus z whole square plus x plus y whole square. Okay, so this will be equals to, like, this is my dd max in terms of x, y and z. This is my first answer, and second answer will be here. I will just simply put the points dd max at a particular point P. So if I want to compute a dd max at a particular point P, what will be it? It will be simply del of phi P. So magnitude of del of phi P. So P is 1 comma 2 comma 3. So this is under root 2 plus 3 whole square plus this is 1 plus 3 whole square plus 1 this is 1 plus 2 whole square. So this will be 5 square plus 4 square plus 3 square. So this is almost like what is this, 25 plus 25. So this will be 5 root 2, because this will be under root 50. 25 times 2, which is 5 root 2. So this will be my answer of maximum directional derivative. So let's compute more questions. So like there are many types of question, right? Many types of question which comes in the directional derivative category. So we'll solve this question one by one, and that will be much easier for us. So this is the type 1, where you will be given like the point P and point Q, and you have to find PQ direction, along which you have to find the directional derivative. Pretty simple, right? I hope you can do this. So what I will do, I will tell you to do this, right, in homework. So this you do, you have to find the directional derivative of this function along PQ vector. How to find PQ vector? We know about position of vectors, right? So I hope you can solve this by yourself. Okay, so yeah, I will give you this as homework, and let's come to the next question. This question is interesting, because here you have been given the function, okay, and you have to find the function directional derivative of the function at 0 comma 0 in the direction 3i plus 4j. They have given you the scalar point function, they have given you the direction. So what is different in this? Difference is you have to find at 0 comma 0 where there is discontinuity. So how will you find? Obviously, if they have given you entity type, right, the answer must exist. So if the answer exists, then what you have to do, you have to find with the concept of limits. So there are two methods of solving this. So first method is simple, what we have followed, we'll do that. So first of all, we'll compute the gradient of this function. So gradient of phi is gradient of f only, because it is like phi equals to, like, c is 0 in this case. So it will be what? It will be del f upon del x I cap plus del f upon del y j cap. Now here, right, it is 0, okay, and here it isn't 0. So about 0 comma 0 we have to find. So what I will do, I will find the left hand derivative, okay, or right hand derivative. I will find simply the right hand derivative, and I know as directional derivative exists, so obviously this also have to exist. So I compute right hand derivative, that will be equals to this only. Okay, so you can compute that, right? So what you will do, I will solve using method 1. So I will simply compute the derivative. So what is my df upon dx? I am trying to compute my df upon dx at 0 comma 0. So I will put my x equal to 0 at a later stage. So I will write here at x comma 0 first. So because y I can put 0. Let me just write in terms of generalized case, then I will put my x and y 0. So what is a df upon dx? So I am coming from here, right, when this is not equals to 0, when x square minus y square is not equals to 0. So this will be simply quotient rule. So this will be x square plus y square whole square, and this will be 3x square. Okay, this is not plus, this is minus actually. This is 0 only. Okay, this will be minus x cube and minus differentiation of this 2x into x square. Sorry, what is it? Okay, sorry, this will be x square minus y square, right? Now what you do, you can divide this. Now what you can do, you can put y equals to 0. So if you put y equals to 0, this will be replaced with 3x square into x square minus 2x raised to power 4 divided by x raised to power 4. So this will become, so I am putting my y as 0, right? I can put my y as 0 because I am like partial differentiating with respect to x. So x is variable, but y I can put as 0. It is constant. So y can treat it as a constant itself. So I can put y as 0. So now this will be 3 x raised to power 4 by x raised to power 4. So this will be equals to 1. So I can observe that for any value of x, it doesn't matter, this will be always equals to 1. So df by dx is 1. Now let's compute df by dy. What will be my df by dy? So similar fashion, so this differentiation will be in the bottom. I will have this x square minus y square whole square. This time, right, I will put x as 0 and y as y only because y is variable. And here, right, what will happen here, this will be 3y square into x square minus y square minus, this will be minus of 2y into x cube plus y cube. Okay, so this will be 0y. So this is 3. So if I put x equal to 0, this will be 3 into y raised to power 4 plus, okay, wait a second, because this is not minus, this is minus, this will be plus 2y raised to power 4 divided by y raised to power 4 equals to minus 1. So for any value of y, this will be always minus 1. So my grad of phi at 0 comma 0, right, 0 comma 0 equals to I minus j cap. Okay, so now is there any other way to solve this? So there is another way to find this grad of phi, right? So what you can do, you can take the limits. So basically what is happening, my x, y are tending towards 0 comma 0. Now what is the definition of differentiation? If you remember correctly, definition of differentiation was, now if I am computing del f upon del x, what I'll do, I will take limit as h tends to 0, f of x plus h comma y minus f of x comma y divided by h, right? So basically my y is 0, so if my y is 0, this will be limit as h tends to 0 because y is 0, right? So here y and x both are 0. So if y and x both are 0, this will be h 0 minus f of 0 comma 0 divided by h. So if you are not able to understand the previous method, so what you can do now, f of h comma 0. What is f of h comma 0? F of h comma 0 is something positive where it is not 0, where my x is not 0. If x is not 0, I will use this definition. So here y is 0, h is not 0. It is h cube upon h square. So limit as h tends to 0, h cube plus 0 upon h square minus 0. Okay, we'll just put all this thing in the top. Minus 0 because it is 0 comma 0, and this will be divided by h. So simply this is equals to 1, right? This becomes 1 because h by h is 1 only. And similar fashion, if I want to solve, okay, let me just can I use some different color because this color is getting boring. So let me just use a different color. Now if I want to compute del f upon del y, so what will be it? It will be limit as I will take another variable k tending to 0. This time my x is equals to 0 only, okay, but y is k. Okay, this time I'm directly writing it minus again f of 0 comma 0 divide by 1. You will get the divide by k. You will get the same answer. This will be simply now limit as k tending to 0. So this will be x 0 cube plus k cube by minus k square minus 0 divided by k itself. So this is minus k divided by k, which is minus 1. Okay, so from here also you can directly compute your grad of phi will be I minus j. Okay, so now what you do, you just find the directional derivative. How to find the directional derivative? You have to compute the, like, your m vector is what you have been given a direction, right? What direction have you been given? You have been given 3i, 3i plus 4j. So you have to compute the like the unit vector, okay, directional vector basically. So your am cap will be simply 3i plus 4j divided by 5 divided by the magnitude. Now if you take the dot product, your dd will be del phi at p dot am cap. So it is simply 3 by 5 minus 4 by 5, so it will be minus 0.2, and this will be your answer. Okay, minus 0.2 will be your answer. Okay, so yeah, this is it for this question. So let's compute this next question. You have to find the directional derivative, just hold on, directional derivative of this function at 1 comma 1 comma 1 in the direction normal to the level surface z equals to xy at 1 comma 1 comma 1. So they haven't given you the direction, but you have to compute the direction. So can you do it for me? Can you compute the directional derivative of this function along the normal surface to this? Do you know how to compute the normal to a level surface? Do you know that? We have just learned this, okay, at the starting of this lecture. So these, I will, like, this question and the previous the question before that will be homework. So try to solve this, and in the next lecture I will solve. So this has a twist also. Okay, so yeah, I will see you in the next lecture. Thank you for watching. Hi everyone, and welcome back to PrepFusion. So today we will be starting the lecture 2 of vector calculus. So what we have studied in the previous lecture, we have studied about basic terms of vector calculus, and then we have studied about gradient of vector calculus. So I gave you a few homeworks, so that we'll do before starting this lecture, and we will also summarize what we learned in the previous lecture. So I will go through the slides of the previous lecture, because the physical significance, right, of gradient is also very important to us understanding that. So I will just go through, because it may so happen just by listening to me first time you may not be able to understand the physical significance. So we learned about this basic terms, right, this Laplacian operator, del operator, okay, and then we learned what is scalar point function is, vector point function. These things are clear. And then we learned what we have to study. We have to study gradient, we have to study divergence, we have to study curl. So in this lecture we'll do like start of this lecture we'll do the divergence and the curl, okay, and few more questions of directional derivative. So first we learned how to find the gradient, but for understanding the concept of gradient, like the physical significance, we had to understand what are level curves. Level curves are what? Basically nothing. If I have x equals to c, right, that means if I vary this c and what different curves I get, those are level curves basically on the 2D plane. So why is it called level? Because it is on the 2D plane. And why is it called level surface? Level surface because I'm just cutting each of the surfaces, right, as this is telling me. Basically I have what? A sphere, then another sphere, then another sphere, right? Now here what is happening, this whole thing, if I just like compute it, z equals to some constant value, that will be just a simple surface. So I'm just like, you can say I'm just what do you say, adding up the spheres, adding up the volumes. Like this is not that important, but the important part is this, right? If this is equal to some constant value, that means if I'm varying c, that is basically level surface, right? Now like, now if I fix my c here, if I fix my c, now if the question is asking us to find the gradient of this function f x y z equals to c, that means I have to find the gradient of this. I will make a new function that will be f of x y z minus c, and then I will find the gradient, not of this. And the gradient will give me a direction, like after finding the gradient, it will give me a direction. That direction will be normal to the phi equals to 0 or f of x y z equals to c. That will be normal to that we have just understood by this example, right? I computed the gradient of this function and I saw this vector, the gradient of this function was always normal to this function, okay? Or also in which direction? In phi greater than 0 direction. Always I will get a always I will get a gradient. Always the direction of the gradient will be phi equal to, in the phi equal to 0 direction, normal to the phi equal to 0 direction, and in the phi greater than 0, because here phi is increasing every time, right? I took one example, then I told you, like, the definitions. What is the magnitude? Magnitude is the rate of change of level surface. Why? We understood this in the next few slides while we are studying the directional derivative. So I took one example, x equals to c. Now first I interchange my phi as x minus c, and then in the next example I interchange as c minus x, just the opposite. So when I found out a gradient, it was only I cap, and I saw as I was increasing my x, c is some constant. Well, as I'm increasing my x, as my x is always greater than c, I'm moving in this direction, and my gradient is also in this direction, normal to this plane, right? Normal to my surface. So gradient is normal to my surface, and in which direction? In direction in which my x is increasing, or in which phi is greater than 0, in that direction. Basically x is greater than c is some constant value, x is greater than c, that means x minus c is greater than 0, that means phi is greater than 0. So in the direction phi greater than 0. Next, if I interchange my phi as c minus x, this also I can do, because a surface, right? A surface has two normal vectors, one in this direction, another one in just the opposite direction, okay? That is also a normal vector to the surface. So if you want that normal vector, then we have to replace like c minus x, and again I will get a normal vector to this surface, or phi equal to 0, that is on phi greater than 0 surface, but this time, right, my x is decreasing. This time my x is decreasing, and on the direction I'm getting my this normal vector, okay? Phi will always increase, but here x is less than c. So it all depends how you are writing your phi, but one thing will be constant: my direction of this your normal vector will always be in the direction of phi greater than 0. Always be in the direction of phi greater than 0. So you have to keep this in mind. Okay, this is very important. Next, we solve few questions. I told you, like, if you have to find the normal plane to a surface, right, you just simplify the gradient, because gradient gives me normal to the surface, normal. But here what is happening, I can have this normal also. The answer can be this also, right? A phi p minus I plus j plus k divided by root 3. So this is also normal to the surface, but in the opposite direction. So this is also normal to the given surface, but in opposite direction. But if nothing is told, by default choose this. So by default choose this. If nothing, they have told us nothing, because this is the positive one, right? That's why, or like just the intuition. Basically we do x minus c, like that only. We never do c minus x. That's why. So by default choose this. Okay, so like then we found a normal unit vector, basically the direction, and then I told you few properties. This you have to put in short notes. You have to put in, okay, put in short notes. That will be best for you. If I have some different color, I don't have different color actually. That is sad. So yeah, then we learned about directional derivative. Directional derivative is nothing. If I am at a particular point, and if I move in a particular direction that has been given to me, how fast my function will change. Okay, how my function will change in that particular direction, that is what this direction derivative tells us. Sorry for that like burp. So yeah, I told you the physical significance, right? If I am on this point on the surface and if I move in this direction, then how much will my function change? That is my directional derivative. And like I told you few formulas, then from here we derive, right, the maximum value of directional derivative, and this also means the maximum rate of change of the level surface in any arbitrary direction, basically in the direction of the gradient normal to the surface. So I will always move like my surface will always change maximum when I am moving in the normal direction to the surface. Okay, so that is very important. Then we solve few questions and then I give you this question as homework. So this is basically like a position vector, right? So I have been given it this point, so I have to find the directional derivative at this point along the direction PQ. So I have a PQ, P and Q. Okay, don't go to my drawing. P and Q. P is this 1 2 3 and Q is 3 2 1. Okay, and I have to write this vector. How do you write this vector, if you remember correctly? Okay, sorry. So you will write your direction vector is basically PQ, right, which will be basically OQ, if you remember, like I told you in the basics, minus OP. Okay, OQ minus OP. So this will be simple equals to OQ is what? 3 I cap, basically 0 minus 3 and all those things. 3 I cap plus 2 j cap plus k cap. And now what is my OP? OP is this I cap plus 2 j cap plus 3 k cap. So M equals to PQ equals to OQ minus OP, that is 2 I cap minus 2 k cap. So it will be 2 into I minus k cap. So this is my M vector. Now what I will do, I will just 2 minus I minus k cap. So whenever these kind of things happen, right, some common term is getting like we can take this common. You take this common. When we will find the unit vector, these two anyway will be vanished. You just have to find the magnitude of this. These two anyway will be vanished because both in the denominator and numerator both are common. So 2 will get cancelled and I will be left with only under root 2, 1 square plus 1 square. So just hold on a second. Yeah, I don't know what happened to my throat. So so unit vector in the direction of M will be simply I minus j by under root 2. Now let's come back to the question. So we have found this, right? So now we have to find the what gradient of our function. Gradient of phi equals to simply x square minus y square minus z square, which is 2x I cap plus 2y. J cap isn't anyways, okay, j cap, no, not j cap, k cap. J cap anyways isn't important because j cap is not present in our direction vector, right? But still we'll compute. Next is 2z k cap. Next is 2z k cap. So this will be x y z. So this will be 2 into what is x is about this point, right? X is 1, y is 2, then z is 3. Z is 3. So this will be 2 I cap plus 4 j cap minus 6 k cap. Okay, so this will be my grad of phi, right? So basically what you can do now, you can simply find the directional derivative at P. It will be simply phi at P dot your EM vector, unit vector. This will be simply 2 plus 6 divided by root 2. Okay, so it will be 8 by root 2, which is 4 times 2, which is 4 root 2. So yeah, this, if you have got this answer, this will be your answer. Okay, now let's go to that next question that I gave you as homework. Homework. Just hold on, something is happening. So let's do this question. So this question is only simple, but there is a twist. Here we have to find the directional derivative of f at 1, 1, 1 in the direction normal to the level surface at 1, 1, 1. So we have to find normal to this. So whenever the normal term comes up, right? Whenever the normal term comes up, that means you have to find the gradient, because gradient finds the normal to a particular surface. Basically, you have to find the gradient of this. So how to find the gradient of this? What do you do? So basically, what do? You write this. We have to find the, first of all, we have to find the normal of this surface, right? Of this surface. So I can take a function phi1, which will be simply z minus xy. And if I take the gradient of this, what will be this? If I take this equals to 0, if I take the gradient of this, this will be minus y I minus x j and plus k. Okay, let me just put this here. Okay, so now the interesting fact over here is I took this as phi1, right? I took this as phi1. I could have taken this differently as well. What I could have done, this phi1, what I could have done, I could have taken phi2, which will be equals to, xy minus z. Okay, xy minus z. Now phi2 is xy minus z, and now if I do grad of phi2, okay, this will be simply what? This will be simply y I cap plus x j cap minus k cap. Basically just the opposite, right? Because it will be in the opposite direction. So now I have two normal vectors, right? I have two normal vectors, phi1 at p. So it is 1, 1, minus I minus j plus k, and it is phi2 at p, which is I plus j minus k. Just the opposite. It will be just the opposite. They will be anti-parallel with each other, because I can have two normals, right, in two directions. So I have got my grad of phi. So no, not grad of phi. This is the what? This is the normal vector. So I have to find the unit vector, right? Then only I can find the directional derivative. So I have to find the direction along which I am going. So a cap grad of phi 1 equals to what? So this will be equals to minus I minus j plus k under root 3, and a phi grad of phi 2 equals to I plus j minus k under root 3. Okay, so these are my unit vectors. Obviously now I have to compute the gradient of the function actually to find the directional derivative. So I will compute that. So I cleared this doubt first. When you have to compute the normal, so you first compute the normal, right? And I can have two normals. Okay, I can have two normals. So they haven't mentioned any direction, so I can have two normals. Now in general, this will be the like the default normal. But if in the option, the solution that is given, if going through this route, if you find a solution, then obviously it will be MSQ, right? It will be MSQ, and you have to, like, if you don't mark that, then your answer will be incorrect. So you have to be careful about that. So now I want to compute my del of f, which is simply 1 by 3 xyz into minus 2 by 3. Okay, 1 is getting subtracted to this, 1 by 3 minus 1 is getting subtracted to this. So this will be minus 2 by 3. Now this, right, then I will apply chain rule. Then I will first took the derivative of the outside function, then I will took the derivative differentiation of the inside function. But this outside function, right, whether I would do del by del x, or I do del by del y, or I do del by del z, this outside function differentiation of the outside function will always stay. So what I'll do, instead of writing it over and over again, I will take this in common, because I know this will come out in common. Why am I teaching all this? To solve the question in a fast manner, so that you can solve the question in a fast manner. So this will be anyways present with all the terms, right? I, j, k, all the terms. So this will, I will take as common. Then I will took the derivative. Then I will take the derivative of the inside function. So it will be, first one will be yz. I am doing del by del x. Then I will do del by del y, which will be xz. Then I will do del by del z, which will be what will be this? Yeah, this will be xy. Okay. Now the point is 1 comma 1 comma 1. So I'll put 1 comma 1 comma 1. This will be 1 by 3. This will be 1. This will be I plus j plus k. Okay. So now I have to take the dot product of these things, right? Dot product. So it will be simply del of f. This is del of f at p. If I take the del of f at p and take the dot product with a cap, a cap phi 1, it will be 1 plus 1 minus 1, 1 by 3 root 3. Okay, and now this will be one of the answers. Okay, if I do it second time, right, with the second normal vector. Okay, this one was the first one actually, sorry, apologies. This will be minus 1. This is again del of f at point p dot with a del of phi 2. This will be 1 by root 3. So I'm getting two answers, right? I'm getting two answers. So you can observe that in the options I have two answers, right? I will tick those two because this was a MSQ. I forgot to mention this was a MSQ. So here option A and option D will be my answer. Option A and option D. Okay, these two will be my answer. So yeah, you have to take care of that, right? You have to be careful about the normal vectors. If they have given both in options, then you have to tick the both. In most cases this will be only given, right? Because in most cases people will solve it like this, but this is also another valid answer. This will be also valid answer. You have to be careful. So yeah, let's start today's lecture. So before starting today's lecture, I just want to give you a quick recap about position vector in 3D, which you already know. Like this is known as mod of OP in 3 dimensions, and this will be equals to R. Okay, like we define it like this. R will be a scalar point function which will be under root x square plus y square plus a square, and R vector, right? This R vector actually. R vector is a function of time. X is a function of time, y is a function of time, z is a function of time, because we are moving in x, y, z and we are all function of time. If a car is moving in some direction, it is a function of time because it depends on the speed and all those things, right? So all those things you know, and few basic physics terms which are these, right? The differentiation of position vector with respect to time gives us velocity vector, and the differentiation of velocity vector with respect to time gives us the acceleration vector. Now what will be the double differentiation of R vector? It will be the acceleration vector itself. So here I can write my acceleration vector also like this: d square r t by dt square. Okay, so yeah, like you can write it like this. So let's solve a question with this information what we have gathered. So like R is given like this, and like R generally we write it like this: x square plus y square under root R is written like this, and R vector is written like x, y, z, I cap, j cap, k cap. So we have to find the directional derivative of a function like this at this point in the direction of the acceleration vector whose position vector components are xt equals to this, yt equals to this, and zt equals to this at t equals to 1 seconds. So along this acceleration vector, along the direction of this acceleration vector. So how to find the direction? We'll see about that. First of all, we have to find the directional derivative. So anyways, we have to find the gradient of this. So we'll first compute the gradient of this. So if I compute the gradient, the gradient of this del of f equals to what? This will be 2xy plus z square into I cap plus 2xy. So this is x square plus 2yz into j cap plus x square y square. This will be 2yz, not 2yz, sorry, this will be y square plus 2zx into k cap. So now I can simply put the points. Okay, so del of this will be not del of f, this will be del of phi. Actually phi is f only because it is equal to 0, so it doesn't matter. So del of phi at point P, what is it? It is simply equals to 2 comma 1 comma 0. So this will not get, this will get vanished. This will be 2 comma 1, so this will be 4 I. Here this will get vanished. This will be 2 4 plus 4j, and this, right, this will be 1, this will be vanished, so this will be plus k. Okay, so this will make gradient. Now they have told us that I have to find to take the directional derivative in the direction of the acceleration vector. So basically what is my acceleration vector? So my acceleration vector is simply the differentiation of the velocity vector. And what is my velocity vector? It is simply the differentiation of the double differentiation of the, like, it is a differentiation of the position vector. So acceleration vector will be double differentiation of the position vector. So for that I need to find the position vector. So if I write the position vector in terms of time, this will be t comma I plus t square j plus t cube k, right? And obviously you don't put t equals to 1 right now. You have to first find the acceleration vector as a function of time, then you put t equals to 1. Don't be dumb. So the double differentiation of this d square r of t by dt will be I plus 2, this will not be I, right? This is the first differentiation. So if I differentiate this twice, what will happen? This will go to 0. So I will not have a I component. If I differentiate this twice, this will be 2 only. So this will be 2j cap plus this is what? This is 3 into 2, 6t k cap, and we're computing at t equals to 1, right? T equals to 1. So t equals to 1, a of 1 equals to 2j plus 6k. Now I have to write it in terms of direction, right? So this will be, if I take the 2 common 2, if I take common, this will be 1 plus 3k. So it will be 1 plus 1 square plus 3 square under root. So it will be 1 by under root 10. So 2, whatever I am taking common, that will be cancelled in both numerator and denominator. So 2 will anyways get cancelled. So it will be j plus 3k cap by under root 10. Okay. So now what you can do, you can simply take the directional derivative. So directional derivative will be simply gradient of phi at p dot a cap. So it will be equals to 1 j plus 3k, and if I take the dot, so j plus 3k, this will be 4 plus 4 plus 3, 4 plus 3, right? 4 plus 3 divided by under root 10, it will be 7 by under root 10. Okay, this will be your answer, like the numerical value will be your answer to this question. So let's solve this next question. We have to find the directional derivative of this function at this point in the direction along xy plane. So direction is along the xy plane to the line that makes 45 degree with the x-axis. So the vector should lie in the xy plane and it should make an angle 45 degree with the y-axis. So if I draw this xy plane, right? If I draw this xy plane, so gradient I can easily find out of the function, but I first have to understand what direction is it talking about, the m vector, right? So this is x, y, and here if I draw a vector, okay, along the xy plane, so the angle here is 45 degree, because with respect to the y-axis it has told me the angle will be 45 degrees. This is my what? This is my m vector, right? Now if this is 45 degrees and overall angle between x and y, they are orthogonal to each other, so this will be total 90, so this will be remaining angle will be 45 degrees. So this angle will also be 45 degrees. Okay, so now what? So we know how to break these down into components, right? If I know the magnitude of this, then I can break this down into components. Magnitude of m cos 45 will be in the x direction. This is the in phase component and this is the out of phase component. For the people who know phasor diagram, all those things. Magnitude of m cos 45 plus magnitude of m sin 45. Okay, so this is it, right? Now this is my value. So what is my magnitude of m? Basically I don't know what is the magnitude of m. I am interested in computing the unit vector. So if I am interested in computing the unit vector, we have already found the unit vector. So your m is this. So unit vector will be just the common thing will go away, right? If the common thing goes away, then unit vector will be am cap. The common thing will go away, right? And this will anyways cos theta plus sin theta is anyways 1. So obviously this will be I plus j divided by root 2. Okay, so yeah, this is the am cap. We have found out the directional vector. Now obviously we have to compute the gradient of the function, right? Okay, I have already written it here. Let's not do it. So what will be the gradient of the function? It's just like bread and butter for you, right? It's simple right now. So first I'll differentiate with respect to x. So it will be yz I cap plus xz j cap plus xy k cap, and it is at point 1, 0, -1. So where y is present, those will get vanished, and this will be 1 times -1. So this will be minus j, and obviously my directional derivative at point P will be simply grad of phi at point P into this direction, which is I plus j under root 2. So it will be simply minus 1 by under root 2. Okay, so this will be my answer to the question. So we have understood like what directional derivative is. Now there are few more models of question, few more types of question which come in examination. So like this is one thing that you have to ratta, you have to remember, right? Ye ratta manna hoga aapko, we have no other option. So this ratta, this we have studied in 12, but I think you have forgotten already right now, and this you have to put in short notes. Okay, just remember this thing. If anywhere, right, some equation is something like this is given, x minus x1 by a, y minus y1 by b, z minus z1 by c, then you will get a straight line that is parallel to the vector whose components are ai cap plus bj cap plus ck cap, and which will also pass through this point x1, y1 and z1. Okay, straight line parallel to the vector passing through this point. Okay, and the vector is a I cap plus b j cap plus c k cap. You have to remember this formula. You have to rectify. You have to remember this formula. So you don't have any other option. So what do you do? Let's do a question, and from there you will understand. So let's read the question. You have to find the directional derivative of this function at 2, 1, 0. So this first part is very simple. I know how to compute. Like I will just compute the gradient and I'll put the value of the point. Then in the direction parallel to the line, this. So how do I find the direction that is parallel to this line? Basically a vector that is parallel to this, right? What is that vector? I can see from the bottom, right? This is the same format as I showed just here. So what is the vector? Vector is 2 I cap minus j cap plus 2 k cap. So that is my direction vector. So obviously my m vector is directly coming from this. M vector is directly coming from this. So this will be simply 2 I cap minus j cap plus 2 k cap. Okay. So like what does this tell us? What does this tell us? This is basically, what does this like three equal things tell us? This is basically a line passing through 1, 0, 1. Okay, passing through 1, 0, 1 and parallel to 2 I cap minus j cap plus 2 k cap. So this is what information that this particular equality gives us. So obviously I am interested in the direction only, so I will compute the unit vector am cap. So it will be simply 2 I cap minus j cap plus 2 k cap divided by under root 9, which is 3. So I got the unit vector. Obviously now I have to compute the gradient also. So gradient of phi, this is again simple, right? Cup of tea, or what do you say, cup of cake, of I forgot the particular word. So it is 2x I cap minus 2y j cap plus 2z k cap at 2, 1, 0. So it will be wherever z is present, that will be gone. So this will be 2 I cap minus 2 j cap. So this is 2 I cap minus 2 j cap. That is simply what I get, right? So now we have to take the dot product of this. Sorry, this is 2, right? X equals to 2. So this will be 4 I cap. 4 I cap. Okay. So basically this is so this will be 4 times 2, which is 8, and then this is minus 1 times minus 2, which will be plus 2 divided by 3. Okay, so it will be 10 by 3, which is 3.33. So your answer will be 3.33. So next you have to find the directional derivative of this function at 1, 2, minus 1 and has a maximum magnitude of 3 in the direction parallel to the line this. Okay, then a plus b plus c. So you have not been given the function, but you have been told few information that the maximum magnitude, this directional derivative has maximum magnitude of 3. In which direction? In direction parallel to the line this. Now you have been given the direction and the maximum magnitude. And when do we get the maximum magnitude? In the direction of the gradient of the function itself. So this direction, whatever this direction is telling me, that direction is the direction of the gradient at this point. So two information have been given, and I can compute I have to compute a plus b plus c. So let's go ahead in this question, right? So first of all, if the directional derivative is maximum and the maximum value is 3, then 3 will be equals to what? Basically the magnitude of this gradient, magnitude of this function, magnitude of the gradient of the function at this point. So first of all I will compute the gradient. So gradient is phi equals to ay plus cz. Everything is recording, right? I need to just check once if everything is recording or not. Just hold on. Yeah, everything is recording. Fine. So ay cz I cap plus b x plus bx, not bx, sorry, it's ax plus bz and j cap plus this is z is present where this is by plus cx, this will be k cap. So basically if I just put the points, right, if I just put the points, it will be y is 2, so this will be 2a, c is minus 1 minus c I cap plus a is what is a is like not is x is 1, this will be a plus 2b plus y is 2 so this will be 2b again. Why is it right? This is b, no, this is not bz, sorry, this is bz, no, yeah, this is bz only. Yeah, I will differentiate with this to divided. Yeah, fine. So 2b, y is and z is not x is 1 only, so this will be plus c, right? 2b plus c, a plus 2, if I have made some z, okay, z is minus 1, sorry, z is minus 1, so this will be a minus b and this will be 2a minus c and this will be 2b plus c. Okay, so now basically what do we know? We know that if the maximum value of my directional derivative is 3, basically that is equals to the magnitude of gradient at this point, right, at this point, which is equals to 3, so which is equals to under root of this 2a minus c whole square divided by like a minus b whole square plus 2b sorry, 2b plus c whole square. So now what is happening? Now basically if I see this clearly, this will be now can I equate this with anything? No, right? But one thing I know, if I know the maximum direction, what is the direction of my gradient? Okay, this gradient, what is the direction of this gradient? It is simply 2a minus c plus I cap by a minus b whole square j cap plus 2b plus c whole square k cap divided by the magnitude of itself. And what is the magnitude? Magnitude is this, which is equals to 3 itself, so this will be divided by 3. And the interesting fact is this will be equals to my direction of the directional derivative along which I took the directional derivative, because it is maximum, right, and it is parallel to this line. So what is this equation telling me? This is telling me, if I copy this, I will just copy this, if I take another page, yeah, then what is this equation telling me? Can you say with me, what is this equation telling me? This equation is telling me that I have a line passing through where? Passing through 1, 2, 3. So I have a line passing through 1, 2, 3 and is parallel to vector what? To vector what? It's parallel to vector I cap minus 2j cap plus 2k cap. So I cap minus 2j cap plus k cap plus 2k cap. So now if I just compute the unit vector of this, it will be simply I cap by 3. Now this will be I minus 2j cap plus 2k cap divide by 3. Now if my dd is max when is my dd max? When the direction of the gradient, that is basically the normal to the surface, is equals to along the direction which I am taking my directional derivative, so which is a m cap. So these two has to be equal when my directional derivative is maximum. So basically these two things will be equal, hence I can individually solve the equations. So I cap component is 2a minus c should be equals to 1, then a minus b should be equals to minus 2, and 2b plus c should be equals to 1, because by 3 is getting cancelled on both ends. So basically if I just try to eliminate c from this first and second, I will add these two. If I add these two, this will become 2 into a plus b equals to 2. So a plus b equals to 1 and a minus b equals to minus 2. If I add these two, 2a will be minus 1. So a will be minus 1 by 2. So a is equals to minus 1 by 2. Am I correct here? 2a is yes, 2a is 1 by 2, and okay, sorry, this is actually 2 here, right? This is actually 2 here. So this this will not be equal to 1. Sorry. So if I add this to this will be 3, and a plus b will be 3 by 2. Now if I add this to this will be 1 by 2 minus 1 by 2. And this will be minus a equals to minus 1 by 4. So a is minus 1 by 4. So from here I can compute my b. What is b? B will be a plus 2, right? A plus 2. A is minus 1 by 4, so it will be 7 by 4. B will be plus 7 by 4. And if I have found out my b, I can simply compute my c, right? So or from here also you can compute your c. C will be equals to 2a minus 1. So it is minus half minus 1, which will be minus 3 by 2, right? And you can cross verify, right? You can cross verify here that if I put c equals to minus 3 by 2, and this will be 7 by 2, and if I add these two, it will be 4 by 2, which is 2 itself. Yeah, it is satisfying the equation. So I have found my answer. So I have found a and b and c, so I have to give answer as a plus b plus c. So do keep this in mind what you have to answer, right? You try to highlight this, right? Highlight this, that I have to answer a plus b plus c, so that you don't forget this. That is also very important. So if I have to give a plus b plus c, this will be minus 1 by 4 plus 7 by 4 minus 3 by 2. So this will be equals to what? Minus 6 by 4, which is not minus, plus 6 by 4, which is 3 by 2. So 3 by 2 minus 3 by 2 is 0. So answer will be 0 to this question. Now let's come to the next topic, that is angle between two level surfaces. Now if you want to find the angle between two level surfaces, how will you go along with that? So the simple concept here is, I want to find the angle between two these level surfaces. Okay, how will I find? If I find the normal to this angle, then the normal to this angle, and if I find the angle between those, will that be same as the angle between two level surfaces? It will be same, because both of them are normal, and if both of them are normal, both of them are 90 degrees from their particular surfaces. So if both of them are 90 degrees, then the angle between the normals will be just simply the angle between the two level surfaces. That will be same. Okay, and like because why do you want to do that? Because it's difficult to find the angle between surfaces just with the equation of surfaces. We know how to compute the normal to a surface, simply the gradient. So we'll compute the gradient, okay, and then what I'll do, then I will take the dot product between these two, because I told you, right, in basics chapter, if I take the dot product, then I will find the cos theta, and cos theta means theta is the angle between the two vectors. Here the vectors, two vectors are normal vectors to the surfaces. So basically here I have a common point. There will always be a common point between the two surfaces. If there is a common point between the two surfaces, okay, then I find the normal. So what is the normal vector to this at this point? It will be somewhat like this. I will change the color. Let's say this is G1 vector, right? And the angle between this is, let me compute the angle between this. So let me compute the normal vector to this F2 curve, right? F2 surface. It will be like this. It will be G2. Okay. So I found out G1 and G2, which is simply equals to what? G2 is equals to what? Can you tell me G2 is equals to what? It is simply the gradient of that function, which is equals to grad of phi 2, right? Grad of phi 2. Okay. At particular point P, and this is also equals to gradient of grad of phi 1 at particular point P. Okay. And this angle, right? I want to compute this angle. Okay. Which is simply the angle between these two. Simply the angle between these two. So this is the angle that I am interested in. Okay. And as my theta will always lie between will always lie between 0 to 180. So I will always report the angle which is less than 180, right? I cannot decode the angle which is greater than 180. So basically, what is phi 1? I forgot to tell what is phi 1. Phi 1 is basically f1 minus c1, one of the level surface, and phi 2 is basically f2 minus c2. Phi 2 is f2 minus c2, and phi 1 is f1 minus c1, and this, right, this is the common point. So obviously, for computing the angle, they have to have a common point between the surfaces. Okay. Okay, so yeah, this is the case. So basically what we do, we just simply compute the dot product between these two, and then we found the theta, right? And the range of theta will be what? Will be between 0 to 180 degrees. So range of theta will be between 0 to 180 degrees. It will not exceed, right? It will not exceed 180 degrees, because if it exceeds, obviously we'll take the other angle. Right? So that is very important. Range of theta has to be 0 to 180 degrees. So let's solve one question, and from there we'll understand this better. We have to calculate the angle between surfaces this and this at particular point 1. So obviously check the points, right? Check point. Step 1. Step 1 is check the common point. Check the common point. Obviously I can see very well that 1, 1, satisfies both of these equations. So I will write here 3 is equals to 3 and 3 is equals to 3. Okay, so both of them satisfy. So that is fine. Step 2 is what? Step 2 is simply compute the gradient, right? Find the gradient of both of this. So del phi 1 is equals to what? It will be 3 will be common with everything. It will be x square I cap plus y square j cap plus z square k cap. Now if I take the now I have computed del of phi 1. Now I will compute del of phi 2. It will be, no, I have to also compute the point, right? So this will be 3 times 1, 1. This will be 3 into I cap plus j cap plus k cap. And if I compute del of phi 2, this will be 2 into x I cap plus y j cap plus z k cap. This will be 2 into I plus j plus k. Okay, so like you got this. Now you have to what? Just take the dot product. That's it. So this is my what? This is my G1 and this is my G2, right? So now what I will do, I have to find the theta, right? So what will be cos theta? Cos theta will be G1 dot G2 divided by magnitude of G1 divided by magnitude of G2, which is equals to G1 dot G2 is simply 3 times 2, 3 times 2 and 1 plus 1 plus 1 divided by magnitude of both of this. So this, right, this magnitude is what? 3 root 3 and this is 2 root 3. So like I hope you're understanding how am I able to compute all this thing very fast. This 3 will be common, right? So 3 will get out of the square root. I will have 1 square plus 1 square plus 1 square under root 3. Then 2 will get common from the square root. 1 square plus 1 square plus 1 square under root 3. So you have to make your computations fast in the gate examination. So 2 root 3, which will be 3 into 2 into 3. So 3 into 2 anyways will get cancelled. And this will be 2 into 3 divided by 3. Okay, anything. Okay, 3 into 2 will get cancelled. So that will get cancelled. 3 divided by 3, which is 1. So cos theta is 1. And when is cos theta 1? Theta equals pi by 2? No, right? Theta is 0 degrees. Theta equals to 180 is different. Theta equals to 180 is minus 1. So do take that note. So your answer will be theta equals to 0 degrees. So they will have no angle between them. This is your answer. So how will the curves look like? So roughly, right? Roughly, if I draw the curve, the curves will look like this. So the normal vector, this will be normal vector G1 and this will be my normal vector G2, and the angle between them will be 0 degrees. The angle between them will be 0. The angle between the surfaces is 0. Okay, so this you have to take care of. And sometimes what happens is like theta equals to 0 degree is also answer. Theta equals to what? 360 is also answer, right? So like it depends on the option. If it is a MSQ, then theta equals 360 is also a valid answer. So why is that the case? We'll understand this in the next question. So this is the next question. So we have to calculate the acute angle between the surfaces, right? So again the same question. So basically what I'll do, I will compute the, first I will check whether it is satisfying the surfaces or not, the point. So I will check the surfaces. Step 1, check the surfaces. Check point on surfaces. So it will be 1 minus 2 1, 1 minus 2 1. So this equation 1 will be 1 times 4 times 1 minus 3 into 1 equals to 1. So which is 4 minus 3, which is 1 equals to 1, which is true. Now let's get to this. This is 3 into 1 plus 2 equals to 4 plus 1, which is again 5 equals to 5. So both are satisfying, right? Both are satisfying. So obviously we can go ahead. So obviously then we compute the G1 and G2. So G1 will be grad of phi 1. It is simply equals to grad of phi 1, right? So I have to choose phi 1 now. So phi 1 will be this, right? Phi 1 will be this. If I just compute this, x y square z minus 3x minus z square equals to 0, right? So grad of phi 1 will be y square z minus 3 I cap plus 2xyz j cap minus plus I can say, I have to put this on more left hand side. This will be y square xy square minus 2z k cap. Okay, so this will be simple equals. Now what is the point? Point is 1 comma minus 1 comma minus 2 comma 1. So z is 1 and x is 1 and this is minus 2. This is 4 minus 3 plus this is minus 2. Yeah, this is minus 2 into 2 g, and this is xyz, right? Xyz is this. Why is this xy? This is xy square, sorry, not xyz. This is xy square, right? So this will be 4 minus 2 only k cap. So this will be I cap minus 4j cap plus 2 k cap, right? So this is I cap minus 4j cap plus 2 k cap. Okay, so we got the g1. Now we have to compute the g2 also. So what is my phi 2? So I think this is not looking that elegant, so let's just change the color to make this look more elegant. So what is phi 2? So phi 2 is simply 3x square minus y square, 3x square minus y square plus 2z minus 1 minus 1, 3x square minus y square minus 1. And if I want to find the gradient, so obviously I want to write the point also, else I will forget. Minus 2 comma 1, point is 1 comma minus 2 comma 1. So grad of phi 2 is simply 6x I cap minus 2y j cap plus 2 k cap. So I will put the points. It will be 6 I cap plus 4 j cap plus 2 k cap. Okay, so this is my grad of phi 2. Now what I need to do, I just simply have to compute g1 dot g2, which is equals to g1 also, not g1, sorry, g2 vector. Cos theta equals to g1 dot g2 divided by magnitude of g1 magnitude of g2. So what is g1 dot g2? G1 dot g2, this will be 6, this will be minus 16, okay, and this will be plus 4. Okay, so yeah, this is minus 16 and plus 4. So what does this become? We'll write that later. And this will be what? Magnitude of g1 g2. So 2, if I take 2 common, this will be 2 under root. Okay, let's first do this first. This is 1 square plus 16 plus 4, 21, under root 21. So this is under root 21. And this is 2 if I take common, and then if I do this, this will be 1 square plus 4, that is 5, plus 3 square, 1 square, it will be 14, right? Or what will be it? It will be under root 1 square, 2 square plus 3 square, 9, 1 square plus 3 square, 9, and 2 square, 14, so under root 14. Yeah. Now if I compute, this will be minus 6, right? Minus 6 by this. So what will be the answer? So the answer will be 2 I can cancel. This will be 3, and here under root 7 is taken as common, and I have okay, 7, yeah, under root 7 is taken common, so I can take those two outside. This will be 3 times 2, which is under root 6. Okay, so if I further simplify this, right, your cos theta will be 2 into under root 3, so this will be minus under root 3 by 2 divided by 7. Okay, 1 by 7 into under root 3 by 2. Now let me compute the angle for this. If I compute the angle for this, just hold on, 3 by 2 under root divided by 7 cos inverse, okay, actually it was negative, sorry, 3 by 2 under root divided by 7 cos inverse, it is almost 0.8 degrees, right? But like not cos theta, sorry, this is theta. So in the question, what have they asked us? They have asked us to find the acute angle, but what I'm getting an obtuse angle. So if you remember the definition, so basically obtuse angle, right? Obtuse angle is between 180 to 90 degrees. An acute angle is between 90 to 0 degrees. Okay, so obtuse is this and acute is this. Obtuse angle is 180 to 90 and acute is 90 to 0 degrees. So what is the important point over here? The important point is theta has been given this. Now there can be, like, they can define the angle as many things. In general case, what we define is the angle between the two normals. Okay, angle between the two normals. But let me copy this thing. And let me paste it over here. If I can go to the next page. So this, right, if I observe correctly, the angle between two surfaces, I defined it from here to here. The angle between two surfaces can be this also, right? It can be this also. Okay, so if I just compute the minus of this gradient, okay, just compute the minus of this gradient, I mean just take the opposite direction, okay, instead of choosing this. If I just go here, do I have any other color? That is what I'm searching for. I don't have any other color. Oh no, here, right here. So this angle can be also defined. Okay, this is theta 1, this is theta 2. Okay, and if I take this as the opposite one, that will be same only. If I take both opposites, that will be just same only, right? This angle and this angle will be same. Just the property of lines, right? Transverse lines, if you like remember those angle properties. But if I want to find this angle, again, this angle will also be same, right? This angle will also be same. So overall, like if I extend this and this angle, theta 2 and this angle will be same, theta 1 and this angle will be same. So overall, if the angle between the two surfaces can be defined it like this, either it can be theta 1 or theta 2. So what I have computed now, it may be, I don't know what I have computed. No, sorry, I know. I have computed theta 1. So this is equals to theta 1. Okay. But they are asking us the acute angle. They are asking us the acute angle between the surfaces. So if this is theta 1, okay, and I have to compute theta 2 because theta 2 will be acute, because this straight line total, what will be the angle of this straight line? 180 degrees. So theta 1 plus theta 2 is equal to 180 degrees. So theta 2 will be equals to 180 minus theta 1. So if theta 1 is obtuse, obviously theta 2 will be acute, because acute means between 9 to 90, right? So if something is greater than 90, then obviously if I subtract this, this will be less than 90. So in the question, indirectly they have asked us to compute the acute angle theta 2. So theta 2 is equals to 180 minus this, and this is almost equals to 90, not 90, sorry, 79.82, right? 79.82. Okay, sorry, not 82, sorry, 92, 79.92. Okay, so this is the case. Basically what has happened here, instead of minus 1 by thing, so this will be theta 1, my cos theta 2 will be plus 1 by 7 under root 3 by 2. You just compute this, you will get this, because the direction of either G1 or G2 has been interchanged. So basically what I have done, instead of writing phi1 equals to this, I write phi1 equals to z square minus xyz plus 3x, just the opposite direction. Just interchange one of the directions, hence the sign will change. If I interchange both of the directions, minus into minus becomes plus, sign won't change. But here one of the direction has been interchanged, so sign will change and this will become positive. Now if you compute the cos inverse of this, you will get the exact same angle. 3 by 2 under root divided by 7 cos inverse, this will be 79.92. So this is my answer. So as they have asked us our acute angle, right? Acute angle, so answer will be 79.92. So I hope you got the point, right? Generally we define angle between the two surfaces as this. By default this, okay? If they have mentioned nothing, so by default this is the answer. Okay, so this is the first thing that you have to keep in mind. So yeah, do keep these things in mind. So your answer will be this, right? And if they have mentioned obviously acute angle, you will compute the acute angle only. Okay, so let's first understand few properties of del operator, right, with respect to our position vector. So R is our position vector, you already know this. R is a position vector, right? So also I have told you that R vector is a position vector and simple R is x square plus y square plus z square. This is the normal convention to write R. So this is just a scalar point function. Remember, this is a scalar point function. Scalar point function. Okay, and this is a vector point function, right? Vector point function. Now what do we do? Now if I want to take the gradient of R, what is R here? This is simply the scalar point function, because gradient happens only with R, right? Only with what do you say? Only with scalar point function. So this is scalar point function. If I take the gradient of this, what will happen? Here this will be, if I differentiate this with respect to x, then this will be 2x divided by under root x square plus y square into half. So this will be x by under root R I cap plus y by under root R, not under root, simple R j cap plus z divided by R k cap. So x I cap plus y j cap plus z k cap, which is equals to R itself. So that's why we get our result like this, that the gradient of R is simply R cap R vector, position vector by R only. So now if I take the gradient of f of R, something which is a function of R, and R is basically, remember, is a scalar point function, which is equals to under root x square plus z square plus y z under root x square plus y square plus z square. So if I want to take the gradient of this, simply just think like chain rule, right? Simply think like chain rule. Why chain rule? You just differentiate this function with respect to R, then you differentiate the inside function, that is R. And what is the differentiation of inside function? Basically, what is the gradient of inside function? It is R upon R. Basically, R vector, position vector upon R itself. So that is what you do. First, you differentiate the outside function, then you differentiate the inside function. And if I want to take the Laplacian, what is this? Just hold on a second. I don't know what has happened to my throat. Like, yeah, if I want to differentiate the Laplacian twice, then this will be f double dash R plus 2 by R f dash by R, f dash R, right? So basically, if I want to take the Laplacian of this, then I will obviously differentiate this twice, okay, with respect to R. Then I will add the first differentiation with respect to R, and then I will multiply 2 by R, whichever has once differentiation, okay, I will multiply that by 2 by R. So you have to remember this, right? These things you have to remember this. These things you put in short notes. Like, you try to revise your short notes daily and you put in your short notes. Okay, So let's do few examples. From there you will understand what is the gradient of LNR. What will be the gradient of LNR? What you'll do, you will assume this as f of r. Okay, assume this as f of r. So f of r is equals to LNR. So what will be the gradient of f of r? It will be f dash of r, which is 1 by r into r vector upon r. So it will be r vector upon r square. So this will be my answer. Now what is gradient of sine of r? Again I will choose f of r equals to sine of r. So gradient of f of r will be f dash into r upon r. So it will be, sorry for this, cos of r into r vector upon r. Then what is the gradient of this? This is interesting, right? So you have to use the chain rule thrice now. So here again I will assume f of r equals to sine of ln of r. So what will be f dash of r? It will be simply, so not f dash of r, what will be gradient of f of r? Simply f dash of r, right? So it will be simply equals to, I will write this here only, cos of ln r. Then I will differentiate the inside function, which is equals to 1 by r. Then I will differentiate the inside function, which is r, which will be r vector upon r. So overall this will become cos of ln r into r vector just hold on a second. R square. Okay. So this is my answer, right? Cos ln by r square into r. Now what will be the answer to this? So if I want to compute the answer, so this will be simply the gradient of r raised to power n will be okay, let me do this with different color, else I will get confused. This one is the most interesting one, and okay, I don't have space. So whatever, I will compute the next one here, right? I will compute this. So 4 will be basically f of r equals to r raised to power n. So gradient of f of r is equals to what? F dash of r, which is n into n minus 1. Okay, n into r raised to power n minus 1 into r vector upon r. I can further simplify n into r into n minus 2 into r vector. Okay, so this will be my answer to all of the questions. So I hope you're understanding how to compute this, because this will be helpful. Sometimes gate gives question like this in terms of position vector, and you can directly compute this without wasting much time. You see like how difficult it is, right, to compute this if I write in terms of x, y and z, but how simple it became. Just with 2 lines I'm able to find the gradient of this. So that is the beauty of this property. So like let's solve one question according to this property. So find n if the Laplacian of the following function f of r equals to r raised to power n is 0, where r is this. So the Laplacian of this is 0. I told you, right, how to find the Laplacian of this function. So Laplacian of, if you remember correctly, you have to put this in your short notes. Laplacian of f of r will be, first I will take a double derivative, then the function with single derivative will be multiplied by 2 by r f dash of r. And obviously you can observe that I will get a scalar, right? I will get a scalar here. So this is how you remember. You will always get a scalar, not a vector, because you are taking the Laplacian, and the result of Laplacian is a scalar. I told in the first lecture itself. Okay, So this is the case. Now what is f double dash of r? So this will be n into n minus 1 raised to power r into n minus 2, right? This will be my f double dash of r. And so also I had to write this thing that here, right, you don't write in terms of vector. So you write r by r as 1, r this, right, this thing you have to assume as 1 only. Okay, so I forgot to write this. Else, yeah, r vector is not anywhere here, right? I haven't wrote r vector anywhere here, so you ignore r, right, because this is just a scalar function. That's why r vector won't be present over here. So this will be r raised to power n by 2 by r into f dash, which is n r raised to power n minus 1, n into n minus 1 r raised to power n minus 2 plus 2 n r raised to power n minus 2. So obviously what I can do, I can take r raised to power n minus 2 common, right? And they have told us that the Laplacian of this function is 0. So I will equate this with 0. So del square f of r equals to 0 equals to I can take common n into n minus 1. I have taken common n into n minus 1 plus 2n into r raised to power n minus 2. Okay, so either this can be 0 or this can be 0, right? And they have mentioned that n is also not equals to 0, and r obviously is not equals to 0, right? This r is not equals to 0 also. So this will be, if I take this thing in common, n common, n plus 1 into r raised to power n minus 2 is equals to 0, right? So n can either be equals to 0 or n can be equals to minus 1, and if they have eliminated n equals to 0, then obviously only one solution exists, n equals to minus 1, and this will be my answer. Okay, so like this was it for basically the directional derivative and the gradient part. Now we'll study a new topic, that is the divergence of vector point function. So if you are feeling overwhelmed, you can take a break, okay, of 5 minutes, then you can again restart from here, right? So like these are simple things only, but the physical significance is the most important part that we have to understand. So what is the divergence of a vector point function? What is the divergence of a vector point function? Basically, if I have been given a function, right, it is a vector point function. This you have to keep in mind. We apply this operation on vector point function. This you can't forget, right? This you can't forget. Okay, so if I have a vector point function like this, f of x, f of y, f of z, okay, then what will happen? If I take the divergence, basically I'm taking the dot product, okay, of the del operator, right? Del operator. So if I take the dot product of the nebula operator, that will be, if I will just differentiate this x component with respect to x, I will differentiate this y component with respect to y, I will differentiate the z component with respect to z, and I will add them up. And the result, what I will get? I will get a scalar value, right? I will get a scalar value. And what is the significance of the scalar value? That we'll see just in few slides, next few slides. So we'll get a scalar value, okay, after the divergence. So let's first take an example and compute the divergence of these functions, and then we'll understand the physical significance of divergence. So if I want to compute the divergence, right, it's very simple. So computing the divergence of r, what will be it? It will be simply del by del x in of x, which is 1, plus del by del y into of y, which is 1 again, plus del by del z of z, which is again 1. So this will be simply 3. So you observe, right, we get a scalar value. We get a scalar value. And again, if I take the divergence of this second function, it has to be a vector, right? It has to be a vector. This will be what? Del by del x of x cube, because in the I component I have only x cube. 3x square plus del by del y of y cube, which is 3y square, plus del by del z of z cube, which is 3z square. Okay, simple as x square plus y square plus z square, which is simply equals to 3r square. Okay, r is under root x square plus y square plus z square. So you can like simplify like this. Now let's understand the physical significance. So what is the physical significance? So if you don't understand this, that is fine. Just you go to the conclusion and that is enough. Like what I will tell in the conclusion, that part is enough. Okay, because obviously they won't ask you practically, right, what is the physical significance of divergence, but in interviews or to understand this concept much better manner, it may be needed to understand this. So consider we have a motion of fluid having velocity Vx that is flowing through this space. So a fluid is flowing, okay, like a water is flowing, or like you have रंगोली होते हैं ना, रंगोली से हम कुछ करते हैं, मतलब होली के टाइम पे पानी मतलब कलर्स, पानी से कलर्स फेंकते हैं, तो कुछ जा रहा है, फ्लूइड जा रहा है, उस नॉब से निकल रहा है, तो नॉब से निकला यहाँ तक आया, ठीक है, इट केम अंटिल हियर, देन it went inside a box and then it went outside. So the amount of change in the velocity, like initial velocity of this fluid when it was entering a particular box was Vx. Now when exited, the like the velocity of the fluid is a function of x itself, so it became like del Vx plus x, right? Here the velocity is something else that will compute. So v is given as a function of vx, vy, vz, okay, so, and it can be function of x, y, z, anything. Velocity can be function of x, y, z, right? It is a function of x, y, z. The fluid is a function of x, y, z, the velocity of the fluid. Now the fluid entering at this surface S, this is my surface S, okay, this rectangular region, let me just highlight this region. This region is S. So can you tell me what is the fluid entering at this section S? So it is difficult for you to understand because you may not be from the particular background. Electrical people may not be able to understand. The fluid that is entering at this region per second is what? Velocity times area. How is it the case? So if you take an example, velocity means meter per second, right? Meter per second. So in a second, this fluid has traveled some x meter, right? X meter. So x meter of fluid has traveled inside this x meter. And so what is the total volume? Because fluid means how much volume is entering at the surface. Fluid means volume basically. So if x meter has, like the fluid has been inside x meter, so x meter of fluid has been inside this block, okay, and obviously like the fluid is totally filled with this, right, this box. So what is the area? That is del y into del z. So what is the volume that has entered? The volume that has entered is del y into del z into x, right? That is the total volume of fluid that has entered in 1 second. 1 second. So what will be the amount of fluid per second divided by time? So if I divide by time, it will be simply what? X divided by time into area. X by t is velocity, that's why it is velocity times area. If you understood it, well. If you didn't understood it, don't need to understand, because like this is just a proof and this will not be asked, okay, but people who are able to understand, it is good for them. It is good for them. So this will be velocity times area, which is simply equals to, I have to write this in different color. Velocity times area, which is simply equals to, velocity is Vx at that surface S into what? Into area is what? Del y, length is del y, like I have taken a small surface, right? Small surface, like small volume, del x, del y is its y distance and del z is its x distance, okay. So now what I can do, this is what is the unit of this? This is meter cube per second, basically volume entering inside this small box per second, okay. This is also known as the flow rate. This is also known as the flow rate. Now, how much fluid is leaving S dash? Now, what is S dash? S dash is this surface. Okay. S dash is this surface, right? Okay, I will just use some different color. S dash. Okay, so basically how much of it is leaving? It is simply V, I will write here Vx plus del x, because the velocity has changed, times, but I have taken a small volume, right? Hence the volume is small, so the del y and del z haven't changed. They are same only. Okay, so del y times del z. Okay, so now what am I interested in? I'm interested in the net increment or decrement in the fluid flow in the x direction. So like fluid is flowing from all directions. Okay, I haven't told you, but fluid, let's say fluid is flowing from all directions, but I'm only analyzing for x direction for now. So the amount of fluid entering and the amount of fluid outgoing, the difference of those two fluids will be the net increment or decrement at this point, right, of fluid. So how much fluid is increment or decrement? So basically, to find anything in net, right, what we do? We write final minus initial. So what is the final fluid? It is V delta Vx plus delta x. And what is the initial? It is Vx. Obviously, del z, del y and del z are common. Del y and del z are common. Now what is this? This is nothing but del Vx by del x into del x, because this is what? This is del Vx with respect to x, because I am just measuring the increment change in Vx with respect to x direction. So this will be del Vx divided by del x into del x itself, because this I have to cancel, right, as del x tends to 0. So del x, now this is just a proof. Okay, don't like get into this too much, because this will not be asked in your gate examination. So don't break your head in this. Okay, so main thing is solving the questions, but this will help you understand the physical significance. So this is del y, del z. Okay, so now what is the important point? Important point is, now if I find the total increment and decrement in fluid flow in all directions, right? So if I am computing for all directions, then this will be what? Del v y upon del y into the same volume, and similarly for del z also. So this will be simply equals to del Vx, let me just change the color, del Vx upon del x plus del Vy upon del y plus del Vz upon del z into del x, del y, del z, right? So now if I compute this per unit volume, right, per unit volume, rate of loss or gain of fluid per unit volume, this is per unit volume, like I am dividing del x, del y, del z per unit volume, that will be simply equals to del Vx by del x plus del Vy by del y plus del Vz by del z. So this is what the significance of divergence is. It tells us the net increment or decrement in a fluid or anything, right? Anything in a fluid or field line. So here, if it is positive, right? If it is positive, if here I have a field line, which is a vector field and which is outgoing from this point, right? Everything is outgoing. So it is increasing. I'm giving something, right? I'm giving something. From this point, I'm increasing, right? Initially it was 0, then I'm increasing. So it is positive. I'm giving something. So here, if I take the divergence of this, will be positive. Now, if something is incoming, right? I had 0 and everything is incoming towards me. So like inside, I'm getting maximum, right? Everything is coming towards me. I'm not giving anything. the light source, right? It is like a light source, right? You think like this is a light source, and I'm absorbing anything. If I'm absorbing, then I'm negative, right? Then I'm neutralizing myself. So obviously here, this is like a sink. Hence, del dot F will be 0. This is like a light source. You can understand this like a light source. Okay, and sink, I don't know, like a black hole. You can assume this is like a black hole, right? It absorbs everything, right? Or your wash machine sink, whatever you want to assume, black hole. This is like a more modernized example. Okay, so this is a sink point. This is a sink point. This P point, right? This P point is the sink point and the source point respectively. So I want to mark this point here, source point and sink point. Okay, so these are very important points. There are more examples. So when this divergence of a particular scalar field function becomes 0, okay, then it is said that fluid is incompressible. Basically, whatever fluid is incoming, same thing is outgoing. It is not getting compressed inside that, right? Hence it is incompressible. Then fluid is called incompressible. So if in the question they have told us that this vector field is incompressible, or the net flux doesn't change, okay, or it is solenoidal, then it will be, we have to do divergence equals to 0. Solenoidal I will also explain later slide. So like it can also be understood by the concept of electric flux density. If I feel lines like this, so before this point P, right, before this point P, what was happening? My field lines were lower. After this, they become higher. So if they become higher, that means it is increasing after reaching me. So obviously I can become a source. Obviously my divergence will be greater than 0. Now before this point P, the field lines were greater. After this, the field lines became lower. Hence I absorb something. So I became, like, I am the negative person, right? So I have to absorb to neutralize myself. That is the thing. Now this, when divergence is equals to 0, that means the magnitude before the field lines and after the field lines, the strength of the field lines are same. The strength of the field lines are same. Before the strength was more, after it is less, hence negative. Before it was less, after it is more, hence positive. So another definition for when the divergence is 0, it is known as solenoidal field, or it can also be said as divergence free field. If it is told as divergence free, solenoidal field, all those things are meaning the same thing only. Basically, you have to do one thing, that you have to equate the divergence of that particular vector field equals to, okay, sorry, equals to 0. So when the divergence of a particular field is 0 for all points x, y and z, such a vector is called solenoidal field. Now here, right, it is incompressible at that point, but for if it is 0 for all the points x, y and z, then it is called as solenoidal field. Okay, that is the definition. Now what are the examples? Magnetic field lines, any field lines forming closed loop. So here, right, I see it is forming a closed loop. So whatever comes in at this point, if I just take this point, right, okay, I have to take another color. Whatever comes in at this point will go out from here, right? Whatever comes in at this point will go out for it. Same strength and same thing goes out. Hence, this will be 0. Hence, it is told that del dot B, right? Del dot P is known as the electric flux density. Basically, the magnetic field is always 0. Okay. In EM.tech, we will study this. Don't worry. In EM.tech, we'll study this. Okay. Hence, B will be a solenoidal vector field. I can safely say B will be a, just hold on, solenoidal vector field, right? Hence B will be a solenoidal vector field. Okay, so like let's compute this. Calculate the value of lambda if A is divergence free. Basically, it is telling that the divergence of this particular scalar field, scalar point function will be, sorry, vector point function will be 0. So we'll do that. We'll do del dot f equals to 0. Hence this will become, let me write in some other color, this will be 2x delta y plus 4xy minus 2xy equals to 0. So if I take common xy, this will be 6 lambda, okay, minus 2, right? 6 lambda minus 2. 4xy minus 6 lambda minus 2. Fine. Okay, no, I'm doing this correct, right? This is lambda only, right? So this will only be 2 lambda. Like here I have lambda also, so I can take this common. This will be 2 lambda separately, and this will become overall 2 xy. So I can take common 2 like xy only from here. So this will be 2 lambda plus 2. So from here I can directly write my lambda is equals to minus 1. This is my answer, right? NAD type question. So this is my answer. So this is basically about the divergence. Now we'll try to understand about curl of a vector, right? So we saw, right, the divergence of a vector point field is a scalar function. Now the curl of a vector point field will be a vector function, so it will be a vector. So this is the result of the vector. If I have a vector point function like this, the curl of this will be the determinant of this particular matrix. Okay, ijk del by del x, del by del y, del by z, del z, and fx is the function here, fy is the function here, and fz is the function here. And do note that this will be a vector point function, right? This will be a vector. Okay, so let's first compute the curl of few functions, and we'll understand how to find the curl actually. So let's first compute the curl of R itself. So what is the curl of R? The curl of R will be, it can be written like this: del cross R equals to I j k x y z x cube y cube z cube. Sorry, I'm sorry. This will be del by del x, del by del y, del by del x. Okay, so this, right, this is simply differentiation of this, which is 0. This is again 0. So this is 0 I cap plus 0 j cap plus 0 k cap, which is equals to a null vector. Do keep this in mind. This is not equals to 0. Not equals to 0. This is not a scalar field, right? This will be a null vector explicitly. So you don't write 0. You write 0, then a bar sign above, right? Keep that in mind. Now let's compute del cross A. If I want to compute del cross A, I'll do the same thing again. I'll copy this chin again. This will be x cube, this will be y cube, this will be z cube, right? Now if you compute this, you will see this will also be equals to null vector itself. Now there is one property of curl, right, that I will explain later on, and there I will tell you why we are getting null vector specifically. So first key point is about the position vector. So if you remember all this will be helpful for you. If you don't, that's fine, but this one you remember, right? These you can compute in seconds. This one will take like 30 seconds, 20 seconds. So we know what is R vector and what is R, right? So if I take the gradient of R, it will be R vector upon R. If I take the divergence of R, it will be 3. If I take the curl of R, it will be 0, right? And why it is 0, I will explain in the 4-5 slides after this. But first, let us understand what is the physical significance of curl of a function. Okay, so it represents the circulation or rotational effect of a vector field to rotate a point P. Okay, how much is the strength of the field to rotate that particular point. So with point, it is pretty difficult for us to visualize. We'll take a box. So if I take a box here, okay, very small box, right? Very small box, which is almost equal to a point. So what is happening on the right hand side? On the right hand side, the field is much more higher, right? If on the right hand side the field value is much more higher, then what will happen? It will have more force. If the right hand side has more force and the left hand side has less force, what will happen? There will be moment, right? There will be moment. If you have studied in physics, there is moment. There will be rotation about this point P. So the right hand side has more force, the left hand side has less force. So the box will rotate in the anti-clockwise direction. Box will rotate in the anti-clockwise direction. So if it rotates in the anti-clockwise direction, as the right hand side has more force, left hand side has less force, it will rotate like this in the anti-clockwise direction. Now you rotate your thumb in the anti-clockwise direction in front of your face. What is happening? You are seeing the thumb that is coming towards you. It means the arrow is coming towards you. If the arrow is coming towards you, what you will see? You will see just a dot, right? You will not see the behind of the arrow. You are seeing the in front of the arrow. It is going to kill you. So basically you will see a dot. So that's why you will put a dot over here. This will be very helpful in EMFT. Okay, just hold on a second. I will come in a second. Yeah, sorry for the interruption. So here I was telling that this will rotate along this direction. So here this rotates in this direction. Hence the curl is definitely not a zero vector. It has some direction. And what is the direction? Direction is towards you, right? Outside the skin. Okay. So first of all, what we know, our curl of this, right? Curl of this A vector at point P is not equals to null vector. And what is the direction? I will just use some different color. Yeah. What is the direction? Direction is outwards, right? Outwards. Okay. Basically, if you see it from the screen, it's coming towards you. So hence it is outwards. Now let's take for the second case. Again, I will place a box, very small box. So if I place a very small box, this time the force on the right hand side is more than the left hand side. So again, some torque is getting produced, right? Some torque is getting produced. Now if you rotate your hand, what will happen? You are seeing the behind of your hand, right? Behind, and it is going inwards. It is going inwards. So here the force is like this. The torque is like this. Hence it is going inwards. Now if it is going inwards, that means you are seeing the behind of the arrow. That means basically it is a cross sign. Right? Arrow has some cross in it. So it will be a cross sign. So this will be useful in your EMFT. So this, right, I will again copy this. This time it will be obviously non-zero, but direction will be inwards. Okay. So let's take few more examples. So here, what will the curl? So if I am at this point, right? If I am at this point, and now if I place a box over here, so what is happening? Is the curl 0 or non-zero? So curl here, right? Obviously this field itself has a circular motion, right? This field itself has a circular motion. If I place a box somewhere around here, this will also try to rotate this. This will also try to rotate this, right? This will also try to rotate this. So obviously my curl, as this point is also rotating, okay, hence curl again will be non-zero. And what will be the direction? As we can observe, right, this field is getting increased, right? This field is getting increased as we go on. So on the right hand side, if I place a box over here, if I place an imaginary box over here, right, just lightly if I place a box over here, on the right hand side there is more field than on the left hand side, because as I move outwards the field is increasing. Hence this has a rotating tendency like this. So if it has a rotating tendency like this, then it is inwards. Then it is inwards, right? If it has a rotating tendency like this, so it will be obviously inwards. Okay. Yeah. So this will be basically cross. This will be cross. Okay, so I hope you got the point, right? As I'm moving away from this center point, the field strength is increasing. Hence, just at the right of this box, the field strength is more. Just at the left of this box, the field strength is less. So it will get a rotatory motion like this, right? So I have to rotate my hands like this, and it is inwards, going into the screen or whatever you want to say. So hence it is inwards. Then again, for the other case, right? What will happen? As I move along this, the field strength is increasing, and what is happening? Again, on the right hand side, I'll just take this. This time it is rotating in this direction. As it is rotating in this direction, this strength is more, but in the opposite direction. Hence, what is happening? It is like this, right? Like this. My hand I have to rotate like this, which is coming towards me. This thumb is coming towards me. Hence, what I'm seeing? I'm seeing a dot. Hence, the direction is outside, and obviously curl is not 0 because it has some torque associated with it. So curl will not be 0 and it will be outwards. Hence, here there will be a dot. Okay, dot means towards me, cross means going away from me. Okay, so this is the case. But what is 0 here? Is anything 0? We just learned from an example, right, that the divergence will be 0 of this, because whatever is coming in is going out. Same thing only, right? Hence, the divergence will be 0, but curl is not 0. So it is not necessary that even if divergence is 0, curl has to be 0 also. So for both of these cases, the divergence is 0, right? Whatever is coming in is going out, whatever is coming in is going out. Okay, so let's go for the case E. Now in this case, does this have a rotation tendency? If I keep my box here, right, if I keep my box here, just left, just right, the field strength is same. Okay, so if I keep my box here, anywhere you place your box, anywhere, it doesn't matter. Okay, just near this point, on the left hand side also the field strength is same, on the right hand side also field strength is same, right? Hence it doesn't have any rotational action. So what will happen? I'll just copy this thing. This time the curl of A will be 0, and direction, obviously it doesn't have any direction, right? It is irrotational. Like whenever the curl is 0, it is known as irrotational. And what do we know? We just saw an example that whatever is coming in is getting out. Hence the divergence of this will also be 0. This will also be 0. Similarly for this case also, just in the opposite direction, like in the orthogonal direction, the same case will happen for this also, that there will be no rotation, there will be no direction, no rotation, it will be irrotational field. Okay, now what about this? I just told you example, right? This is like a source field, but does this have a rotation action? Okay, so if I place my box over here, so some force is telling me to move this, some force is telling me to move here, there. You have studied in physics, right? The summation of forces. So total net resultant force is 0 in this free body. Hence there will be no rotations itself. Anyways, like the net force was 0 there also, but there was some rotation, right? Here there is no rotation. Everyone is pulling this box, but it is not able to pull it, right? There is no rotation along a direction. So obviously the curl will be 0. Okay, it will be irrotational, but the divergence will be greater than 0, as this is a source point. As I can observe, the strength of the field lines is increasing after this point, right? Hence it is a source point. Similarly for this case also, this case, does this have a rotational effect? I will say yes, right? This is rotating like this, right? Hence if I place a box over here, the net rotation will be in this direction. Hence the curl will also not be 0, and it is rotating in the clockwise direction. So clockwise means inwards, right? Clockwise means inwards. So it will be in the cross direction. So here it will be in the cross direction. So I will write here, this is clockwise, this is anti-clockwise, and this is also previously also was there, right? This is in the clockwise direction, not anti-clockwise. This is in the clockwise direction, and here this is in the clockwise direction, right? This will be not equals to 0. This will be rotational, and okay, I have to change this to copy somewhere. The clockwise direction will be inwards. Clockwise direction. And is the divergence 0? No, it isn't 0, right? Because it is providing something. It is providing, in field lines are increasing after this. Obviously, it will be greater than 0. Greater than 0, right? It will be positive. The divergence will be simply positive. If I can write the A in a better manner, that will be good. Okay, so that is basically what curl means, and I have told like what are irrotational vector fields. Basically, for all x, y and z, the curl of that vector field will be 0 for all. So here I have told the same thing only. The curl of that function will be 0 for all x, y, z. Okay, and what is the example of this? Electrostatic field lines. The curl of electrostatic field lines will be a null vector. Okay, so whenever, not 0, sorry, null vector, it has to be null vector. So whenever the curl of some vector field function is null vector, then it is called a irrotational vector field. Okay, so my bad, it is null vector. Now another thing, if I have a vector field whose x component is only function of x, whose y component is only function of y, and whose z component is only function of z, then the curl of that will also be a null vector. Basically, that field will also be a irrotational vector field. So this will be irrotational. Vector field. Okay, so what does this means? This means the x component is only function of x. This is a shortcut, right? If you see some vector field whose x component is only function of x, this is only function of y, and this is only function of z, then what will happen? Then this will be called a irrotational vector field, right? So like let's do a problem here. Here we have been given a function like scalar point function, and they have told us that it is irrotational vector field. Then I have to compute a plus b minus c. Okay, here I can see that this is not only function of x, not only function of y, not only function of z. So it may so happen, if like the x component is a function of x, y, z, y component x, y, z, and z component function of x, y, z, it may so happen then also the field can become irrotational. But if I have a vector point function whose x component is only function of x, whose y component is only function of y, whose z component is only function of z, then for surely it will be a irrotational function. Then for surely. But if a vector point function is a irrotational vector field, then I cannot surely say that its x component will be only function of x. So the converse is not true. Okay, but if I have a vector field function whose x component is only function of x, whose y component is only function of y, and z component is only function of z, then then it will be surely a irrotational vector field. Okay, then it will be surely a irrotational vector field. Now like we have to compute the curl of this, right? And we have to equate this with 0. So this will be I j k curl, this is del x del y del z. Now I have to give more space to this because I have like the functions are big. So this will be x plus 2y plus az, bx minus 3y minus z, 4x plus 3y plus 2z. Okay, so this will be equals to null vector. If I compute this, this will be del x, this is b, this is what, z, right? This is z actually. My handwriting has gone real bad. So this will be b plus 1 and this is I cap. Okay, oh sorry, so not plus 1, sorry. This I have to do b x, no, I am just dumb, man. So this is like with respect to y, this is c, and with respect to z minus 1, this will be c minus 1. This is I cap, and now I will do this one. This is 4 minus a, and I have a minus sign at the head, so 4 minus a j cap plus this I will cover, this will be b minus 2. So b minus 2 k cap, this has to be equals to null vector. So all the components of a null vector are 0, hence my c has to be equals to 1, my a has to be equals to 4, and my b has to be equals to 2. So this is basically a plus b minus c. I have to compute a plus b minus c, a plus b minus c, which is 5, right? So my answer will be 5 to this question. Okay, this is my answer. So now like there are few properties of del operator. You can put this in your short notes and you can remember. Okay, like these, the last two are simply the null identity. Okay, this I hope you can remember. This is simply like a chain rule thing, right? This is simple only, right? If you are taking the divergence of a plus minus b, you can individually take the divergence. That is fine. Okay, yeah, sorry for the interruption. Basically there was a printing error here. This will be dot. So if I am taking the divergence of this, then what will happen, like if I'm taking the divergence, then for sure I will get a scalar point function here. And this is like more like a vector table product, right? First you do some operation with a far one, then you do the same operation with a near one, right? So if I want to do some operation with a far one, this is a vector and I am applying a del operator. So like I'm just telling you how you can remember this. Okay, just telling you the way to remember this. So if I'm operating the del operator with a vector point function, what I will do? I will do a dot, right, to get a scalar, because at the end I need a scalar. So I will do dot, that means I will do divergence. Exactly, that is what I have done. Then I will multiply the scalar function because that will be outside. Then I will do some operation with the scalar function, and I have to get a like I have to add the output. Finally I have to get a what? I have to get a scalar point function. So with a scalar function I can only do the gradient. I have no option of curl or gradient. So I have no option of divergence or gradient. So I will only do gradient. Then I need a scalar point function in the end. So what I will do, I will take the dot product with this vector, right, because this is on the outside, and if I take the dot product, then I will get a scalar point function. तो बेसिकली क्या हो रहा है यहाँ पे कि मेरे को स्केलर पॉइंट फंक्शन चाहिए, तो आई विल डू एनीथिंग फॉर गेटिंग ए स्केलर पॉइंट फंक्शन. तो पहले यहाँ पे तो पहले मैं दूर के चीज़ के साथ कुछ ऑपरेशन करना चाहता हूँ. तो इफ आई डू दिस ऑपरेशन, देन व्हाट विल हैपन इज दैट दिस विल यील्ड मी ए स्केलर पॉइंट फंक्शन बिकॉज आई एम डूइंग द डाइवर्जेंस. सो उसके बाद और कुछ ज़्यादा सोचने की जरूरत नहीं है. सिंपल जो आउटसाइड में पड़ा है उसको मल्टीप्लिकेशन कर दो. लेकिन एक सिंपल स्केलर पॉइंट फंक्शन के साथ मैं अगर डेल ऑपरेटर यूज कर रहा हूँ तो ओनली आई कैन ओनली डू द टेक द ग्रेडियंट. सो इफ आई कैन टेक ओनली द ग्रेडियंट, इसका मतलब क्या है कि मेरे को एक वेक्टर मिल गया एंड आई डोंट वांट ए वेक्टर बिकॉज एट द एंड आई एम डूइंग द डाइवर्जेंस. तो वेक्टर अगर कर रहा हूँ मैं, वेक्टर मिल रहा है तो मेरे को उसको डॉट करके खत्म करना होगा. तो दैट्स वाई वी टेक द डॉट विद दिस टू गेट द स्केलर. So this is the way to remember basically. So this is very important property. This may be used. Okay, you put this in your short notes. This is very important property, and I told you the way to remember this. Okay, so I will write in the bracket here, need scalar at the end. Okay, we need scalar at the end. Now the same thing if I'm doing curl. If I'm doing curl, it is very simple. What do? You first do some operation with the outside one, like the further one. So basically I need a vector function, so I will do the curl. Okay, I got a vector, fine, and obviously the scalar is getting multiplied, but still I have a vector. Here also, this with the inside, like the nearer function, the del operator to a scalar point function can be only gradient. So gradient, and I will just, what do you do? This is a vector, this is a vector, I can take the curl. So I will take the curl, I will get a vector component. So here, this is also very important. This is also very important. And how to remember? Remember, need a vector at the end. Need a vector at the end. Okay, so these two are called the null identities. Null identities. Okay, so if these two are called the null identities, just hold on a second, let me check if this yeah, everything is recording. This is recording, fine. So these two are called the null identities. And how can you remember? So if you're taking the curl of gradient of a function, then it is zero vector. This is zero vector and this is not simple zero. So curl of a gradient. So what is a gradient of a function? It is a vector that is perpendicular to f. That is perpendicular to f. Okay, and what is this vector? This is the gradient itself. So this, right, this vector, whatever I will get, will be always in the same direction along this. Why is this the case? Basically, let's just see one thing, I will tell you, but first let's understand this. Here I am taking the cross product, like cross product, right, del cross A. If I am taking the curl of this, I will get a vector that will be what? I am taking the cross of this, right? If I am taking the cross, I will get a vector that is perpendicular to both del and A vector. If it is perpendicular to both del and A, so it is perpendicular to this vector. So hence the angle between them will be 90, and I am taking the dot product, so cos 90 will be 0. So here basically I will further write this. This will be del dot something x vector, right? And x is basically perpendicular to both del and A bar, because that is what cross means. If I am taking cross of del and A, it will be mutually perpendicular to both del and A bar, hence theta 90. Hence I will write cos 90 equals to 0. Hence this is 0, right? Hence this is 0. Okay, so what about this? What about this property? This property. So here if I am taking the gradient of a function, okay, if I am taking the gradient of a function, if I take the gradient of a function, right, what I will get? I will get f of, let's say, any function, right, g of x. Okay, this will be only function of x, because all the other ones will be treated as constant and they will vanish to 0, because I am taking the differentiation with respect to x. I cap plus g y, only function of y, j cap plus g z z k cap. Okay, and what have I just told you? I told you, right, if I have something like this, only function of x, only function of y, only function of z in I, j, k direction, hence the curl will be 0. That's why if I take the curl of this, hence the curl of this of del x will be null vector, according to property explained in previous page. Okay, trust me, no one no one will explain you this way, right? All these properties, they will just tell you to mug up the things. They will not tell you how to mug, right? That is also important, right? So how to remember all this, I have told you with intuition as well, that how can you remember these things. That is the most important part, right? Like I can write all the formulas. I have book, and I will send you the PDF of the book, and you have to remember, mug up all those things. That is that is not possible. I try to bring intuition as well, as much as possible, to how to remember these things, so that I also can remember, right? How I used to remember, that I want to transfer it to you. Okay, that is the most important part. So now, like, this is just an extra topic. You can skip this. Okay, who are tired, you can skip this, because this is only important for EE, EC and IN part. Okay, basically, how is my del operator computed in all coordinates, basically in cylindrical, spherical. Other branches can skip this. Okay, now Cartesian, you all know x, y, z, and what is h1, h2, h3, I will explain. Okay, so for cylindrical, I have rho, phi and z, or uv, sorry, this is uvw actually. UVW becomes rho, phi, z, okay, instead of x, y and z. So if I want to compute the gradient of a function and it is written in cylindrical coordinate system, then h1 is 1 here, but h1 will be 1 here also, but h2 will be rho. So I'll have 1 by rho df d phi into a, this will be a v cap, basically in the v cap direction, right? If it is in the x cap, y cap direction, it will be a y cap, basically j cap only. But if it is in the phi, it will be a phi cap, df upon dv 1 by h2 plus 1 by h3 df upon dw aw cap. Now what is h3? H3 is 1 only, so it doesn't change. For cylindrical, only a rho comes. If you remember, rho d phi, like that, a rho has extra came here, nothing else. Okay, for spherical, some r square sine theta comes, right? So h2 changes r, and h3 will also change r sine theta. Okay, others will remain same. So if you want to compute the divergence, then the formula will be something like this. You will write 1 by h1, h2, h3, then you will differentiate with respect to u, and you will ignore h1 and you will multiply h2, h3, then you will write au, which was the u component. And similarly for other component, this is actually not u, this is v, and this is w. Okay, so yeah, that is it. And for curl, what you do for curl, again 1 by h1, h2, h3 will be started here, then here h1 into au cap, h2 into av cap, and h3 into aw cap, and this will be del u, del u, del v, and del by del w. And here again h1 will get multiplied, h2 will get multiplied, and h3 will get multiplied. So this will get multiplied twice here. Okay, so this is just a short formula, nothing else. If you remember it very well, if you don't, you have to remember it anyways in the AMFT part, so it doesn't matter. So like who are EECIN, they can see this, or else other branches can skip this. So yeah, thank you for watching, and in this way we are just finished with the differentiation part of the vector calculus, and from the next lecture we'll start the integral vector calculus. So yeah, I will see you in the next lecture.
Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 3A of vector calculus. So what we have studied? We have studied the basics of vector calculus, like basic terms which we just studied in 11th and 12th, and then we studied about vector differential calculus, right? We completed everything from gradient to divergence to curl, and the significance of all those things, right? And then directional derivative. So I hope you have understood the significance, and the significance also may come, like a few theoretical points also may come from there. Okay, so in this lecture we'll start the new topic, that is a vector integral calculus. So here, like, this is a very important topic. You have to listen to each and every word very carefully. Okay, you can't miss anything here, because if you miss anything, you will feel confused at the later stage. So everything is connected. I have tried to connect as much points as possible, summarize as many things as possible, so that you will be able to understand this topic very well, because most students get confused in this topic, and trust me, no one will teach you like this which I am teaching. Okay, so let's start. So what we learn in this lecture? We learn about the
integral vector calculus, like what are the different things that comes under integral vector calculus. Then we'll start with line integral. Okay, like basically the single integration. Then we'll start with conservative vector fields. Like inside the line integral, we understand what does conservative vector fields mean. Okay, so let's get a basic overview of vector calculus, like vector integral calculus. So inside vector integral calculus, you will have three parts. First one is the line integration, then surface integration, then volume integration. Three things. Now, like in line integration, there are also two parts to this. One is the open line integration, another one is the closed line integration. Open means you are not totally covering encircling a surface, right? Okay, you are not going in a loop. Okay, you start from some point and you end at some other point. Okay, you don't start at the same point and then end at the same point. Okay, then it will become a closed integration. I will explain this in the next few slides, don't worry. And for surface integration, the same thing, only just a bit different. That surface, right? Surface means with a like hollow sphere, it is a surface also. What I'm doing, I'm enclosing a volume, right? I'm enclosing a volume. So the surface which encloses a volume, okay, is known as closed surface, and which doesn't enclose a volume, just like this, a bowl. Okay, it's like a paraboloid, right? A bowl. Does it enclose a volume? No, right? Because this upper side is not filled, right? Not covered. This upper side is open. So obviously this is a open surface. And a sphere, right? A sphere is a closed surface. Then we start with volume integration. Obviously volume, we don't visualize 4D things, so volume integration is only open volume integration only. So volume integration only a single one. Okay, so this is just a brief overview. So just keep this in mind. These two are vectors over here, right? Here A is my vector. A is my vector. Vector. Let me just put this here. Vector point function, right? Vector point function. And if you notice carefully, here if you go on to the volume integration, you will see that your A is a scalar point function, because dv, right? Like here I was integrating with respect to ds, and surface has a direction which we'll come to in the next lecture, and dl, the line, right? Line also has a direction, but volume doesn't have a direction with it. Why? All this we'll obviously understand throughout this lectures, right? Next few lectures. So this is a scalar point function. Okay, and what have we studied? Like integral calculus, we have studied integration for real variables in the previous chapters. Real variables, right? Now what are we studying? We're studying integral calculus for vectors, right? Integration of vectors, right? I've told you, right? There are three types of variables. One is real variables, then vector variables, then complex variables. So we are studying this vector variables, integral calculus. And trust me, whatever you studied here, like if you have missed double integration, you have to go through those things, right? Those lectures. If you have studied this real variable part very well, integration, that will help you immensely in vector variables. Next, what we'll study? Like after we finish this chapter, then we'll study complex variables. There will be many things, complex analytic functions, all those things, right? So all those things can be related with vector variables. So with the help of real variables concept, we will be able to understand this vector variables very well, and with the help of the vector variables concept, basically the integration part, we will be able to understand the complex variable part very well. So all these things are interrelated, so you can't miss anything, right? Very important. So yeah, let's understand few key points. The key point is like a function whose value is same at every input is known as a constant function. Basically, I know you didn't understand this with the definition. What do I mean by this? So I have a function, right? I have a function, okay? I have a function, vector point function, which is like this: xi cap plus yj cap plus xy k cap, or xyz k cap. So what happened over here? xyz k cap. Now the important fact is my x, y and z, these variables, right? These variables x, y and z, these are not a function of time, not a function of time. Okay, these are what? The position coordinates. These are not a function of time. Then it's a constant function. Okay, if I give my x input now, okay, at this point of time, or if I give my x input 10 seconds after as 1, it will still remain as 1. It will not change as a function of time. So that is what this constant function means. Now why is this important? Like in sometimes what happens in questions, they use words like this and students get very frightened by these words. They get scared. So I don't want you to get scared. I want you to understand each and everything that what the question is telling us. Okay, so like just wanted to give this keyword, and if I found out more keywords, I will tell you the meanings of those. So yeah, let's start with line integration. So what is a line integration? Line integration, if you have studied physics, that's very well, or if you haven't, just study the work, like just go through for 10 minutes, right, the work done topic in class 11th physics. So if you have studied, then you can correlate, right? What was the work done? If I had moved this small particle, right, let's say I have a small particle over here and I move this small particle from here to here, right, how much work has been done? Because I will need to, like, let's say I have a box over here, I move this box from this point to this point, there must be some energy spent, right, by me. So I have spent some energy. That means some work has been done on the box, because my energy, I have used my energy to move that box. So obviously that work has been done. So how much work has been done? The amount of work is F dot dl. Okay. Now it is integration of F dot dl. Why is it the case? So if I have a small box over here, if I move just a slight length, right, it is known as small length. Okay, if I write this length, right, if I write this length, it is dl vector. Now what is dl vector? You already know, it is the position vector. This is also known as the dr vector. So dr vector equals to xi cap, not x, small movement along x direction, then small movement along y direction, and then small movement along z direction. Okay, so these are the small movements. So what we do, the amount of force that I gave it to this, and now the force, right, the force can be in any direction. Let's say I only gave the force in x direction, so only my box will move in the x direction. So I only want the x component, not other components. If I have given the force on y direction, then obviously I will only want the y component, and which operator gives me only that component. If you remember, it is the dot product. If let's say my force is, I will write my force vector as fx I cap plus fy j cap plus f z k cap. Now let's say all these are 0. I have given only force in this component, so only my box should move in the x direction, it should move in the dx direction. Now which operator gives me that? Which vector operator gives me that? The dot product. If I do the dot product of this f vector, and if all these are 0, then I do the dot product with this, only I cap component will remain, all the other component will be 0. It will be fx dx, and I will, so that will be my work done. Okay, that will be my small work done, dw, incremental work done, right, incremental work done, it will be f dot dl, right, f dot dl. Okay, now I have given the force in this direction. Next moment I give my force in some other direction, and I totally move along this curve a to b. Okay, with the force, right? Okay, and now I'm like making you understand so work done. So this shouldn't be present over here. Sorry, this is my force vector, this is some other, this was something else. Okay, so I will write like I will draw my box over here. This will be my box. Okay, this box has been reached over here. Okay, so so if I want to overall measure how much overall work I have done, so what I will do, I will simply add these up, right? Add these up. So if I add these up discretely, it will be summation. Now if I want to make it a continuous function, okay, at every point I'm adding this up. If I want to make it continuous, what will happen? Obviously I will integrate this, right? I will integrate this. So if I integrate this, it will be f dot dl, and this will be total work done. Okay, total work done will be f dot dl. Now why am I teaching you this? Why am I teaching you physics lecture? So this is not a physics, but this is simply making you understand anything, right? Not just work done. I just took an example of work done. Anything you take, okay, and you apply some force, or if you are in a vector field, if you are in electrostatic field, if you are moving this particle, anything, right? That you can compute with the help of line integration. And this is an example of line integration, and this is how you solve the line integration and the physical significance of line integration. Okay, I just gave you the physical significance. Now let us understand few terms. First one is the open line or open curve. This is also known as, sometimes, mostly, path. Curve is also known as path, locus. Okay, now here the start and end points are different. I already told you previously. Also, the open curve does not enclose an area. Okay, not enclose, it should be encircle, right? Oh yeah, again, look, I am also making mistake. What you do is, most important is, whenever you're talking about line integration, right? Whenever you're talking about lines, curves, you will always associate encircle, because with area, right, we encircle. I will explain just in the next slide. And with surfaces, we enclose. We'll explain all these things. So, but the important point is, it does not encircle an area. Does this encircle an area? Does this encircle an area? You might say, sir, I don't understand what you're saying. So in the next slide, everything will get cleared. Okay, so the most important point is this one. The start and end points are different for a curve, then it is called as a open curve or open line integration. Now let's come to the closed line or closed path integration. So this is also known as curve, closed curve, closed curve, or closed loop. Okay, I hope you know loop already. Okay, so here the start and end points are identical for the curve. Here it was different, and the closed line will encircle an area or a surface. It will encircle. You can see, if I start from here and I move, okay, I am moving in this direction, I move along this direction, I am coming back to the same point again. And the important point, does it encircle any area? Okay, if this is a sandbox or a square box, right, this line encircles this, goes along the boundaries. So that means I am encircling this area, right, along the boundaries. That's why we always associate closed line integration with encircling of area, because I'm encircling it, I'm not enclosing it. Enclosing means totally closing it down, right? Closing it down and closing a volume, and that will be associated with surface. Okay, for now, always when you're talking about closed line integration, you will talk about encircle. Now it may so happen sometimes teachers also may replace encircle and enclose. Okay, but you don't get confused, you know what it is. But if they are getting confused, don't worry, you will say, okay, they have done some error, I will just do the question, because question will be still the same. If they write encircle or enclose, it doesn't matter. Just for your clarity, I'm explaining all these things. Okay, still you solve the question. So here, what shape does it cover? It covers a square, right? It covers a square. This also, if I start from here and move along this direction, the direction has been given this time, move along this direction, what is, I'm enclosing a circle, right? Not enclosing, encircling a circle. Then again, if I start from A and then again I come back to this, right, through a different path, this is also encircling a area. Okay, so this, right, this is known as the closed line integration. If I move from this point and then I'm like integrate this with respect to a vector field or something, this will be a closed line integration, because I'm coming back to same point again. But here I'm not coming back to same point. I just moved along a field. There is a field, okay, electrostatic field, magnetic field. Electrical people can understand from this. They can like take the analogy from this. If I move along this field, I'm not coming back, okay, I'm on different point, and it does not encircle any area. Does it encircle any area? No, right? It doesn't encircle any area. So that is the difference between open and closed surface. Now one more thing, this closed line integration, we can break it down into many small open line integration, just like here, right? We broke it down into open line integration. This also we can do that. So how can we break it down? So I'm moving from this point to this point, okay, I'm moving from this point to this point. So I will name this path as 1. So this becomes a different open line integration. Then I'm moving from this point to this point. So I will name this A, B, C, D. Then this is second path. This is third path. This is the fourth path. Again, I'm coming back to A. Okay. So I can break it down in 4 open line integrations. So what can I write? I can write here. I can take the first curve, not the closed, this one won't be closed. So here, right, whenever there is a circle, that means it's a closed curve. Whenever there isn't a circle, that means it's a open line integration. So this is also a very important notation. So now I am going from along the curve C1. So this first path is C1. This will be some f dot dl. Then I will add C2. This will be also f dot dl plus C3 f dot dl plus C4 f dot dl. Okay, so I have broken this down, closed line integration, into 4 parts. Now when do we need to do this? So this is always universal, right? You can always do this, but like why do we need to do this? Why do we need to break down the closed line integration? The reason is, sometimes what happens at this point, right, the function may not be continuous, so we won't be able to integrate. So during definite integration also, you remember, right, take a break property. Exactly the same thing we're doing over here. We're taking a break. We're not integrating here because the function is not defined, so we're just integrating just after that and just before that, so just for our own convenience. So this property, if you remember, this is like a take a break property. Take a break property. That's why I told you, whoever has studied integral calculus of real variables, they will feel very comfortable here. Take a break. So this I can write in terms of summation. I equals to 1 to 4 integration Ci f dot dl. Okay, just to make you understand this point, that we can break down closed line integration into small parts. Now obviously we have studied like this so much theory. Let's try to implement something, right? So the question is asking us to evaluate the what is this? Is this closed line or a open line? This is a open line. Here there isn't a circle over here. That means this is a open curve where function is this. You have to evaluate this integration where C is the curve joining points 0, 0 and 2, 2, but they haven't mentioned the path. Path is also very important, right? So for solving any like line integration, you need the path and also the function itself. Okay, path and function. So they have mentioned the curve will be like this. First one is this, second one is this. Okay, it will go through like this. Now what does it mean? So first let me solve this first example, then you will try to solve the second one, right? Second one is easier one. So what is this question telling us is, I have my xy coordinates over here and it is moving along this path from point 0, 0 to 2, 2. So 0, 0 is here only. Obviously that has to be included in this path also. 0, 0 and 2, 2 will be somewhere around here. 2, 2. Okay, and you can draw the path simply. It will be locus, like what is it? It is like a parabola. So here it will be like this, right? It will be like this. Okay, and I'm going from 0, 0 to 2, 2. So the direction will be like this. Okay, So you have to always take care of this direction, right? From where you're going, direction important. Okay, so you have to take care. From 0, 0 I'm going to 2, 2, so my direction will be along this direction. Okay, so basically what I'm saying, this is in 2D, so my dx will be what? Not dx, sorry, dr vector will be dx I cap plus dy j cap. Now we have to compute this. Okay, so let me compute this. Let me write this down first. Okay, this is along this curve C, and if I do the dot product, this will be 3xy dx plus y square dy. Now this one I can easily solve, but this one right here, y is also present, so I have to change y in terms of x, and I know what is y in terms of x. This is the I will always follow this curve when I'm moving. So here, what is the equation of this curve? The equation of this curve is y equals to 2x squared. So I simply replace this y value here, right? And if you want to simply convert everything into one variable, that also you can do. You know, y value you put over here, you put over here also, it will be 2x whole square. Then what is dy? You just differentiate this, right? If I differentiate this, okay, I go and find some other value. If I differentiate this, this will be dy equals to 4x dx, right? Basically dy dx equals to 4x. I put the dx which was in the bottom on the right hand side, so it becomes 4x. So this will be 3x. Y is simply, so I will not replace it into single variable, but you can do that, right? So this is my, basically this is my step 1, right? This is my step 1. Write the integration. Then step 2 is identify the path, but we have already identified the path. Step 2 is identify the path, which is y equals to 2x square, and also we have written dy equals to 4x dx. Then you simply integrate, you simply compute the integration, right? Okay, so if I compute, let's name this as I1 f dot dr. What will be this? This will be now we'll replace here, this will be 3x into 2x square dx. Now how is my x moving? X is going from 0 to 1. If you observe here carefully, x is going from 0 to, okay, not 1, sorry, 0 to 2. Okay, sorry, x is actually going from 0 to 1. I made a mistake over here. This will not be yeah, my bad. X is actually going from 0 to 1. I by mistake put here 2. Yeah, that's my bad. This point isn't I know you have been screaming at me since now that this should be 1, sir, this should be 1, sir. Yeah, this should be 1. Okay, this is 1 comma 0 point, because if I put x equals to 1, this will be y equals to 2. So x is going from 0 comma 1. Okay, plus 0 to 2, y is going from 0 to 2, and this is simply y square dy. Now you can simply compute this, right? Okay, this is simple integration. So this will be 6 by 3, not 3, 4 x raised to power 4 0 to 1 plus 1 by 3 y cube 0 to 2. So this will be 3 by 2 plus this is 8 by 3. So this will be now if I multiply this with 3, this will be 9 plus this will be 216, right? 9 plus 16. Okay, and this is 3 by 2 and 9 plus 16. Yeah, so this will be divided by 6 itself. doing this? I'm just checking am I doing this correctly or not. So this will be 25 by 6. Okay, so this will be my answer. Basically this will be my answer. Okay, so now I have computed the answer, right, for the first case. So this is for the first one, this is for the first one. Okay, now for the second, can you pause the video and try for yourself for the second one and tell me what is the answer. Okay, so I will start the second one. Obviously the step 1 will be same. First I have to write this integration, right? This is a step 1, so I have to understand what is the integration that I have to evaluate. Next I will write the path. So what is the path this time? What is the path this time, right? The path is not very weird. The path is very good because it is a straight line, y equals to 2x, simple straight line. So this time instead of going through this curvy path, I'm going to the same end point but with a straight path. We all love straight paths, right? We don't like curved paths. Only for a few cases we like curved things. So if we are going in the straight path, so this, right, this path is y equals to 2x. This is my C2 path. Okay, I will name this as C1 path and this is C2 path. So let me name this as C1 path. Okay, so this will become C1 and yeah, this will become C1 and this becomes C2. Okay, so we have identified the path. Again I will do the same thing, right? I will do the same thing, that identify the path and replace y with everything, right? Replace y with everything. So y equals to 2x this time. So dy will be equals to simply only what? Only 2 dx, right? Only 2 dx. So even though we don't need this, but this may be needed in next like later questions, right? That's why I'm already teaching you this. So step 3 is simply compute. Step 3 is compute. So let's go to the step 3. We have to simply compute, right? So if you have to simply compute this, you can write your I2 is going, this is 3x into 2x dx. X is going from 0 to 1 plus dy, y is going from 0 to 2 and this will be y square dy. This will be same only, right? Yeah. So if I compute this, my I2 will be this x square, right? So 3, this will be 2x to x cube 0 to 1, 0 to 1 plus this will be 1 by 3 y cube 0 to 2. So this will be 2 plus 8 by 3, this will be 14 by 3 units. Okay, so like this how you solve. We can solve this using another way also. This was like method 1, okay, without replacing this dy, but we could have converted everything into a single variable. So this is method 1, okay, and method 2, what you can do, you can convert everything in terms of x. Convert in terms of x. Okay, so if I want to do that, so what I will do, this integration, right, this will be 0 to 1 3x times 2x dx. This is fine, right? But y I will convert now, right? Y won't go to 0 to 2. Y I will convert as x. So what is y equals to? Y equals to 2x. So this will be y square. So y square will be 2x whole square. And what is dy? dy I have written over here, right? dy is 2 dx. So this will also be 2 dx. And limits I will obviously put according to dx, where my x is moving. X is moving from 0 to 1. So obviously I can compute this all at once. This will be 2x cube 0 to 1 plus this will be 4 by 3 x cube zero to 1. Oh no, not 4, sorry, this will be 8, right? Because this is 2 square, so this will be 8 by 3. So again we are getting the same answer. So either way you solve, you will get the same answer. But what is interesting point over here is, what do I observe is that when I am moving from 0, 0 to 1, 2, okay, according to this field, right? So I have this field. What does this field represent? This represents a field basically. So what does this field represent? This represents that along the xy plane, right? I have a field, electrostatic field, magnetic field, any field, right? We are in this atmosphere right now. We are in this earth. We have gravitational field, which is always trying to take us down, right? Always trying to take us down. So there is also some field, okay? And I am trying to move along this field, okay? If I am trying to move up, right? Up. So gravitational force will try to bring me down, right? This is like that only. So I have some field, okay? And if I am trying to move from this 0, 0 to 1, 2, so this much amount of work is needed. Okay, this much amount of work is needed if I'm moving along this path, but the endpoints are same. But now if I'm moving the same endpoints but in a straight line, the work done required is much lower. Which one will you choose? You'll choose obviously the lower work done, okay? But is there any physical significance of this? There is, right? There is. So basically the key point is I1 is not equals to I2. Work done different. Work done different. That means my field, right? My field F is a F vector is a non-conservative vector point function. Now what does it mean? I have said big words here, or sometimes they are also called fields also, okay? I will write fields. Okay, what does it mean? So basically I will explain this definition just in the next few slides, but the crux of this is that it should not matter whether you move, like the endpoint should remain. If the endpoints are same, it should not matter whether you move through this curved path or straight path. It depends on me, right? Whichever way I want to move, I will move. Okay, so that is what this conservative field means. So if there is a conservative field, there's a work done if I move along this parabola, or if I move in this straight line, or if I move some weird shape, it wouldn't matter. So our computation will be simpler if we already know it is a conservative field. So if there is, let's say I can't go straight from here to there, right? So there is some in between, there is some blockage or guard, there is some. So I want to go from other path, but it's good to know that the work done will be same. So I will follow some other path. Okay, it depends upon me. So like I'm just giving you an analogy, but the main crux is like for a conservative vector field, it should be path independent. Whichever path I choose, it doesn't matter. The work done should remain changed. All this I have written in very well manner in the next few slides. So first let's understand about line integration and how should be your approach. First of all, you write this line integration in this format, right? You just remove the vector portion. Remove the vector portion. Okay, remove vectors. Remove vectors. Then you identify C and plot it. Okay, you identify C, like I identified parabola and I plotted it. I identified straight line, I plotted it. Okay, you plot it. Then if your C is a 2D graph, then you just transform to single variable and solve, or you don't need to transform to single variable. Like if it is with respect to y, you write that expression which is in front of dy as a function of y, and if it is with respect to x, you write that as a function of x. And same for 3D. Now if it is a 3D line, then you use parametric transformations. So this is the simple parametric transformations. I know you have done this in childhood. Just let's get a quick revision of this. If I have 2 points in 3D and I'm moving in a straight line, right? So what you do, when I will solve the questions, this will automatically get into your head. This will be in autopilot. Don't need to remember this. This will be in autopilot. Don't worry. Okay. So, but first I will write x. Okay, because I have to write in terms of some function, right? So x is a variable. Then if I am writing this, then in the bottom you can follow any other. You can either follow x2 minus x1 or x1 minus x2, but all the others which follow, they have to follow the same order. Okay, so this only you have to remember, follow the same order. If you're writing x2 over here, that's fine, but here also you have to write y2. Okay, I myself has done this wrong. This will be y1. Okay, whatever you're writing over here, right, all of this has to follow the same order. So I will write this. Follow the same order. Okay, so whatever you write, you follow the same order. So another important point is the limits that we put should be in the direction of the C, along which you are moving. You are moving from 0, 0 to 1, 2. So x should be 0 to 1, y should be 0 to 2. So limits should be in direction of C. Okay, so these should be my limits. So another like short notes I forgot to give you previously, like in vector algebra chapter, this you study in your school days, basically how to compute the area of triangle in 3D. So you can use this determinant formula. Okay, just if you write x1 over here, follow the same pattern, x1 x2 x3 y1 y2 y3 1 1 1, or you can take the transpose as well, x1 x2 x3 y1 y2 y3 then 1 1 1, whichever suits you, right? Whichever suits you, or 1 1 1 then x1 x2 x3 y1 y2 y2 y3. You can take the transpose of this. Okay, so this is basically the formula for area of a triangle in 3D. This I forgot to mention in the vector algebra lecture. So this you should study in the vector algebra lecture itself, right? So like this is forming a triangle and what is the area of the triangle. Okay, sometimes it is also very useful to you to compute this in seconds. Okay, so yeah, this was about the that thing. Now like you can parameterize in different manners. If it is a 3D curve line, 3D line, then you can parameterize like this, right? You can equate this with t, and I converted everything into a single variable, then I can simply solve. Also the limits of t, I will tell you how to compute the limits of t. Now if you have been given a circle like curve, you can parameterize like this, right? It is a line integral, so obviously I am not covering a circle. Do remember, radius is fixed. It is not covering a surface. Radius is fixed. Radius is fixed. It is not variable, so it won't be rho. Rho won't come over here. So you can simply use this substitution. So I have explained this hundreds of times. I don't want to explain it again. And for ellipse, right? Ellipse, what happens? The radius, the major axis and the minor axis are different. So you can write x as a cos theta. Okay, a cos theta is a cos phi. Sorry, a cos phi. But y as b sin phi. Y as b sin phi. That is what you can do, because if we replace here x squared by a square plus y squared by b square, x as a cos phi and y as b sin phi, what will happen? It will be equals to 1, because cos square phi plus sin square phi will be 1, right? So it is satisfying this equation. So you can take the replacement like this. Here just instead of a, it will be, okay? And obviously my phi will always go along this full circle, okay? 2 pi, or if I am covering half circle, you will be 0 to pi. I hope you understand how to take the limits. And I like this dx is simple only. A and b are constant, so I will differentiate only with respect to phi. Okay, this is about how you solve for open line integration with parameterization. Okay, if you have given curve like this or curve like this or straight line 3D. If you haven't given this standard curves, then you have to solve in general method. That way I solved just in the first question. So now let us understand what is a non-conservative vector field. So basically a non-conservative vector field is nothing but simply these conditions has to match, right? If I am taking the open line integration of a vector field, then the integration or the work done, you can say, should depend on the endpoints. Okay, if the endpoints are changed, then obviously the work done will obviously be changed. But even if the work endpoints are same, if I follow a different path, okay, between the endpoints, the path also decides how much work done I have to do for a non-conservative vector field. And like, what is the thing? So if I am moving along this path C1 from A to B, this will be some value of integration I1. Okay, this will be some value of integration A to B f dot dl moving along path C1. Now if I am moving along some other path, right? Let's say I'm moving along this path. This is C2. So this will be I2 will be equals to A comma B. The endpoints are same. The endpoints are same. I'm moving along some other path which will be along C2 dl along C2, and let's say again I'm moving, okay, let me color this as orange only, moving along this blue path, right? This is a white path only from left hand side. So I have a field along this way. Let's say I am gravitational field. I'm moving from this point A to B. I can move along this, I can move along this, or I can go straight. So this is the last path. I'm taking this path in the gravitational field. This is C3. This I3 equals to A comma B, taking the integration dl singular integration C3. What is the important point? The important point is I1 will not be equals to I2 will not be equals to I3. As this is a non-conservative field, this is the property of non-conservative field, that if I take three different paths for reaching the same endpoint, the work done won't be same. Basically the integration, single line integration won't be same. The open line integration won't be same. This is the first point, first key point, okay, that I have been trying to explain since like starting of this lecture. Now, what is another point? So if I'm moving in a closed loop, right? If I'm moving in a closed loop, then the single line integration or the work done won't be changed. So let's say I move from this point A to B straight there, and I took some other path, then I came back to same point again from where I started. The work done won't be 0 for a non-conservative field, okay, but for a conservative field it will be 0. So how to derive this basically? So I'm moving in this loop A to B, B to A. I told you, right, we can break a closed line integration into bits of single line integration. So when I'm going from A to B, I can break it down, okay. This will be A to B f dot dl, sorry for the music. Then if I add this from B to A, f dot dl. So I have again come back to the same point again. Now what I can do, we can simply use the property of definite line integration. So if I just swap the limits, it will be negative. A to B. Okay, another important point, this is along some curve. What? This is the curve along C1 and this is the curve along C2. So this will be C1 and this will be C2. So now I am just swapping the limits. C1 minus A to B C2. Okay, so I have just established in the previous slide that these two, right? Sorry, I have to swap the limits also. These two won't be equal. I have just established. Hence, this will obviously, this, as these two are not equal, these two can't be equals to 0, right? These two can't be equals to 0. If these two are equal, then this was equals to 0. But as these two are not equal, they will never be equals to 0, right? So that's why the integration along a closed line integration will always be non-zero for a non-conservative field. So these are basic things that you have to keep in mind. Now let's come to the conservative field. We'll finish this, wrap this up quickly. So basically, if you are in a conservative field, the open line integration, right? Obviously, it always depends upon path endpoints A and B, but it will be independent of the path that we have chosen. If I go from this to this part, or if I go from here to here, right? I will give you the example here. If I'm going from this path, if I'm taking this path, if I'm taking this path, it doesn't matter. The integration will be same. So basically, if I am going from f of AB dot dl along what curve C1, this will be equal C2 C3. Okay, so if I'm like the endpoint is same and I'm taking different paths, then also it will be equal, the work done will be equal. Okay, so like what your homework is, find out whether gravitational field is conservative or not. If I move from here to there and then I come back from here to here, do I make does any work happens? Like if I'm let's say I'm going from stairs from first floor to third floor, then again I'm coming back from third floor to first floor. Now the force or the work done by gravitation, will it be zero or not? Okay, or work done by you will be zero or not, that you figure out. Okay, so basically the crux of this is I1 will be equals to I2 will be equals to I3, and as these are equal, that means obviously the closed line integration, right? The closed line integration f dot dl will be 0. Okay, so that's the basic thing over here. I'll just copy this proof that I was proving here. Everything will be same, every single thing will be same, just at the end these two will be equal. As these two are equal, that means they will cancel out and the answer will be equals to 0. So that is the difference between a conservative and a non-conservative vector field or a function, whatever you want to call. Okay, so here I have summarized every point. For a conservative vector field, the closed line integral is 0. What are the examples? Electrostatic field is a conservative vector field. Magnetostatic field is a non-conservative vector field. So when we will study EMFT, the electrical and EC and IN students, they will study this, then they will understand. Okay, so basically if my field is a conservative field, then what can I conclude from that? Conclusion. Okay, conclusion, I can conclude that if f is a conservative vector point function, then I can conclude that the open line integration of that same f will be independent of path. If I take a straight line or something, so always I will take the easier path, straight line. Generally this will happen whenever you have to compute the open line integration or closed line integration and they haven't provided you the path. So in those cases we have to check for conservativeness. I will come to that. And obviously the closed line integration will be 0 for every closed curve, any closed curve it will be 0. Okay, so these are few basic points, okay, to check the conservativeness. How do we check if a vector field is conservative? We check whether the field is irrotational or not. So if f vector is irrotational, then f will be conservative vector field. Okay, why? We'll understand this in Stokes theorem. Okay, this will come to in Stokes theorem. But do keep in mind, this is not the only condition okay, for it to be conservative. It may so happen even if my vector f is rotational, it is not irrotational, then f may or may not be conservative. It may or may not be conservative. It is not necessary that if f is rotational that it will not be conservative. We will come to this in like the theorems part of integration. Okay, for now I'm just going through this point. Now if circulation of or closed line integral of f is 0, then f may or may not be irrotational. Basically the same point I'm just telling over here. If f is conservative, it may or may not happen that f is irrotational, but if f is irrotational, then 100% f will be conservative. We'll come to this point when we'll study about vector theorems. Don't worry. Okay, if you don't understand this, don't worry, we'll again come to this point. For now I'm just going through this, whoever are able to understood this point. Now when to use this, what are the key points? When to use this conservatism? When the curve given is very complex, very weird, parabola, circle, or like very weird shape like this, right? It's weird shape like this, then it's a hint that you have to check for conservativeness. Then you will choose a simple curve, right? Like a straight line or something. So here in the question they have asked us to evaluate this if where C is a curve joining 0, 0. So they haven't given us the curve. If they haven't given us the curve, then how will I like simply compute the line integration? So you have to check for conservativeness. So you don't know. Okay, so if I just proceed along this question blindly, just according to what I have taught you. So first you will do the step 1. So in step 2, what you will do? You will write integration of df dot dr. This will be simply x plus y dx plus xy dy. Then you will start with plotting the curve. Now whenever I start to plot the curve, I can write the endpoints. Okay, I can write the endpoints. So endpoints are basically here, right? 0, 0 and 2, 2. So it is x, it is y. Now when I start to plot the curve, I see that they haven't given me the curve. So I can choose anything. I can choose this. I can choose this straight line, or I can choose this. Okay, anything I can choose. So obviously here we have to stop and test for conservativeness. So we'll test for conservativeness. How to check? So I told you, right? If f is irrotational, 100% it will be conservative. Okay, 100% will be conservative. So what do I check? So I check the curl of this. I will check the curl of this. So the curl I will see. Okay, if you compute the curl, this will be 0. So it will be, if along this component I will compute, this will be y and this will be simply 1. So yeah, 1. So y minus 1, so which is not equals to 0, right? Not equals to null vector. So here nothing is conclusive, right? Nothing is conclusive. I'm not sure that f will be conservative or not. Okay, because this is irrotational. Now this is rotational, so I can't say for sure. So I will say here that as this is rotational, I will say that f may or may not be conservative. Okay, so f may or may not be conservative. I am not sure. So obviously I won't be able to proceed further in this question because I don't know, I don't have any other tools to compute the conservativeness. So I will say I have insufficient data. Insufficient data. But what you can do is here like you can compute the closed line integration. Then also you can understand if the closed line integration, you take any random path and you compute the closed line integration, you see that whether it is coming as 0 or not. If it is coming 0, it may be conservative. Then you have to take another closed line integration and so on, right? So yeah, this will be hectic. So that's why you will tell that you have insufficient data. So if I modify the question now, if I modify the question, okay, and if I change my vector field, again no path given, again I will say no path given. So you will check for del cross f, the conservativeness. I have changed my vector field. So this time if you compute del cross f, you will see that my del cross f is coming as 0 vector, right? Del cross f is coming as 0 vector. Now if del cross f is coming as 0 vector, what does it mean? Like you compute the del cross f, you will see 0 vector. It means I choose any path, it doesn't matter. I will get my answer. I will get to my answer, right? So I will choose the easier path. So I'm moving from on the x-axis. I'm moving from 0, 0 to 2, 2. So I'll choose the easier path. That will be C. So here I can choose the easier path, right? C. So what is this? What is this curve? What is the equation of this curve? The equation of this curve is simply y equals to x only, right? Y equals to x. So now you can follow your steps. Now you have all the data. You can simply compute the single line integration. So single line integration, f dot dr equals to x dx plus y dy integration. So y is going from 0 to 2, x is going from 0 to 2, and x is y. Anyways, I don't need this, right? Anyways, I can simply compute. So it will be simply equals to x square by 2. So 1 by 2 x square 0 to 2 plus 1 by 2 y square 0 to 2. It will be 2 plus 2, 4 units. Now what is the homework for you? The homework for you is you try to compute the same integration, okay, in this path. Okay, so this will be, what is the equation? Can you tell me the equation? Okay, the equation will be y equals to x square by 2, because if I put 2 over here, my y will be 2 also. So this you compute, right? This you compute, okay, f dot dr. This is the homework for you. So let's now try to solve few questions. Let me just drink a bit of water, then I will start again. Yeah, so let's solve this question. Here they have given us the field and they have told us the curve is a line joining these points. So this is a line in 3D, right? Line in 3D. So first of all, I notice that this is a line in 3D. So I'll write line in 3D. So I will use that conversion, right? T conversion. So before that, I will use the step 1. So first I will write my integration f dot dr. So integration f dot dr equals to x minus yz dx plus xz dy plus 2y plus 3. Okay, now I am computing the integration, okay, along the closed path. This will be dy also. Okay, so basically it is a line in 3D. So here I have 2 points and I'm going along a line, okay, in 3-dimension space. So what to do? Along this, right, from 1, 0, 1 to 1, 1, 1. If you notice carefully, only my y coordinate is changing, everything else is same, right? So like just hold on a second, have I done something wrong? I'm just checking. Okay, maybe I have done something wrong. This will also be 0, this will not be 1, this will also be 0. Okay, hold on, no, am I correct? No, this won't be 0. So like yeah, what I was saying is, can you notice one thing, that my x is not changing and my z is not changing. So what I can write is that change in x is 0 always, change in z is 0 always. Anyways, this will be cleared just after like one minute. So now if you want to parameterize this, how will you write? You write any way you want. If you want to write this first, okay, write this point A first. You can write this point A, you can write this point B first also, it doesn't matter. So this is curve C. So if I am writing this point A first, okay, and then I am writing this point A here again minus point B, this convention I have to follow in the upcoming variables as well, for y as well. So I will write point A. What is point A? Point A is 0. I will write 0. Again I will copy this point A over here, so I will copy this point. And what is point B? It is 1, y equals to 1. This will be z. Point A is 1. Point A I will copy again minus, this will be 1 again, okay, equals to t. Now what you are observing, these are going towards infinity, right? So these are not the things that I will evaluate, okay, because from the bottom itself I am observing that these are going towards infinity. So only I will evaluate this. So what is my y equals to? Y is equals to minus t plus 1, okay, y is equals to minus t plus 1, and my x is always constant. So my x will be what? X will be always equals to 1, because along this curve my x is never changing and my z is also always equals to 1. So that is what my z is equals to. And what is my dy equals to? Dy equals to minus dt, and here if we differentiate, this will be dx equals to 0 and dz equals to 0. That is exactly what I have written at the starting itself, because I knew my x is not changing, okay. So yeah, that is how you convert this into parametrics. So next, obviously you compute the integration. So I'll copy this integration and I will convert the variables. So my x is always 1, so it will be, and okay, this dx is 0, right? Dx is 0, okay, this is dz actually, sorry for that, this will be dz not dy, this will be dz. This will be dz. So now this is dz, this is dz, and okay, now what else is there? So this, right, this is 0, this is 0. So obviously these two are vanished. I have to only compute this. So I have to compute this xz dy, which is simply equals to 1 times 1 dy. And how is my y moving? Or if you want to convert everything in terms of t, so what is dy? Dy is to minus dt. So I'll convert this in minus dt. And how is my t varying? So you vary your y. So how is your y varying? Y is going from 0 to 1. Y is going from 0 to 1. So if I put 0 over here, t will be equals to 1. So y is going from 0 to 1. So t will go from, if I put y equals to 0, t will be equals to 1. If I put y equals to 1, t will be equals to 0. So 1 to 0, just the opposite. Okay. So this will be, you have to understand along curve, right? 1 to 0. So this will be equals to simply 1 unit. Okay. So this will be your answer to this question. Very simple, right? We'll solve another question like this, and this you will understand. So again, right, if I have a f vector which is a force vector, as they have mentioned the units as Newton, find the work done in moving the particle along the line joining the points 0, 0, 0 and 1, 2, 3, and the curve defined by this, okay, going from x equal to 0 to x equals to 2. Okay, so first of all I will solve this, and this one I'll give you as homework. So this what you do, again the same thing. This time I will not for if you want to find work done, what is work done? Work done, I have told you at the start of this lecture, it is f dot dl along the curve, or dr you want to say. So in our case, what is it equals to? It is equals to 3x square dx plus 2xz minus y dy plus z dz. Now obviously what is the curve? Again I will copy all these things. Okay, I just copy all these things because I don't want to work again for the same thing. This time the points obviously has been changed. I will just move this curve a bit to totally join the curve, and this also will copy here, right? Thus the endpoints will change, right? Endpoints will change, and here dx dy dz nothing is 0, because if you observe it carefully, I am going from 0, 0, 0 to 1, 2, 3. Two, 3. So this will be, now you follow any convention, right? You follow any convention, it doesn't matter. This time, right, I will put here x2, it doesn't matter, but the same convention has to be followed here also. That is the most important point. But yeah, you can put that, but what I am seeing easier is if I put 0 over here and if I put 0 over here, that will be much more easier for me because my start points. So I will put my start points at these places. That convention I have to follow here also. So starting point I will put here, but here, right, here I will put the ending point. What is the ending point? It is 1. For x it is 1. Starting points and then ending point, which is 2. Starting points and then ending points. Same convention you have to follow. Don't need to remember anything, right? You follow whatever convention you like, but that same convention you need to follow. So now x will be equals to t, y will be equals to 2t, and z will be equals to 3t. Now dx will be equals to dt, dy will be equals to 2 dt, and dz will be equals to 3 dt. Now what is the important point? The important point is how is my limit of t changing. So limit of t, if you observe it carefully, you try to compute through any one of these and that will give you same, right? So if I compute the limit of t here, so x is going from 0 to 1, so my t will also be 0 to 1 as x is equals to t itself. Now if you try here, y is going from 0 to 2. You observe t is also going from 0 to 2. The same limits you will get. It doesn't matter, right? So limit of t will be 0 to 1. So now we'll compute the integration and convert everything to t. So this, right, this will be, this 3x square will be 3t square, and this will be dt. So I will write dt at the end, plus here I have 2xz. So x is 3t and x is t and z is 3t. It will be 2 times t times 3t minus y is 2t, plus just the calculation becomes lengthy. Your calculation needs to be very good. This is z, this is 3t, okay, and whole integration, right, with respect to dt. So I'm just converting it in terms of parametrics. So this will be what? 0 to 1, 3t square plus 6t square, this is plus t dt. Now if I want to write this, this will be 9t 3t whole cube 0 to 1 plus 1 by t 1 by 2 t square 0 to 1. This will be simply 3 plus 1 by 2, which is 3.5 joules, because unit of work done, if you remember your good old days, it will be 3.5 joules. Okay, so yeah, this is how you solve. this question. Now the second one is homework for you. Second one is simple homework for you. How to do this? So what you can do, I will give you the hint. As they have given me the limits of x and they have written x in terms of y and z, what I will do, I will take my x equals to t. Now you solve. You find the limits of t. You write y also in terms of t and x, and then you solve. It is a very easy question. Okay. So let's solve this next question. So this question is very simple. You have to evaluate this field in along curve C along a circle of radius 0, 0 joining points 3, 0 or 0, 0. So like, yeah, I can solve this along a circle, but still the curve is looking like a bit complex, right? So what I will do, I will try to first compute the curl of this, and if it is 0, that means f is irrotational, that means it is a conservative field and I can take a simpler curve. So this is how you solve this type of question, right? First you try to take compute the curl. If the curl is very long, obviously you can skip that, but this helps, right? This helps big time. So if you compute the curl, this will be I j k, and this is anyways in 2D, right? So I will only have the k component. You just compute for this last column. You don't need to compute for this. Why, I will explain in a bit. So this, if I'm right here, ddx ddy ddz, this will be y square plus 2yx x square plus 2xy, I think, yeah, and here it is 0, right? So you can observe this is anyway 0, and here if I just compute for the first column with respect to I component, this will be 0, and this is anyway 0 because here I don't have any function of z. Again, if I compute with respect to the second column, then this will be anyway 0, and here also I don't have a function of z, this will be 0. So only the k component will be remaining if I am computing for a 2D vector field, the curl. So k component, if I compute this carefully, this will be what? 2x plus 2y, and this will be what? This will be 2y plus 2x, and also I have to subtract this 2x plus 2y, so which is equals to 0. Hence it is irrotational, and I am happy again. Right? Because now my task has been just simplified. So what I will do, I will choose a different path now. I will choose this path, right? The simpler path. I will choose a straight line. Okay, why will I go through that much hassle, right, to go through this path if my field is conservative? Okay, by field I mean the field is somewhat like this, right? Field is somewhat like this, okay, and I am moving along this path. Okay, so what will happen is that it will give me some force, or it will give some attraction or repulsion. So if I move through this straight line or this curve, it doesn't matter. So I will move through this straight line now, and I will compute this. So what is the equation of this straight line? So now you should be pro at all this, right? It should be what? X plus y equals to 3. What you're saying? Always you're saying this is like a straight line, and whenever you have a straight line with negative slope, you first write x plus y. Then you try to find the slope. The slope of this will be what? 1 only, because if I'm moving 3 steps up, then like I'm also moving backwards 3 steps, right? So 3 by 3 is 1, which is -1 basically. So also if you add these two up, x plus y, it is 3. Here also x plus y equals 3. You can satisfy these 2 points also, and you can directly write. So you can save your time there. Okay. So what is the important point? The important point is you can replace your dy as minus dx. You can take dx here and you can differentiate with respect to x. So these you have got, okay, and your x is moving from where to where? You are going from this point to this point, right? So x is moving from 3 to 0. Keep that in mind. So first let me write f dot dr along c dash, I will not compute c, I will compute c dash. That will be easier for me, which is equals to y square plus 2xy plus x square plus 2xy dy, and I'm computing the integration. So we'll just reduce the size of this. So now, right now, what I will do, I will just replace this y in terms of x, or you could have done, you would have created a dummy variable also, but it would have been the same thing also. Okay, so my x is going from 0 to minus, not minus, sorry, x is going from 3 to 0, and my y is going from 0 to 3. So I'm moving up, and also I'm moving left side. So basically my x is reducing. So this will, I can write this as, I can convert everything in terms of x, right? So y square will be what? Here I can write my y equals to y equals to 3 minus x. So this will become 3 minus x whole square plus 2x 3 minus x dx plus this is x only, x square plus, so this thing is same, right? This thing are not same. Actually here there is subtraction. This will be 2x into 3 minus x, and here is minus dx. Instead of dy I am writing minus dx. So okay, so this will become my brackets are messed up. That is a sad thing. Okay, so what will happen? My x is going from what? 3 to 0. Okay, so if I just reduce the size of this, and can I reduce? No, I cannot further reduce. So this will become what? This will become these, and these will get cancelled, right? Because this is in negative, this is in positive, and no, sorry, this is in negative and this is in positive. So these two will get cancelled simply. Okay, so if these two are cancelled, only I am left with this. So this will be going from 3 to 0. This is 9 plus x square minus 6x minus x square with respect to dx, because here also I have a minus sign, right? Minus sign. So this minus sign will get distributed and this will get cancelled. So I will have only this, right? So it will be integration 3 to 0 9 minus 6x dx, and this is 9x minus 3x square. X is going from 3 to 0. So this will be if I put 0, this will be 0. If I put 3, this will be 9 into 3 minus 3 into 9, and in negative sign basically. So this will be simply 0. So like at the end the answer is 0. Okay, so we'll get answer as 0. Okay, so this was basically a very simple question. Only you have to take the substitution. That is the more important part, how to convert this into a single variable function, not a two variable, to compute the single integration. So that is the important part. Let's now compute this question. This has come in git 2020. So here the vector function expressed by this represents a conservative field. They have mentioned conservative field where ax, ay, az are unit vectors along xyz direction. Then what are the value of k1, k2, k3? If this is conservative field, okay, I'm 100% sure it is conservative field. It has to be irrotational also, right? It has to be irrotational also. So yeah, if it is irrotational, it is 100% sure. I'm 100% sure it is conservative. But they haven't mentioned about the condition of irrotationality, and I have no other tool to check for conservativeness. So I will go for the irrotational thing. So I'll find the curl of this, and I will equate this with respect to 0, and from there I will be able to compute k1, k2 and k3. It will be del upon del x, del upon del y, del upon del z, and like this is 5y minus, what is this, k1z. Okay, this has to move on the right hand side a bit. This will be 3z, k2x, k3 y minus 4x, k3 y minus 4x. Okay, now what I will do is I'll just reduce the size because this is taking humongous space. So if I reduce the size, so this will be equals to, if we compute this, right, this has to be equated with 0 first, but first let me compute this. So if I compute this, if I compute with respect to this, this will be k3 minus 3, k3 minus 3 I cap minus, there will be j cap, so j cap will be there, but I will write that later. It will be minus 4 plus k1, minus 4 plus k1 j cap, plus this will be k2 minus 5 k cap. So but as it is conservative, my del cross f should be equals to 0. Okay, so if I compute this equals to 0, so k3 has to be equals to 3 and k1 has to be equals to 4 and k2 has to be equals to 5. Okay, so simply if you compute this, k1 is 4, k1 4, 4 5 3, 4 5 3. So option C will be your correct answer to this question. Okay. So this is how you solve for the conservativeness. So like you can see in GATE, easier question comes. What I will teach you all types of question, all varieties of question to the highest level. So whenever a difficult paper comes up, right, only my students will be able to solve that question, and other students will not be able to. So then you will be ahead of the competition. So whenever you're preparing for any competitive exam, you always pray that the question paper difficulty comes a bit difficult. If you have prepared very well, then it is to your advantage, else it is to your disadvantage, because even if you have learned so many concepts but you are not able to use it, because everyone will use the same concept in easier questions, but the day when the difficult question comes, you will only be able to solve it, because the trend is right now GATE is setting up difficult question papers, not easy question papers. So you will be in advantage. So yeah, that's it for this lecture. So we have covered the basics of singular integration, and in the next lecture we'll cover the basics of surface integration, and after that we'll cover with theorems. So mainly you don't need to do this much of hassles. Mainly you will solve the vector integrals with respect to theorems, Green's, Stokes and Gauss. But this also you have to understand, because when those theorems fail, then you have to come back to basics, and basics always never fails. Basics never fails. Okay, so yeah, that's it for this lecture, and I will see you in the next lecture. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 3B of vector calculus. So we have started integral vector calculus, and we have studied about line integration. So in this lecture we'll study about surface integration and few tools regarding surface integration, that is the area vector, and obviously we'll do few numericals on surface integration. But do keep this in mind, whatever we learn the basic method of surface integration, but in general cases that is not used in gate examination because we solve using theorems. So our surface integration simplifies, right? So but why is this important? Whenever those theorems fail, we have to solve with basics. So that's why your basics should always also be clear, right? So I will say all this as we go along this lecture, but before starting, I gave you one question as homework. So let's do that question basically. So here I gave you okay, which one was it? Yeah, this one, right? I gave you the second part as homework. So I told you to just take x as t. So if I take x as t, then what will be my y equals to? So my y will be equals to x squared by 4. Y will be equals to x squared by 4, which is t squared by 4, and my z is equals to 3t cube by 8. 3t cube by 8. Just hold on a second, let me check everything is recording or not. Yeah, everything is recording. 3t cube by 8. So what is my dx? Dx is simply dt. Dy is simply 2t by 4, which is t by 2. T by 2 dt, and dz will be simply what? 9t by 8. I hope you are understanding how am I able to do this. Just simply differentiating it. This is what I'm doing. I'm doing dz upon dt, and I'm taking the dt on the right hand side, nothing else. So we can talk about limits. Limit will be for only this only, right? So here my x is going from 0 to 2. Obviously my t will also go from 0 to 2 as x is equals to t. So now I'm ready. I can convert my integration. So my f dot dl, basically the work done, will be converted into this, right? So this was my f dot dl. If you remember, this was my f dot dl. So I'll just copy this once so that I will be able to keep track of this. Let me delete this. Now if I replace everything with respect to t, this will be simply 3t square, and this is dt, plus this is 2 times t times what is z? Z is equals to 3t cube by 8, and my y is simply t square by 4. T square by 4. Then plus what is the end? It is z dz. Z is 3t cube by 8, and what is dz? Dz is, okay, I forgot this thing, right? I cannot simply replace this with dt because dy, what is dy? Dy is t by 2 dt. So I have to replace with that. Okay, I'm running out of space, so I will try to write this in the next page, then I will bring this back. So my forgot to write this. This dt won't be simple dt, right? This will be replaced with t by 2 into dt and this is 3t cube by 8. Z is this, and what is dz? Dz equals to 9t by 8. That I will replace here. So this is 9t by 8 dt. So now if I reduce, like, I'll just reduce the size of this to fit in everything, right? So now I'll cut and paste, basically cut and paste here. So now I can simplify all this in terms of t, right? So this t will go from 0 to not 0 to 1, 0 to 2. Here x is going from 0 to 2, so this t will also go from 0 to 2. Okay, so I'm following a different path now. Also I can say whether this force, right, is a conservative field or not. So this will be equals to, if I simplify this, I have 3t square dt over here. I will keep it as it is, 3t square. I will write dt at the end, and this will be what? This will be 2, so this will be t to the power 4 divided by 4, right? T raised to power 4 divided by 4, yeah, plus write this t raised to power 4 divided by 4, and also I have a 3 at the top. Also I have a 3 at the top, and this is t square by 4, t by 2 dt. And okay, this has been done, and this is 3 to raised to power, this will be t raised to power 4 27, okay, not dt, actually t will come at last, plus 27 t raised to power 4 upon 64. Okay, so this is dt, 3 times 9 and 8 times 64, t raised to power 4 dt. Okay, now I can take the like terms together. So I have, do I have t square? No, t square I don't have, right, anywhere else. So this will be 3t square only, and this, right, this becomes t raised to power 5 and this becomes t raised to power cube. So everything is different, there are no like terms over here. So this will be simply plus 3t raised to power 5 by 8 minus t cube by 8 plus 27 t raised to power 4 by 64. Okay, so this, okay, I had, okay, I forgot one thing here, right? I had t raised to power 4, yeah, sorry, I made a minor mistake. This, right, this will be t square, this will not be simple t cube because I'm differentiating, right? I know you guys were screaming. So here 3 will come in front, and obviously this will reduce its power by 1, so this will be t square. So here this also will be t square, so hence this will be t raised to power 5. So yeah, this can come together if I just convert this into like terms, else let us compute it differently itself. So this will be t cube plus 3 by 8 into 6 t raised to power 6 minus 1 by 32 t raised to power 4 plus 27 by 64 into 6 t raised to power 6. I'm going from 0 to 2. So this will be what, t cube is 8 plus, this is t raised to power 6, this is 2 raised to power 6, and this is 2 cube. So this will be, here I have in the bottom I have 3 times 2, so this 3 gets cancelled, and I have 2 raised to power 4, so I will have 2 raised to power 2 at the top, minus this is 2 raised to power 5, okay, and this is 2 raised to power 4, right? So this will be 1 by 2 plus 2 cube plus, yeah, then this is what, 2 raised to power 6 on the top, and here how many numbers I have? 8 into 8, 2 cube into 2 cube, so which is 2 raised to power 7, 2 raised to power 7, 3, and 9 by 2. Okay, so then if I compute this, this is what, 8 plus 4, 12, and this is how much? This is 8 by 2, which is 4 again. So this is how you have to be mentally, you have to be very good in calculations, right? So that you will be able to solve this very fast. 16 joules. So this will be my answer to this question. Okay, so just be careful of the silly mistakes that we make over here. This dz, t cube, t square, all these things, right? You have to take care. So I also make the silly mistakes. I show the silly mistakes because the same thing you can do in the examination hall. So you have to be very careful about that. So this was a pretty simple question. Now let's start today's topic. So today's topic is about surface integration. So first of all, let's understand few nomenclatures. I told you, right, what is an open curve and what is a closed curve. Similar thing is there for surfaces also. So what is open and closed surface? So if I have a open surface, that means it does not enclose any volume. You can see a closed surface, right? Surface of a cuboid. Cuboid is also a surface. Cube or cuboid, you might say. It encloses a volume inside it. Okay, it covers everything, it encloses. Just keep this in mind. Whenever we're talking about surfaces, we'll talk about enclose, and whenever we're talking about curves, we'll talk about encirclement. So here we are enclosing a volume for a closed surface. So this, what do you call this volume? We call this volume a hollow volume, right? This is what? This is a hollow cube. So if I have a closed surface, it will be a hollow volume, hollow cube. This is a hollow cube. And this, right? Does this simple sheet of paper, does a sheet of paper enclose any volume? No, it doesn't. It has some surface area, but does it enclose any volume? No. So it has the surface area like this, right? This square thing, sheet of paper. It does have a surface area, but it does not enclose any volume. That's why this is called a open surface and this is called a closed surface. Now, what is the important point? The important point is, you can observe this is a curve, right? This was a closed curve, and a closed curve can be associated with a open surface. Yes, closed curve can be associated with a open surface. But can I break this down into multiple closed curve and I can compute the surface, like surface integration? Can I do that? Because in the previous case, I broke down my curves into 4 parts and I computed my line integration. Can I do something similar here? Can I do that? I will show that, right? But before that, let's come to the orientation part. Here I can see that I'm moving along this curve. In some particular direction. And what does this direction specify? The direction specifies the direction of the area vector. So we will use our right hand rule. So if I use our right hand rule, that means, like, this is what? This is in the anti-clockwise direction. Now if I'm moving in the anti-clockwise direction, my thumb is pointing towards me. It is coming out of the screen. So if it is coming out of the screen, okay, where did I go? It is coming out of the screen. That means what? This is a dot, right? Dot. I will just see a, if I can somehow, okay, I cannot simply make a circle. It will be very difficult. I will do this. What is it? This is simply a dot, right? I'm just seeing the arrow. Okay, just seeing the arrow is coming towards me. It is coming to kill me. Okay, so anti-clockwise means like the direction of the area vector will be towards me, or the direction of the surface, the gradient. If I take the gradient of this surface, right, I will get the direction normal to this. Okay, all this will come to when you will study the area vector. And can you tell me the direction of this surface? Okay, I'm moving along a circle. Can you tell me the direction? I'm moving in the clockwise direction. So if I'm moving in the clockwise direction, that means I'm moving like this. That means it is coming towards you. Coming inside the skin. It is going inside the skin. That means I'm seeing the behind of the arrow. I'm seeing the cross. So this will be simply a cross. Okay, all this thing got copied. That is bad thing. This will be not a dot. This will be a, okay, I have to delete this. This will be a cross. This will be a cross, right? Not a dot. Okay. So, but does this have a direction? Yes. This closed surface also has a direction. Like this, what we can do, we can break this down into different surface integration, right? This is an open surface, this is an open surface, this is an open surface. All this individually I can compute. Okay, so basically how we used to compute a closed line integral, we used to divide that into different open curves, open line integrals, and then we used to add those up. The same thing is applicable for closed surface integration. We'll break this down into different open surface integration and we can add this up. That's the basic thing. But can we divide this into different curves, right? Different single curves. So, like, what do I mean by this? Can we do something like this? That if I am taking, like, this is the first curve, then I am taking the second curve, then I am taking the third curve, then I am taking the fourth curve. So let me just put a few things over here. This is, let's say this is C2, then C3. Even though there is space, I am just making the space to visualize everything, right? This is C3. So now can I write like this, that this closed surface integration is like open surface integration, it's written like this, that it is f dot ds over the surface, okay, over the surface equals to, can I write it as summation of the closed curve C1 plus C2 and infinity? Is it possible? No, this is not possible, right? Why is this not possible? Why is this not possible? Because I have to keep on decreasing the curve and I will never get to zero, right? I will never get to zero, and I will never be able to compute this single line integration, right? As the radius is decreasing. So basically, like we can't discretize this. Like we can't use discrete things like I equals to 1 to n integration of ci some v dot dl. Okay, I won't be able to discretize this, but what will it be equals to? But I can write this, that my surface integration, okay, surface integration f dot ds, I have to take infinite curves, right? Infinite curves. So what I can do, not this, is I can totally take the integration from like 1 to infinity, okay, 1 to infinity of integration, line integration of the curves, right? Line integration of the curves along the path ci. Okay, so I have to what? Continue, like make it continuous, right? So basically I have to take infinite curves. That's why this discretization is not possible. So that's why we write it like double integration. Just wanted to show you the significance of double integration, nothing else. Okay, so like we have already studied about level surfaces. So this is one level surface, right? This is the surface of a simple triangle. And does it enclose any volume? It does not. Why? Because this only has this area, right, associated with it. But if I say a sphere is also a level surface, but sphere, what is it? It is a hollow sphere, right? Because this is equals to, okay, so this encloses a volume as well as a surface area. So a closed surface encloses a volume as well as has surface area. A open surface does not enclose any volume, but it obviously has surface area. Okay, just hold on a second, I have got a call. Yeah, let's come to the next point. The next point is about area vectors. So I told you, right, to compute surface integration, we have to have the information about area vectors. So for surface integral, area has to be considered as a vector. Just like your dx, right? Dx was also a vector, if you remember correctly. Dx was what? Not dx, sorry, dr or dl. It was dx I cap plus dy j cap plus, okay, wait, plus dz k cap. Simply, so area also has vector quantity. Area is also a vector quantity. So here area can be written as, the area vector can be written as s vector equals to s a s cap. So s, magnitude of the s will be simply area of the open surface, that is area of this, okay, and as will be basically the direction perpendicular to the area. Okay, so basically if you have to compute the area of the open surface, you can use the what, simple mensuration formulas. Okay, and you can find for regular shapes. For irregular shapes, you have to compute the double integration 1 dx dy, which we have been expert at, so that's not an issue. But what is as? As is the direction of the open surface perpendicular or normal to the open surface. And now there can be two perpendiculars, right? Two perpendiculars, one could coming out and one coming inside. Which one I will choose? I will choose according to the right hand thumb rule, where my curve is following for oriented surfaces. So this as cap is formula is like this. Few you will be able to simply find, and few you have to use the gradient formula. Grad of phi upon phi. Phi is the function of the surface. Okay, phi is function of surface. Basically, you already know how to find the normal to a surface. So, like there are two types of surfaces. Open surface, I mean, one is non-oriented and another one is oriented surface. Now, what is non-oriented? Now, you have been given this surface. Okay. Now, can you tell me the direction of this, like the direction of the area vector of this surface? Can you tell me that? You can't. Why? You have to say, sir, I can, but there will be two directions, not a single direction. I can either move in this direction or in this direction. As you haven't specified any orientation, so as no orientation is specified, I can move. Okay, I will copy these two things. I can move in the anti-clockwise direction or in the clockwise direction. It doesn't matter. Okay. So in this case, the direction of the curve representing the boundary or surface is not specified. So your AS cap can be plus minus what? K cap. Okay, because outside and inside is K cap, X and Y is on the surface itself. But by default, if the examiner is very like what do you say, firm on his words, please give me one surface. So what you'll do, you will give him just the positive. So generally we like positive things. So by default choose AS as positive K, and if I choose AS as positive, that means it is coming out of the screen, which means anti-clockwise. That's why in generally you see that anti-clockwise is understood as positive direction. So anti-clockwise, general cases you see, right? If I move in the anti-clockwise direction, angle is positive. That is the reason. Okay. So this is the thing. Now, if it is oriented, then there is no question itself, right? Even though this is covering area, this is covering the same area, but as this is oriented, they have specified the path, and here, right, I have mentioned the axes always need to be mentioned. So again, I will follow the right hand rule, and obviously I can see this is in the anti-clockwise direction coming towards me, so this will be dot, hence the direction will be towards me. Direction will be plus K cap. Direction of the AS will be plus K cap. Okay. So yeah, that will be the direction of the area vector, right? So how do you find the direction? What you do, you write your surface. You will be given a surface. Okay, I am talking about irregular surface. This is simple. I can simply conclude that this is a K cap. But if I have surface as a function of XYZ level curve, okay, level surface. So what I will do, I have to compute in the greater than direction, right? In the greater than direction, because this is in the anti-clockwise sense, this is going outward of the surface. So all this I will explain. So what you will do, you will write, if it's in the anti-clockwise, you will write this, you write your phi as this, phi, okay, phi of XYZ. Okay, so now how do you compute? You compute your area vector. You compute your area vector like this, del of phi by magnitude of del of phi, not magnitude, del of phi by magnitude of del of phi, right? If you remember correctly. Okay, I have to put this at the top. Okay. So yeah, this is the formula for area vector for a oriented open surface. Whatever I am specifying, this is for a open surface, right? Simply compute this and you convert to this and you will find the direction. As this is in the anti-clockwise, so you will compute phi like C, this will be F minus C, not C minus X. That is very important, right? Now what about my closed surface? So closed surface can be written as a combination of many open surfaces. So what you can do, my direction of the area vector will be the normal outward direction of the volume. So I don't want to go inside the volume, I want to compute outside the volume. So the direction of this will be in the plus A cap direction, right? This will be not plus A cap, plus I cap direction, as this is in the positive x direction. This will be I cap, but this, right, this will be minus I cap, okay, as this is in the opposite direction. So this is how you like compute the direction of the surface for a closed surface. Very simple, very simple. Direction of the area vector for a closed surface, just to the normal outward volume. So it is normal direction and it is on the outward, not inside, and this is also in the outward. So this is minus I cap and this is plus I cap. So like how do you compute open and closed surface integration? So open surface integration, I will just tell you the method in the next few slides how to compute, okay. And if you have been given a function that is differentiable vector point function, then you compute like this. I will tell you the methods. We will have two methods. And for closed, right, you can break it down into multiple open surface integration, just like we broke down a line integration into multiple open line integration, like a closed line integration into multiple open line integration. Similarly, you can break it down to multiple open surface integration also, okay. So yeah, that you can do. So now what is the important point? The important point is how to compute the open surface integration, and this, right, this computation we will anyways do with the help of theorems, so you don't need to worry, okay. So in the next few minutes, whatever I will explain, right, whatever I will explain will be very important to you, so do listen to me very carefully. But don't worry if it seems a bit too much for you, because 90% of the cases in mathematics, this vector calculus integral questions will solve with theorems, and 10% may happen when your function is not differentiable. Then you have to go with this basics only, right, along this whole surface. If the function is not differentiable along the whole closed surface, then you have to break it down into open surfaces and then solve. Else you will use theorems that will simplify your question just very much, right. You will be able to solve it in seconds. So problem solving approach number 1, what do you do? This is for simple shapes. So if you have been given simple shapes, right, if you have been given simple shapes, then you solve according to this, okay. So what you do, you just compute like you have to compute this, right, open surface integration of this, okay. So what you do first, like you understand this is in the Cartesian plane, so this is in the Cartesian plane, and you can easily find out the direction of area vector. So can you tell me what is the direction of the area vector? According to the axis, you can say that it is plus z direction, which is plus k cap, right, plus k cap. This is my direction of area vector, okay, and my dr is this. And now, like you have to remember this thing, right, dr is this, okay, and whenever you are in the your area vector is in direction of plus k cap, then obviously your area is lying on the xy plane or somewhere like xy equals to some xy constant, right, some xy constant. Z equals to 1 will also be not in the xy plane exactly, but some, like it will have some shape, like if I take the projection, it will have some projection in the xy plane, right. So can you tell me, if I take a very infinitesimal small shape in the xy plane, whose length will be what? Along the x direction will be dx and along the y direction will be dy. So can you tell me the infinitesimally small area of this, okay? So it will be dx term dy, right? Very small area and this dx term dy. That is exactly what I have written. And what is the direction of that? It will be in the positive k direction, as the orientation is in the anti-clockwise direction. That's why this is positive. If the orientation was in the negative, this would mean minus. So you can replace your ds vector like this: area, magnitude of the area, dx times dy into the direction. Got the direction. So this is the area magnitude and this is the direction. Similarly, if you just place a surface in the what yz plane, you will have a thing like this, and this will be what? This will be dz, this will be dy, and this will be dz. Area will be dz times dy, and the direction will be in the positive x direction or in the negative x direction depending on the orientation. So this is exactly what I've written. And similarly for the xz plane. So you replace your ds like this. First identify the surface, plot the surface, okay, then you decide the ds. Then what do you do? Then you compute this limits from smaller value to larger value, Okay, this is very important. You go from smaller value to larger value. In line integration, we used to go from along the curve. In line integration, we used to go along the curve, but in surface integration, we will go from the smaller value to larger value. Okay, so we won't go along the curve. So once we solve this example, there we'll understand. So let's solve this example, right? So here I have to compute the closed surface integration of this vector point function along the surface where S is a cube bounded by the planes x equals to 0, x equals to 1, y equals to 0, y equals to 1, z equals to 0, and z equals to 1. So if I am bounded by this, how can I solve this? I can solve by breaking it down into single surfaces, right? So what I can do, first I can name these things. So how I can name? First let me name the points, right? I will break this down and name these points. So this will be, so I hope you are able to trace the curve, right? All those things we have learned in obviously much before, right? Those I have taught much before. So I hope you are able to do all those things. This will be A, B, C and D, and this will be P, Q, R and S. Okay, so now if I have a field like this which is going along this closed surface, then I have to compute this surface integration. And what does this signify? That also we'll understand. Okay, so we can break it down into different surfaces. So why not first like name the surfaces, right? Name the surfaces. So let me name this surface as the first surface. Okay, do I have more colors? Let me name the surface as first, then I can name any surfaces, right? You can, like, if you have named this first, then you can name the opposite one, the second one. Okay, then you can go from top to bottom. 3, it doesn't matter, the ordering doesn't matter, 3 to 4, and then obviously the this front and the back. So this is the 5th surface, if like you will be able to understand. This is the 6th surface, the back one, right? Back one, front and the back one. Okay, so like, what is the important point? Important point is I can compute my closed line integration, of f dot ds, which will be equals to simply the summation of different open line integrations, right? Not closed line, closed surface integration to different open surface integration. So there are 6 surfaces of a cube, so I can simply add those up and compute the open surface integration along the surface of f won't change, but obviously my ds will change. I can write also ds as a n cap ds, right? This also I can write. Okay, a n cap is the direction of the surface or direction of the area vector. So let's solve it slowly. So this will take time, so we'll solve this slowly. So first I am talking about the surface 1. Okay, surface 1. So what is the surface 1? Surface 1 is this this one, right? Surface 1 is this, which is BQRC, okay, or BCRQ, whatever you want to name, right? BCRQ, So can you say the, like, let's see the steps, right? First I have written it down how to compute this, like I have to compute this, right? So I can do f dot n cap. So I have to decide the direction of ds first. Whatever I do, you decide the direction of ds. So what will be the direction of ds? So what will be the direction of n cap? That is the direction of ds. If you see, this is a closed volume, okay, and this is surface 1, and what will be the direction? Direction will be normal vector outward from the volume. So normal vector outward from the volume, which is in the positive x direction, okay, which is in the positive x direction. So this will be plus I cap. So like, how else you could have done? You could have written, what is the equation of this surface? The equation of this surface is x equals to 1, right? X equals to 1, but this is not the yz plane. That you have to be careful. This is not the yz plane. This is some other plane. This is not x. This is just x equals to 1 plane. X equals to 1 plane. Okay. So this is x equals to 1 plane. So what you could have done? You could have written phi equals to x minus 1, and then if you have computed grad phi upon magnitude of grad phi, you would have got the same thing only. Okay, so you could have solved like that also. Now I will simplify this integration. This will be surface 1, and what will be my f dot a n cap? So f dot a n cap I can write like this. This will be like I am along the I cap direction only. I will take the I cap component, which is y square, and this will be simply what? Now what will be the magnitude of the ds? What will be the ds? ds will be what? I am in the yz plane, so area vector will be dy dz. Yz plane area vector will be dy dz. Okay, so now you can simply solve this from lower to higher, right? Lower to higher, you can take the projection. You can take the projection on yz plane. So what you can do, for the first one I will do this very slowly, after that we'll do this very fast. So I have to compute what? Double integration of y square, okay, in the dy dz plane of this x equals to 1 curve. You can solve that, right? You can solve that. How to solve that? You simply take the projection on the dy dz plane, so that you can identify the what? The limits of the strips. You have to take one strip either along the dy or dz direction. So I will take a strip in the what? dy direction, because y is coming first, or you can take dz also, that doesn't matter, but I have to compute according to the dy, right? Compute according to the dy. So this obviously will be vanished. This will be vanished. This can stay, right? What I will do, just in small manner I will show you that I will place a sun over here. Sun has to be orange, and it has to compute the projection. Okay, so if I compute the projection, what I will get? The projection of this surface, it will be simply a square, right? So it will be simply a square. So I can write it like this. Okay, let me go to the next page itself, that will be better for us. Simply in the what? Now how will I write my y? So if I write my y like this, y is in the positive direction and z is in the positive direction. So if I write my z over here, y over here, so zy won't be okay, z, if I write z like this, yeah, we can write it like this, right? Can write it like this. This will be z and this will be y. Okay, so my curve will be like this, right? And my projection will be like this. This is what? This is simply the projection. So my projection is just area vector. And can you tell me the direction of this? Can you tell me the direction? Direction is along this, right? So positive x. So if I do y cross z, y cross z should be in the positive direction. So I have to do y cross z, right? This y cross z will come over here. So I'm going from here to here. So I'm going from y to z. So this will be y to z. So this direction will be like this. Okay, whichever is suitable to you. But we have already computed direction, so we don't need to compute the direction again, right? We will ignore the direction calculation. We just compute the surface integration. So now what I can do? I can take a strip, basically. Simply a strip. So this is just simply a rectangular region. So this strip will go from y equals to 0 to y equals to 1, and obviously I'll move this strip from z equals to 0 to z equals to 1. So this is very simple. Okay, so this will be 0, 0, 1, 1. So this will be 1 by 3 into 1 into 1 itself, which is 1 by 3. Okay, we have computed 1 by 3. Very simple, very simple. Now the same thing if you want to do for the second surface. Second surface if you want to do. Okay, now this is equals to what? I will change everything, right? I will change this to second surface. Now what is the second surface name? It is APSD, right? So it is completely different, which is APSD. And what is the value of the x at that surface? It is x equals to 0, right? X equals to 0, which is this time this is yz plane. This time this is yz plane, or I can write phi equals to x. So obviously, what will my direction? My direction I have already told you this time, right? It has to be unit downward vector outward from the volume, which is on the left hand side, which is in the negative x direction, which is simply minus phi. So this time phi will be my what? I will choose my phi in the negative direction. So this will be minus x, right? So this will be minus I cap. Okay, and ds is anyway same. Again, I am in the yz plane itself, or like in projection is on the yz region. Projection is on the yz region. So it will be dy dz. Again, I will compute in the I direction, but this time here extra negative sign will come up. And if I take the projection, right? If I take the projection will be the same only. No difference, zero difference. This is on the xy yz plane and zero difference from this, right? So projection will be same strips I will take, same limits I will put. Okay, where did I go? So my answer will be this time, instead of plus, it will be minus 1/3. Everything is same. Okay. So again, if I copy these things, right? This time, okay, let me take the third surface. Third surface is this along the along the positive y direction. So I will again copy these things. I will paste it over here. This time I am taking the not this. This will be third surface. What is the name of the surface? The name of the surface is APQB. APQB. This is what? This is y equals to 1 plane. Okay, you can go back there. You will see y equals to 1 plane. This is not the exact plane, but this is y equals to 1 plane. Just keep that in mind. So this time, this is going outwards, right? In the increasing direction. In the increasing direction. So obviously my phi will be what? Phi will be equals to y minus 1, as it is in the increasing direction. So obviously your direction of the area vector will be in the positive j direction. Positive j. Okay, not this, sorry. Positive j. This will be positive j. And your ds this time, as this is the what? This is the y equals to 1 plane. The projection is on the xz plane. ds will be dx dz, and this is j cap. So I will only take the j component this time. J component. So j component is what? J component is minus yz. So it will not be y square. It will be minus yz dx dz. Okay, minus will be here and it will be minus yz. So now again, what is the projection? Projection is simply a square only, right? Projection is simply a square only, just like this. It is simply a square. So I will just simply copy this. Change the planes. So planes this time will be what? This is along what? If I take the projection from top, this will be in the xz plane. So z is in the positive direction and x is in this direction. So I can draw my x as this, right? Z I can draw like this and x like this. This will be x, and I will again take a strip. Okay, this is just repetitive. You can solve it for yourself, right? So this will be z going from 0 to z going to 1, and obviously x going from 0 to 1. So this is going from left to right. So all of this is going in autopilot, right? You don't have to think much. All of this you are doing in autopilot. Don't have to think much. So the limits will be same only. This will be yz. So this will be minus 1/2 into 1/2. Okay, not 1 by 2 actually, sorry. Just hold on. Y is, now what is the value of y? What is the value of y? Value of y is 1. So I can replace this as minus 0 to 1, 0 to 1, z ds dx. So this will be equals to, this is surface 3, this is surface 2. This will be equal to simply 1 by 2, minus 1 by 2. So answer will be minus 1 by 2. Similarly, if you solve for surface 4, okay, so this part I will solve quickly and then I will just show you how I solve it. Okay, so I have computed everything. So I stopped, I think, up until here, right? I stopped until y equals to 1. Now in the next plane, what will be the simplest thing? Y equals to 0 plane, right? This is a surface 4. Surface 4 is the y equals to 0 plane. I'm on the xz plane. So if y is 0, simply what will be my direction? Direction will be in the negative y direction, which is minus j cap. So this is minus j cap, and you can compute with phi, and your ds will be what? The opposite to, which is dx dz. And if you want to compute this, right, f dot a n cap, you will be left with only yz. It's the same thing as previous case, but the difference will be y is equals to 0 instead of 1. So this whole integration will turn out to 0. I don't need to compute this strips. Okay, I don't need to compute the strips. Just the strips, right? The strips go from low to high. That's why the limits are lower to higher in this method, right? Limits are lower to higher because of the strips, as we choose the strips. That is the reason. So you don't need to worry about this lower to higher, just strips. You just choose the strips carefully and you will be in autopilot. Okay, so you will solve this questions automatically. So just the important thing to note here. That's why I'm going from bottom to up. That's why this is going from 0 to 1 and left to right, which is 0 to 1 again. Okay, so yeah, that is it. Next, in the surface 5, what was surface 5? Surface 5 was z equals to 1 plane. If you observe carefully, this is my z equals to 1 plane. This is my surface 5. This is coming outwards towards me, which is plus k cap. And what will be the ds, magnitude of ds? Magnitude of ds will be dx into dy. So exactly what I have written. This is z equals to 1 plane. Magnitude of dx is dx dy, and if I do dot product, if I do dot, I will only have the k component. K component is 4xz and my z is 1. So if z is 1, this will be 4x dx dy, and if I compute, I will get 2. Simple, right? Simple computing. Now z equals to 0 plane, it will be minus k cap in the opposite direction, and z is 0, so this whole thing will become 0 and I will get 0. Now what I told you, right, I have to simply add this up discretely. So if I discretely add this up, I will get 3 by 2 as my answer. So this will be my answer to this surface integration. So this is the basic method with how you solve this type of question, right? But don't worry, you will use mainly theorems, and there you will not take this much amount of time. So like, what is the significance of this number, this 3 by 2? What is the significance of this number? The significance of this number is basically the flux. So if I compute the surface integral, open surface integral over, or a closed surface integral over a field, okay, of a surface, then it measures the how much field lines of vector f crossing the open surface as perpendicularly. So this has some angle with the surface, okay, but how much of those are crossing perpendicularly on its direction? Because that's why I do f dot ds. I am taking the component on its direction. So it will be how much of this area vector, okay, area vector is some other direction, and if I take the dot, it will tell me, if I take the integration, it will tell me how much field lines are crossing that surface perpendicularly. Basically, this is also known as flux. Okay, so I hope you already know all these things. Like, this is just a physical significance. So if they in the question they are asking, can you compute the amount of flux through this surface of field vector this, then that means they are just asking you to find the surface integration. That is it. Now there is another approach to solving this surface integration, okay, closed surface integration. So the thing is here, just let me just write, if the surface or the coordinate system is weird to you, okay, previously we were in Cartesian coordinate system, right? Here we were mainly in Cartesian coordinate system. Cartesian coordinate system. Okay, now as we are in Cartesian coordinate system, then this, right, either you are in spherical or cylindrical system, then you will use this method. Okay, spherical or cylindrical coordinate system. Okay, so now how to use this method basically. So you will use the help of polar symmetry. So you have been given this cylindrical system. So basically, can you convert this into some directions? So the direction vector, basically when your surface, right, when your surface is not simple, like your surface is not simple, the unit vector direction of the surface, it's not simple, it is a function of x, y and z. Okay, then you use this. Okay, I told you 3 systems, right? Whenever you have cylindrical, spherical, or your direction of the system is not simple. Basically, can you tell me the direction of rho cap over here? What is it? It is the unit normal vector outside to this cylinder coming outside. So this is the direction of the rho cap, if you observe carefully, a rho cap, and which is not some simple k cap, j cap or I cap. Okay, it is not some simple k cap, j cap or I cap. It is a function of x, y, z. Okay, it is a function of x, y, z. It is not simply I cap, right? Because it is always changing. Okay, direction is always changing as I move along this cylinder. Now, if I ask you what is the direction of phi, it will be along this direction, right? Along this direction. So, which is also a function of x, y and z. Okay, but obviously the z cap direction is same only. Z cap direction is same, it is az cap, right? So this is same, this is not different because I'm going along the positive z axis, but my phi and my rho are of different directions. So then you will use this direction, right? So basically these are function of a rho, a z, a cap. So what you will use the polar symmetry, and like what you can do, you can simply compute, right? You can simply compute the direction with respect to this. Okay, because you are confused, I don't know what is the direction, so you just simply go through this. Previously I didn't use this formula, grad of phi upon mod of phi. I didn't use this because it was very simple, I cap, j cap, k cap, as it was on the Cartesian planes. Now this, right, computing this is difficult. The direction here, right, it is changing, because if I am at this point, the direction is along this outside the cylinder. Then if I am at this point, the direction is like this. Okay, it is different. So it is a function of my coordinates where I am at currently. That's why I have to use this grad of phi upon magnitude of grad of phi. Okay, then what you do, you have found out the direction, then you take the dot product of this d and s. Okay, but I don't know the ds also, because my ds vector is n cap ds. I have found this n cap, I have to compute ds. So how you compute ds? You compute ds like this, because this will get converted into what? Into a region projection. Surface integration gets converted into region f dot n cap, and this will be some dx, right? So here what you will write, it depends. For now I'm just taking an example. If I am writing along this z direction, okay, if let's say my n cap is along this z direction, then or in some any other direction, let's say I am taking the projection along the z direction, basically on the xy plane. So if I am taking the projection along the xy plane, let me take the sun. So you have to listen to me very carefully right now. I will just repeat once again, but you have to repeat, you have to listen to me very carefully right now. So if I am taking the projection along the z axis, then it will be xy. The region will be xy region. So this is xy region. So this ds will be converted into dx dy, and I will write here magnitude of n cap dot k cap, because I am taking the projection along k cap direction. So I will write here k cap, and I will take the dot with this n cap, which is the direction of the surface of what they have given to me. But you might say, sir, what region I will choose? Why I will choose positive z axis? I may choose positive y axis also. Okay, I may choose positive x axis also. Yes, you can choose anything. It all depends what is this f dot n cap. This f dot n cap and this n dot k cap or n dot I cap or n dot j cap, these are cancelling each other out. Whichever one is suitable after for computing the integral, that projection I will choose. Okay, what do I mean by this? Once we'll do example, there I will explain. So I will write all three. I will write here all three together with respect to k cap, with respect to j I cap, with respect to j cap. I will write all three, and whichever one is cancelling out right here, whichever one is making the expression more simpler, that projection I will choose to solve my integration. So that I will be able to solve it much more faster manner. So obviously you know what is dr, right? So if you are writing over here, like how to remember this, simply you know this is the projection method. This is a method 2, which is the projection method. So if you are not able to solve using the first method, you will use this method. So here what you do, this integration can be written in region R1, and this region R1 is in the xy plane. Okay, in our case it is simply like a disk. Okay, simply like a disk. So this is in the xy plane, right? R1 is a projection in the xy plane. Okay, and R2 is a projection of S in the yz plane. R3 is a projection of S in the xz plane. So if I am taking my sun in the k cap direction, then it will be xy. Taking my sun in the x I cap direction, then it will be yz and y so on. Okay, so but one thing you have to keep in mind, obviously this cannot be equals to 0, right? I cannot make this equals to 0. So from here you will be able to simply compute your projection method. So once we'll solve a question, there you will understand this. Just I'm stressing this again. Don't worry if you are not able to get this concept. This is not that important. This is like the 10% one. When like some difficult paper they will set, right, for mathematics, these types of question will come, because like normal theorems won't be valid there. Okay, so you have to solve with this basic method. So let's solve this question, right? You have to evaluate this closed surface integration of this particular field in the surface region bounded by the cylinder xy plus z square equals to 9, and x equals to 0, x equals to 1, y equals to 0 and y equals to 1, and z equals to 0 plane. So basically what does it mean? Basically if you understand this, x equals to 0, y equals to 0, z equals to 0, x is positive, y is positive, and obviously if I compute this, right, z can be negative and positive. As the region is bounded, they are talking about the first quadrant, right? First quadrant. So basically if I write here x equals to 0, then not quadrant, sorry, first octant, y equals to 0 and z equals to 0, right? So if you take the intersection of this, okay, then you will see that is in the first octant. Okay, so I have already drawn the shape. The shape will be somewhat like this. I hope I'm not wasting my time in tracing the curve. Tracing you can do. We have done this multiple times in our normal calculus chapter. So that's why all those concepts will be used here. Okay, everything will be used. So now if I just name my surfaces, right? If I just name my surfaces. So let me name this. This one is looking very difficult because as I move along, right, the direction, you need normal vector outward from the volume will change, because my volume is this is a closed surface, right? This is like a 1/4 part of a cylinder. 1/4 part of a cylinder. So obviously I will name this surface as surface 1. Okay, I will name this as A, B, C, D, then this will be E and F. Okay, and let me name like how many surfaces we have. I have this surface, okay, then I have this and this top and bottom. So this I will name this as 2, this will bottom will name this as 3, and this surface and this surface, right, thus rectangular ones. So this right, this will be simply negative, this also will be negative, both of them will be negative, doesn't matter. So this I can name as, this is 4 and this as the fifth one. Okay. So like, can you tell me the direction of this? Can you tell me the direction of this surface too? You will say, sir, this is simple. Normal outward vector. This is in the y direction. Hence, like, just keep this in mind also. This is in the xz, right? Our circle-like structure will be in the xz plane, and here y is going from 0 to 8. So I will not explain all this. I will not explain the tracing. If you are not able to understand the tracing, you go back and watch the lectures. So y is going from 0 to 8. So now the important point, can you tell me the direction of this surface too? You will say, yes sir, very simple. It is what? Along the positive y direction, which is plus j cap. Can you tell me the direction of surface 3? Yes sir, very simple. It is in the opposite direction of positive y axis, negative y axis, which is in the minus j cap. Can you tell me the surface of this fourth surface? Yes, again, right? It is in the opposite direction of the z cap, which will be minus k cap. Can you tell me the like direction of the surface of this fifth surface? Again, right? Opposite to the x axis, which is in the positive k cap, right? Positive k cap. So what is important? The important is surface 1. That is what I am skipping. Can you tell the surface direction of the surface of this surface just with one glance? Can you tell me it? You will say, sir, I am thinking, but I am not able to tell you the surface, right? It is like I'm confused. Whenever you're confused, go to the method 2. Go to the simply method 2. Don't think about anything. So what you have to do? You have to write it in terms of phi. So I don't know this surface, right? This surface is some function of x, y and z, because as I'm moving along this surface, the direction is changing. If I move along this surface, the normal vector outward to this surface is always j cap. Okay, if I move along this, it is constant. But here, if I move along this surface, the direction is also changing. You need normal vector outward is also changing, right? It is changing always. So here what I will do? What is the equation of this curve? What is the equation of this curve? The equation of this curve is what? X square plus z square equals to 9. That is exactly the equation of this curve. So I will write the equation of this curve as x square plus z square equals to 9. Now I will choose my phi. I can go two ways from here. I can choose my phi as x square plus z square minus 9. Okay. And I can choose my phi as x square plus y square. Sorry, let me just bring this over here. This will be 9 minus x square plus y square. Now you tell me which one I will choose. I'll choose that. Okay, you tell me which one should I choose. Okay, this one or this one, because the direction will just come opposite if I choose the other one. So here what I'm observing, you need normal vector outside of the volume, pointing outside, and this curve, right, level curve is increasing. So what I will choose? I will choose this f of x y z greater than 9 because it is increasing in this direction. So I will choose this greater than 9 because my phi will always the direction of the phi will always be phi greater than 0. So as I want greater than 9, that's why I will choose this, not this. So this one I will choose and not this, because this point direction, like I can get some intuition, right? This is going in the direction where this curve is level surface is increasing greater than 9. So I will choose this, not this. Okay, so I'm not going inside this, I'm going outside. So outside. Okay, so we'll use method 2 and we'll use this projection method, right? So basically first thing we have concluded. Now we have concluded we choose our phi as this. Now the next thing is you have to compute the surface integration, right, of this surface 1 dot ds. Now I am confused. Which region should I choose? Which region of projection should I choose? I can choose this region R1, which is on the xy plane, so this will be somewhat like this, n cap dot k cap. Okay, or I can choose the region 2. I can lower the size of this, choose the region 2, not this, you can copy this again, which will be on the what, YZ plane, and region 3 as XZ plane. So this will be on the YZ plane, and this will be on the XZ plane. So this will be plus j cap. This is just a mod sign, right? So it doesn't matter, plus minus j cap doesn't matter, mod sign. This will be I cap, this will be R2, this will be R3. I'm confused, I'm also confused, I don't also know. So what do? You try to compute this n cap and you write this f dot n cap. Okay, then you see which one are cancelling out and then you compute that. So what you do, computing like n cap, right? So what will be my n cap? N cap will be, so I'm computing for surface 1 right now. So my n cap is basically grad of phi upon mod of grad of phi, which is equals to this, right? 2x I cap plus 2z k cap divided by this 2 will be outside, x square plus z square, which is equals to what? X square plus z square is equals to 9. So this will be 3. This will be x I cap plus z k cap by 3. Okay, so this will be your case. This is your direction vector. Now what do? You write f dot an. Okay, basically you write f dot an. So what is your f dot an? If I compute my f dot n, right, so it will be simply equals to I cap and k cap I have. So I cap component is 6z and k cap component is minus x. So this is I cap component is 6z times what, x by 3. So this will be 2xz, and k cap component is x minus x, and this is what, this is plus z by 3 minus xz by 3. Okay, so this is your I cap and j cap component if I compute f dot an. Okay, so now what I will do, I will take few things in common. So this I can write, I can compute my surface integration S1 as, I can take common 2x minus 2 minus 1 by 3, which is simply 6 minus 5xz by 3, right? This is simply 5xz by 3. And I don't know, right? I don't know what ds I have to choose. Dx, dy, dy, dz, I don't know that. So I will write all the 3, right? I will write all the 3. So if I write all the 3, what will happen is this ds, right, can be anything. First of all, I can choose dx dy upon what, n cap, basically this n cap, or I can write this a n cap also, it doesn't matter. Like sometimes I write like this n cap and they are interchangeable, right? So don't worry about this. So a n cap, all these things are same only, don't worry. Okay, so n cap dot what, n cap dot k. If I do n cap dot k, this will be what, this will be z by 3, z by 3. If I do n cap dot, this is now dy dz, so this will be I cap dot n cap, which is again x by 3. And next is, this is dx dz, which is k cap dot, not k cap, sorry, j cap dot n cap, and there is no component of j over here, so this will be simply 0. So this one is anyways gone, this one is eliminated, I have denominator 0, eliminate. Now here I have x by 3, z by 3, choose any. Whichever projection you find simpler. So this, right? This means I'm taking the projection on the dx dy plane. So if I'm taking the projection on the dx dy plane, so I'm taking the projection here. This is like a rectangle. Okay? This is like a rectangle, which is easier for me. Okay? Which is easier for me. So I will choose this. If I would have taken the projection about dy dz, okay, which would have been same also. So this also would have been a rectangle. If I ever place my sun here, or if I would have placed my sun here, it doesn't matter. Okay, I'm getting a rectangle and the rectangle is same only, so it doesn't matter. So I will choose anything, choose any, but it doesn't matter, choose any. Choose any. Okay, so if I choose any, I can choose any. So what is easier for me? Dx dy, I have seen it more, so I will choose dx dy. So what I will do, I will copy this. Okay, if you are not able to understand, like, quickly you go through the lecture and I will quickly summarize what I did. Okay, quickly summarize what I did, and like so that you will be able to recall like what we exactly did once I finish this question. So here I will just delete these things, right? Delete all this. So this one will be simply, I am placing my sun up here, right? Placing my sun up here. Placing my sun up here. So basically the projection will be on xy plane. So projection will be just like a rectangle, right? Projection will be just like a rectangle on the xy plane. Projection will be just like a rectangle. Okay, and you know I'm going from y equals to 0 to y equals to 8. So this surface is what? This surface is y equals to 8, and this surface is y equals to 0. So this is very simple. This is 0 comma 8, and this is what? X, I think x was going from 0 to 3, I believe. Yeah, x is going from 0 to 3, right? Oh, not 0 to, yeah, 0 to 1 only, sorry. X was going from, this planes are cutting it here. X equals to, just hold on a second, x equals to 1 is in this plane, right? So this will cut it here. Okay, this will be a bit wrong. This will be x equals to 3 actually. That's my bad. This will be x equals to 3, not x equals to 0, x equals 3. So if you have like picked up this mistake, that's very well by you. Okay, so this will be x equals to 3, like this will cut it over here. So I will have 3 planes, right? One is this plane, one is this y equals to 0 plane, then okay, no, y equals to 0 plane is this, y equals 0 plane is this, and y equals to 8 plane is this, and z equals 0. So I hope you are good with the curve tracing part. So this will be 3 comma 0. Okay, obviously I will place a like a strip over here. Okay, this is just a rectangular region, will be very simpler for me to solve. Okay, so what is happening is that this is dx dy upon z by 3, and this is what? Xz by 3. So z by 3 is getting cancelled. I have only 5x left. So this will be simply be replaced region 1. Okay, this will be 5x dx dy, and this is very simple, right? This is just a rectangular region. So this will be 5 by 2 x square 0 to 1, and this is 1 only. So this will be simply 5 by 2. Okay, sorry, this is not going 0 to 1. Sorry. Like I have been so accustomed to 0 to 1, so there I make the mistake. This will be 0 to 3, and this will be y is going from 0 to 8, right? So this will be 5 into 9 into 2 cubes, so 2 square is 4. So this is 20 times 9, which is 20 times 9 is 180. So this will be 180. Now this is 180. Can we compute the other surfaces? So I will compute one more surface, and others I want you to try by yourself, right? One more surface I will compute, and others I want you to try by yourself. So let's compute the y equals to 0. Okay, let's compute this one first. This one first, right? Y equals to 8 plane. So if I want to compute the y equals to 8 plane, what I'll do, I'll just copy this thing, right? Whatever I did from the previous methods. Okay, that I will compute, because that is being used with the previous method only, not with this method. Okay, so basically if I compute this, right, if I copy this, only for this one where my surface vector was a function, there I had to think about this. Anyways, I will add all this, right? I will add this. Basically my overall integration, okay, close integration of f dot ds will be simply the summation of the what, 5 surfaces, right? I equals to 5 to, so not I equals to 5, I equals to 1 to 5. Basically the open line integration, open surface integration of each of the regions, right? Ri f dot ds, or you can write si also, f dot ds. Okay, I just want to recheck one thing what I have written over there. I got, yeah, si, you can write anything. Okay, f dot ds. So yeah, let's solve for this one. If I solve for this one, this will be my S2. Okay, what is the name of this S2? The name of this S2 is what? DCE. DCE, right? DCE. DCE. And what is this? This is y equals to 8 plane, right? Y equals to 8 plane. So this will be y equals to 8 plane. Okay. And what I will choose? I will choose my phi as y minus 8, right? Because it is increasing on the levels of it is increasing. Y minus 8. Obviously my n cap will be very simple now. I don't even need to compute anything. N cap will be what? Plus k direction. Not k, sorry. In the j cap direction. Already computed that. So this time, right, my ds will be very simple. Okay, it will be simple. Dx dz. I don't even need to choose anything. Think about anything, right? Ds can be anything. Dx dz. I've already learned this in the previous method. So if I'm taking the projection on the dx dz. So if you place a sun over in this y direction, you take the projection on the xz plane, what do you see? You see a what? Quarter circle. You see a quarter circle, right? So this will be a quarter circle simply. So this time my projection won't be that simple, it will be different. So you have to use parametric transformations. So this is why it is very useful. You will see a quarter circle. It is not a line, it is a surface. So you will see a quarter disk. Okay, not a circle, sorry. You will see a quarter disk, because it is enclosing a volume also. So this is covering a surface. You will see a quarter disk. Now if you want to solve this, right, if you want to solve this, it will be a bit difficult for me to solve. Okay, if I just want to solve it using Cartesian, so what I'll do, I will take help of polar coordinates. So like that is, like I told you, right, either you use like surface vector, also you can use polar coordinates, but there we didn't need the polar coordinates because the region was simple. So I will take a arrow, I will take this row, okay, and my phi, how is my phi moving? Phi is moving from phi equals to 0 to phi equals to what? This is phi equals to what? Pi by 2. And this projection is where? Dx dz. So here if I observe carefully, my this is x positive and z positive. So z will be in the top side, x will be in the bottom. So this is going from x to z, right? X to z. So this will be z axis. Okay, Okay, so yeah, and row, how is my row moving? Row is this disk of quarter disk of radius radius 3, right? Radius 3. So obviously I'm covering this whole thing, so row is moving from 0 to 3. Okay, so this is the most important part. I'm covering from 0 to 3. So like obviously I have to do transformations. So my like before doing the transformations, let me just compute few things, right? So like let me compute f dot an. So I'm computing along the j cap direction. So j cap direction, what is j cap? If I do j cap, this will be 2x plus y. So this will be s 2x plus y dx dz, right? So the important point is my y is fixed, y is 8, so it will be very simple. So this will be, I can break this down into two parts. This will be dx dz plus this will be simply dx dz only, right? And 8 is obviously here, y is constant 8. Okay, so this is simply area of quarter disk. That is easy, but this one, right, I have to compute. So obviously what type of transformations you are doing, this is in the x axis, so this will be rho cos phi, z will be rho sin phi. This you are expert, so I won't explain this much. So my dx dz will be converted into rho d rho t phi, and I have already told you the limits of phi and rho, right? So this one you can simply do, this will be x rho cos phi, so this will be rho cos phi into rho d phi plus area. What is the area? Area is what? Pi r square by 4, because it is a quarter disk. So pi r square 9 pi by 4 into 8 also I have, so this will be 2 into 9, which is 18 pi. Rho is going from 0 to 3, this is going from 0 to pi by 2, so this will be rho cube by 3, so 1 by 3 into 3 cube into cos phi 0 to pi by 2. What is it? It is some positive area, so it will be simply minus sin phi. So sin 0 is 0 and this is 1, so it will be 1 only, right? It will be 1 only. Okay, and of course I have a 2 also outside, right? Don't forget the 2 here outside. So I have a 2 here outside plus 18 pi, so it will be 9 times to 18 plus 18 pi, so it is 18 into pi plus 1. So this is the answer simply. Okay, so obviously you have to sometimes convert into polar formats also. That's what I meant over there when I talk about cylindrical. Like whenever your like direction vector is some function of x, y, z, you solve using projection method that particular surface. For the other surface you solve using normal method, because the direction is very simple. So what I want you to do is do all these surfaces, right? I hope these surfaces are easy. Now I have solved for this, you can solve for 3. It is very easy. Okay, you can solve for this, is again a rectangular region. Okay, you can solve for this, right? Whichever is suitable to you. So I will solve this and then again I will come back. So I have solved the surface integration of all the 3 regions, of all the other 3 regions. So solving those in front of you would have been just a waste of time. So let's first go through one by them. Let's first go through them one by one. So this one is surface DCE. If I see DCE is this surface, right? This top surface. Okay, no, not the top, this bottom surface. This would be AFB, right? I haven't changed the name. This should be AFB. Okay, this is surface 3. So this was at y equals to 0 plane, where okay, this will not be equals to phi equals to y. This will be phi equals to minus y, because here my level curve is decreasing. Okay, I'm going y less than 0. That's why I have to equate it as phi. This will always be y is less than 0, I'm going towards y less than 0, y less than 0. Okay, that means like my phi will be always on the greater than 0 sign. Now, so what is greater than 0? Minus y is greater than 0. That means I have to equate phi as minus y, and exactly that is what I have done. Like this is just to give you intuition. Anyways, you can directly compute that it will be in the minus j direction, and ds will be the other two, dx dz. And now if you do take the dot product, it will be same value as the previous one, just extra minus sign will be in front of it. Here the value of y is 0, so this will get vanished and I will be left with only 2x, and minus sign will be there. So whatever I've computed, like I don't need to compute this anyway, right? Because like sometimes what shortcut you can do, this x dx dz 2 times this, you name this as I, and here I'm computing the same integration because the region projection is the same only, right? This is in the negative sign, so they will anyways get cancelled. So your all this time, right, of solving these things will be saved. This has come minus 18, here it has come plus 18 pi. 18 pi has come as extra, so you didn't have to solve this, you could have saved your time. So like that is how you save your time in examination hall. So those two will get cancelled and only plus 18 will remain. Again, the surface 4, that is a BCEF, that is z equals to 0 plane. If you observe it carefully here, BCEF is this plane where my z is 0, z equals to 0 plane, which is basically the xy plane. Now what is the projection? It is simply a rectangle, so solving this will be simple. And what is the direction? Direction will be minus k cap. Minus k cap means plus x, minus k cap into minus x will be plus x dx dy. So this will be plus x dx dy, and x dx dy will be very simple because I'm just computing the double integration over a rectangular region, which will be 36. Next, if you compute x equals to 0 plane, x equals to 0 plane will be this one, right, where my x value is always 0, which is the yz plane. Again, this is a d e f surface, and the direction is what? Minus, okay, this is wrong actually, this will be minus I cap, right? This I've written here wrong, this will be minus I cap. Okay, it may so happen I speak something, okay, and like he writes something else, like I may change that to like the correct one afterwards, but if I don't change that, you can always ask doubt in the Telegram group, right? So this will be minus I cap, and this is minus I cap. So if I do minus I times this plus 6z, that will be minus 6z dy dz, and the region is again rectangular, and z has 0, 3, and y has 0, 8, 0, right? So yeah, this will be minus 6z dz dy, and if you compute this simply again a rectangular region, this will be simply minus 216. Okay, now if I add the 5 regions, what will I get? I will get 180 plus 18 pi plus 18 minus 18, these two get cancelled, plus 36 minus 216. So overall I will get minus 180 plus 180, this will get cancelled, and I will be only left with 18 pi, and 18 pi will be my answer. So that will be my solution to this question. Okay, so I hope you got the answer to how to solve this. So anyways, you will be given simple surfaces only, you will not be given like too much difficult, else it will be impossible for you to solve in the examination hall. So they will take care of that, don't worry. Okay, this was simple only, except that first surface, everything else was simple, routine, as we did in the previous question. Okay, so let's take another example. This is the last example. We have been given a vector like this f. We have to calculate the flux of f bar through the upper side of the triangular region, triangular ABC, with vertices at point A 1, 0, 0, B 0, 1, 0, and C 0, 0, 0, 1. So this is C, this is A, this is B. Okay, so we have to calculate the upper region. Upper region means the level surface above this. So basically it should come somewhere around here, and the area is this. Area is this, and it should come on the upper region, that is on the positive side. On the positive side. Okay, no, not this. Now, can you just explicitly say me the surface? What is this? I cap, J cap? This is like a triangular surface, right? Triangular surface. Like you have like my coordinates are here. Okay, this, and the bottom surface, and I have placed a triangle like thing. Okay, triangle like thing. Each of its vertices are on one of the axes. So it's like a 3D figure. It's not simply a plane, right? It's like a 3D figure. So it's like triangle is present on this plane, and above this plane. So they are present at different points. It's like a 3D figure. So I cannot simply say the surface. What is the surface? I cannot say, right? The direction of the surface. So what I can do? I can write the equation of this surface. What is the equation of the surface? If you ever are confused, right, regarding like a simple triangle or something, this is anyways very simple. You can anyways compute. Like you can observe here, my in this plane, my x is always 0. So x is always 0. What is the equation of this line? It is what? X plus not x, sorry, it is z plus y equals to 1, because both of them are satisfying. Again, here on this plane z is 0. What is the equation of this line? It is x plus y equals to 1. Again, what is the equation of this line? It is x plus z equals to 1. So everything plus equals to 1. So now if I want to write this in terms of our equation, it will be x plus y plus z equals to 1. So from there you can find the surface. Anyways, I have already told you how to like identify this surface, right? This I have already told you. So this you can easily identify the equation of the surface. So it will be like your surface will be x plus y plus z equals to 1. Now as I am going on what? Greater than 1, on the direction greater than 1, so obviously my phi will be what? Phi will be x plus y plus z minus 1 as I am going on the greater than direction. So phi the direction that phi gives is always greater than 0. So obviously this is greater than 1, so this is greater than 0. Cool, fine. So obviously now I will find my a n cap. Now what I am applying here? I am applying the method 2, because this is not a simple shape and I don't know the direction of my surface, area vector, direction of my surface, right? So basically they have told us to compute the open surface integral. So if they are asking us to compute the flux F, so I should have written this first only. I should write using method 2, and flux means basically I'm computing the open surface integral of this particular surface f dot ds. Okay, so that is what this question is asking us to find. So a n cap will be simply grad of phi, which will be xi plus yj plus zk divided by x square plus y square by z x square plus y square plus z square. Okay, this is under root, right? So what is this direction basically? Sorry, I made a mistake here. This should be okay. Sorry. I am also mad. This should be I cap plus j cap plus k cap, right? Yeah, we also tend to make mistakes. I cap plus j cap plus k cap and root 3. This should not be function of x and y and z. Why is it should not be? Because whether I am here or here, the surface vector is along the same direction only. It is not changing according to position, because this is just a like plane kind of thing, but a tilted triangular plane. Okay, not a square plane. So this is like a plane kind of thing. Hence the surface vector, direction of surface vector won't change along the plane. That is the more important part. So my direction vector is this. So again, what region you need to choose? I don't know. Let's see what region we can choose, right? So this f dot, let us compute f dot ds. If I compute f dot ds, this will be like I am getting all the regions. This will be x minus, okay, not f dot ds, I am computing f dot a n cap, x minus 2z, root 3 is anyways in front, and this is x plus three y plus z plus 5x plus y. Divided by root 3. This is x 6x 7x, this is 3y 4y, and this is minus z. Now here, right, I don't have anything in common which can easily get cancelled out. So whichever region I choose, it actually does not matter much. This is 5x. Yeah, whichever area I choose, it does not matter much, right? So like I'm confused, so let me compute the all of the three. If we compute all of the three, right, what you will see that your ds will be same for everything, right? Same for everyone. Okay, ds will be same. If we compute ds equals to what? The first one, dx dy divided by your a n cap dot k cap. It will be equals to dx dy divided by root 3, right? Because this is k cap, like this will be 1 by root 3 if I take the dot product. So this will be root 3. dy dz. What I can do, I can take okay, no, I won't do that. Dot I cap, it will be root 3 dy dz. So all of them will be same only, right? All of them will be same only. Now which one to choose? Which one to choose? That is the more important concept over here. So we'll just cut this and take this to the next page. Take this to the next page. I just copy this and paste this over here. This will be dx dz j cap root 3 dx dz. Now you can choose anything, right? You can choose anything, and as they are symmetrical, whichever region you choose, it doesn't matter. So for my simplicity, I can choose dx dy, but like if you take the projection along this z direction, right, you will get a triangle like this. If you take the projection along this along this y direction, right, again you will get a triangular like structure. Okay, if you take the projection along this x direction, right, again you will get a triangular structure. It doesn't matter. So as I am more familiar with xy, so I will choose along xy plane. So I will take the projection along the xy because it is giving me the same result. Okay, giving me the same result, so it doesn't matter whichever way I choose. So I'll choose xy. So if I choose xy, so here there will be projection, right? This will be the projection basically. So the projected figure will be look something like this. This is the R1 region, okay, and this is going from 1, 0 to 0, 1. Okay, so yeah, now you can obviously place a vertical strip over here. Okay, vertical strip over here, which will go from x equals to 0 to, not x equal to 0, sorry, y equals to 0 to, what is this, y equals to, what is the equation of the line, x plus y equals to 1. I already mentioned this earlier, x minus z, right? And of course you have to remember this thing, like this is your strip, right? This is your strip. So now you can simply put the values over there. So it will become simply just hold on a second, this is 7x minus 8y. So what will this get converted to? So your integration of this surface f dot n cap ds will get converted into, I will change this to region R1, 7x plus 4y minus this is z, and z here, right, this is what, this is z equals to 0 plane, right? Z equals to, not z equals to 0, sorry, z is some value here, right? Z is some value. What is the value of Z? So value of Z is what? Value of Z is 1 minus x minus y. That is the value of Z. As I move along this, right? As I move along this, the Z also changes. If you remember, Z also changes. As I move along this, Z will be somewhere around here, right? Z will be somewhere around. So Z is equals to this, varying according to this. So Z is equals to 1 minus x minus y. So that is what I have to put instead of Z. So I'll put instead of Z, this is 1 minus x minus y, because I am converting this into two variables now, dx dy. And like if Z was constant, I would have put Z here as I done previously. If you see here, yeah, not here, here, y equals to 0 plane. So my, like I was computing about y equals to 0. So if y is 0, I just replace this y with 0. So but in this case, Z is not 0. Z is some function of x and y. So I will replace my Z as some function of x and y, and that is exactly what I am doing over here. So I hope you are keeping up the analogy. So this will be root 3, and here also I have root 3 in the bottom, dx dy. So this will become I will write here so my integration will become simply eight x plus 5y minus 8x plus 5y minus 1 dx dy. Okay, minus dx dy. So now you can simply compute. So what is the, like this will be, I can break this down. This will be 8 times x dx dy, and this will be plus 5 times y dx dy, and this is minus integration of this region dx dy, which is the simply the area, right? Which is simply the area. So or you could have done this like in one hand also. Okay, what I will do this in single integration itself. That also you can do, or doesn't matter. So whichever, you are expert at solving double integration, so I don't need to mention anything. So this will be 8 now x square by 2, and okay, so I have taken a vertical strip, so obviously I have to put y first. So I will just do one thing. This will be y equals to 0 to y equals to 1 minus x. This will be x equals to 0 to x equals to 1. This is x dy dx plus, okay, I will just keep this in, okay, no, let's do this like this way only, same integration only. This is 0 times 1, and this is simply the area, right? Area of the region. What is the area of the region? It is half, right? 1 by 2 into 1 into 1, so it is half. So this will be 8 into x square, not x square, x into y, x into 1 minus x, which is 0 to 1 x minus x square dx plus, okay, I've just not written this function here. I have completely skipped this dx, not dx dy actually. This will be dy dx. So this will be y square by 2. This will be 5 by 2, 0 to 1, 1 minus x whole square dx minus half. So this will become, okay, I came back all the way back. This will become simply 0, and then if I put 1 over here, this will be 1 minus 1, 0 only. Okay, this will be anyway 0. Okay, that is a sad thing. So this is anyway 0. So this is 0 plus, now this, right? This will be minus of like somewhat like this, x minus 3 by this, and this will be going from 0 to 1. Minus sign is in front, and obviously I have 5 by 2 also. Minus 5 by 2, and obviously I have minus half also. If I put 1 here, if I put 0 over here, this will be minus, like this will minus 1 by 3, this will be 5 by 6 minus 1 by 2. Okay, so now if I do this, I'm doing anything wrong. This is 2. Just hold on a second, let me check if I'm doing everything correct or not. Okay, sorry, I'm really sorry. Okay, this is not 0. I'm really sorry. This will be 8 times x square by 2 minus x cube by 2, 0 to 1. Okay, so this will be 8 times 1 by, this is 1 by 2 minus 1 by 3, which is 1 by 6. What is it? No, 1 by 2 minus 1 by 3. So it's 3 minus, yeah, 2, 1 by 6 only, yeah. If I multiply this with 8, this will be, like this will be 3 and, yeah, 4 by 3 plus this, right? So if I take a common denominator, this will be 2 times, this will be 8 plus 5 minus 3 equals to 6, 2, 10 by 6, and this is 5 by 3. So this is the answer that you get. This is the amount of flux that will get out from this region, right? From this region, if I have a vector field like this, like, well, let me just explain you quickly. If I have a vector field like this, how much amount of flux will get out? So my vector field is like this. Okay, if I just copy this diagram, and if I have a vector field like this, like I don't know exactly how my vector field is varying, but let me just assume something. My field is like this. Now it is obviously crossing this surface. Now what does flux tell us? Flux tells us how much amount of flux is crossing this surface perpendicularly, and that is what this is asking us in the question. So this is my answer. This is the amount of flux. Like what I'll do, as this lecture has already gone long, I'll quickly summarize this lecture in the start of the next lecture, so that you can get a quick recap, because all this concept, right, all these concepts will not be that much important, because mainly what we'll learn in the next few lectures, that is Green's theorem, Stokes theorem, and Gauss's divergence theorem, that will be mainly used. But this also helps if those theorems fail, then you use this. So I will try to quickly summarize all this in the next lecture. Okay, thank you for watching, and I will see you in the next lecture. Hey everyone, and welcome back to PrepFusion. So today we'll start the lecture 4A of vector calculus. In this lecture, we learn about the different theorems of vector integral calculus, and this is very, very important. Afterwards, whatever that we learn, right, will be very, very important, because this has the maximum weightage. So you have to listen to me very carefully, whatever I will explain. But before going into the theorems, obviously I told you that I will summarize quickly whatever we learned in the previous lecture. So we will quickly summarize, right, what we learned in the previous lecture. So I will go from the starting. We learned about surface integration. So in surface integration, how do we compute? We have two methods of computation. Like firstly, there are two types of surfaces: open surface and closed surface. Open surface are just simply those surfaces which doesn't enclose any volume, right? And closed surfaces are those surfaces which enclose a volume. That is the difference. Okay, and like how can we compute the surface integration of closed surface? By breaking it to different open surfaces, just like simply single line integration. Just like that, we can solve the surface integration. And for solving the surface integration, we have to find the ds vector. So how do we compute the ds vector? The ds vector has a direction and has a magnitude. So the direction you can easily find out by, for regular shapes or for like known planes like x equal to 0, x equals to 1, those planes we know how to write the direction of the surface vector. But if you don't know, then you have to compute using grad of phi by magnitude of grad of phi, which is phi is the basically the equation of the surface, different level surfaces. Okay, and how to find the magnitude? Magnitude is basically whichever plane I am in, that dx times dy, that I will explain. So here then I explained about non-oriented and oriented surfaces. So if I have non-oriented surfaces, that means I don't have any direction associated with it. So it can either, like, it can be clockwise or anti-clockwise. They haven't given me any direction, particular direction of the surface along which I will move through the curve. So it can be either plus minus, but in general, like if they are asking me to find one direction, I will tell them the positive. Okay, that's why anti-clockwise is positive. And if it is oriented, then there is no confusion. You can simply find out the direction using right hand thumb rule. So, and you will compute the direction. If they have given some weird surface, then obviously you have to go for grad of phi by magnitude of grad of phi. Now, in the increasing direction or decreasing direction, that depends what they have mentioned. If we have been given a closed volume, obviously it will be on the outward direction. In this region, okay, if this is, let's say this is x axis, this is x equals to 1, so this is greater than x equals to 1, so like phi will be like the direction of grad of phi will be phi greater than 0. So phi greater than 0 means x greater than 1, then that is correct. Okay, x minus 1, then that means x minus 1 greater than 0. So that will be my equation of the surface, that I have also used in the next few examples also. So, and this will be what, x equals to 0, this is x less than 0, right, x less than 0. So this time I will take my x to the right hand side, it will be minus x greater than 0, phi will be minus x, hence phi is greater than 0, hence it will be minus I cap. So that's why I chose as minus x and not x. I hope you got the point. The grad of phi always gives me the direction along the phi greater than 0 direction, along which phi is increasing. Okay, that is what grad of phi gives me. So I told you open and close. So basically the first problem solving approach is when everything is simple, like cuboid, cubes, all those things, right? And you know the directions, then you simply write your dr like this. Okay, like your dr is this, right? And from dr you can take the analogy how to write your ds. Your ds can be of three types. If it is on the k cap, I cap, or j cap. Okay, k cap means you are on the xy plane. Basically the area will be small length along dx and along dy. So it will be dx dy times k cap. Okay, and this is how we solve the question. You don't have to think about this, you just take the strips and from there you will understand how to take the limits. You don't have to think about this. Okay, so then we solve this question, right? We broke it down into 6 individual surfaces, open surfaces, then we computed the area and we did the projections. So projections I am not explaining that much because all those things have been explained in detail in the normal calculus chapter. So this one was done. Then I told you the method 2, also the significance of this integration, right? Surface integration. The significance is how much flux has been cut by this particular surface, right, which is perpendicular to it. That is the more important definition about surface integration. Then I told you about the second approach. Second approach is when it is getting difficult, when you don't know the direction of the surface. Okay, then obviously you have to use this formula, grad of phi upon magnitude of grad of phi, and you write your this region, right, about which region you have to take the projection, that you take on hold for a second, that you decide later on after computing all the 3, right? It will take you 10 seconds more, but that is fine, because what will happen is that few things may get cancelled from here, right? May get cancelled. Whichever is cancelling the maximum things about that axis, you should take the projection. That will be the easiest for you to compute the surface integration. So that is what you do. And then we took this example, right? We took this example and we solved this. Only this surface was the difficult part, other surfaces were anyways easier. So we computed the area and then we solved the answer. Okay, so yeah, 18 pi was the answer. Then I gave you like a question about the triangular region, and it is a open surface, and we just have to compute the amount of flux that goes through the upper side of the triangle, and that is greater than this, right? Greater than this. So in this direction, so obviously I choose my phi vector. Okay, then I computed the directions, and then I computed the this surface integration. So obviously here I will replace my value of z as 1 minus x minus y. Why I will replace it? Because I'm computing with respect to dx dy, so obviously z has to be also a function of dx dy, and here, right, z is not constant. If my x and y are here, right, then obviously z will be somewhere around here. Okay, because z is also a function of x and y, because this is the function, right? If my x and y is, let's say, hold on a second, x and y is minus half, sorry, plus half and plus half. So x and y is somewhere around here, okay, somewhere around here, then my z will be 0. Then my z will be 0. If my x and y is, it can't be minus, x and y is, let's say, 1 by 4 and 1 by 4. Okay, it can't be 1 by 4 and 1 by 4. It can be somewhat, whatever it is, like whatever x is, right? Whatever is x, then like z will also vary according to this x and y. Z is a function of x and y, right? So obviously I have to replace this z with x and y. Then I will simply compute my integration. So if I compute, this simply becomes a double integration problem, and this you can do with ease. So we have done this so many times, so this won't be an issue for you. So we computed this and we got the answer that 5 by 3 amount of flux will cut through this area. Okay, we'll go along this in this direction, whichever direction we assume, in this direction, in positive sense only. Okay, so this was basically it for this surface integration with normal methods. Now we'll understand the theorems. So first of all, we study about the Green's theorems. In this lecture, we will only study the Green's theorem, and this is the most important theorem. Obviously, the other theorems are also most important. Don't worry. So in this integral vector calculus, I told you, right, the division of integration, closed line integration and surface integration. So in closed line integration, if it is in 2D, if closed line integration is in 2D, then you will use the Green's theorem. Okay, Green's theorem helps us with the relationship between line integration and surface integration. Basically, if I have a closed 2D curve, then I can, with the help of Green's theorem, I can solve the line integration and convert it into a surface integration. Okay, so basically the important point is it has to be 2D. And if I have a 3D, if I am in 3D space and I have to compute the line integration, I can use the Stokes theorem to again convert the line integration into surface integration. This is the Green's theorem, is the simplified version of Stokes theorem that we'll see. Next is surface integration. If I want to compute the surface integration, if my surface is open, then again what I can do, I can use a Stokes theorem to convert into line integration. So why am I doing all this? Like, if some surface integration is looking very difficult to me, so I will use the help of theorem and convert it into some other format which is much more simpler to me. So that is the main reason, right? So this is also, sometimes they call it as inverse Stokes theorem, but I will just call it Stokes theorem in opposite direction. It doesn't matter. Still, it is Stokes theorem, right? When we will use this in example, there we will see. And then if my surface is closed, so then what to use? Then I will use the Gauss divergence theorem, which is the relationship between the surface integral and the volume integral. So if my surface is closed, obviously I am enclosing a volume. That means there has to be some relation. So why am I giving you, like telling you this? The important point is you have to remember when to use which theorem. Okay, so if I have a line integration and it is closed line integration, then I will use Green's theorem. If I have a 3D closed line integration, I will use the Stokes theorem. If I have a surface integration which is open surface integration, I will use the Stokes theorem again, because these things are same only. If I have a closed surface, then I will use the Gauss divergence theorem. All this we learn. So today we learn the Green's theorem. So what is the Green's theorem? So basically Green's theorem, the equation is somewhat like this. If I have to compute a closed integration of some m of xy, which is a function of xy, dx plus n dy, okay, n is also a function of xy, along the xy plane, then this can be simplified del n upon del x minus del n upon del y bracket into dx dy. And you have to take care of the sign, right? You have to take care of the sign. What is the sign? Where see, my curve is in the xy plane. So this is in the xy. So you have to take care that we are talking about 2D. We are talking about 2D plane encircling a surface as in anti-clockwise direction. Also, this is important. They have mentioned the direction as well. This is the default direction. If you want to go in the opposite direction, what you have to do? You have to simply add a minus sign. So this also is important. Direction is also important. C is this and S is surface bounded by the curve C. So if I have C like this, which is in the anti-clockwise direction, so S will be simply the surface bounded by the C, or surface encircled by C. Okay, so basically if we have been given any closed line integration like this, where I have to compute f dot dl, right, you just break it down in 2D you just break it down in terms of dx and dy, then you can take the partial derivative. Okay, this one you take with respect to del x and this one you take with respect to y. This is with dy, so you will take with respect to del x. This is with dx, so you will take with respect to del y. So this is how you remember. This is how you also used to remember. And also never forget that this orientation is in the anti-clockwise orientation. You should never forget this. Very important. Else you will make questions wrong. Just due to one negative sign, you will get 0 marks. Okay. So this is in the anti-clockwise direction. That's why first I will differentiate with respect to partial differentiate with respect to x. Then I will partial differentiate with respect to y. Okay. So like you can see, for clockwise orientation of curve C, we put a negative sign on right hand side of the Green's equation, right? There will be some negative sign. So basically what I will do, I'll just copy and paste this. Okay. And if my C is in the clockwise notation, clockwise direction, I will just put a negative sign, right? So here C orientation is in the clockwise orientation. C is in the clockwise orientation. Okay. And obviously M and N are continuous and differentiable at every point S. So this is also another key point for you to apply the Green's theorem. So here, right, you can only apply the Green's theorem, like this equation, only when M and N are continuous and differentiable about the region in which you're computing your single line integration, or about the surface, right? At every point in S in the surface, it has to be continuous and differentiable. This is a very important point. So whenever you're applying Green's theorem, okay, whenever you're applying Green's theorem, you should check, first of all, you should check whether you have closed line integration or not. Okay, whether you have been asked to evaluate closed line integration or not. Then you should check whether it is in anti-clockwise or clockwise direction. Also, you should check whether it is 2D or 3D. All this in simultaneously, right? Not one by one. You can check it this simultaneously. And I will write Green's theorem in short as GT. So anti-clockwise or clockwise, then 2D or not. Then you should check what if M and N are continuous and differentiable. Okay, so these are the 4 things. Just remember these 4 things and you are good to go. Remember these 4 things, that you have to check whether M and N are continuous and differentiable, whether you are in the 2D plane or not. 2D means xy, xz, zy, it doesn't matter, but it should be 2D. Okay, not just in xy plane, but in general for Green's theorem we only used to solve for xy plane only, but it doesn't matter, it can be any 2D plane. Next is anti-clockwise or clockwise direction. Anti-clockwise, this will be with positive sign. Clockwise, this will be with negative sign, as shown here. And obviously it has to has closed line integration. Then only you will be able to solve. These are the 4 things. So let's solve this question. Before that, I will just drink a bit of water. So we have to evaluate a closed line integration. So this is a closed curve, right? As they have mentioned, like C is a circle. So C is a circle which is a closed curve in the clockwise direction. So from here I am scanning the question. So this is a closed curve. So this is a closed curve, and this is in the clockwise direction. These 2 things are there. And what is this? This is continuous, right? Polynomial. This is continuous, and this is in 2D, right? Simple 2D. There is no z term over here. Simple 2D. So obviously I can compute my f dot dl, which will be along the circle. So I will write the surface itself. So this is on the xy. Plane, and this is the circle, right? Basically this is x square plus y square equals to 4. Okay, so this will be simply 3x plus 4y dx plus 2x minus 3y dy. Now this is what? This is m dx plus n dy format, m and n. So I can simply use the Green's theorem, right? Green's theorem I can use, which will be simply the double integration along this surface. If I do del n upon del x, this will be 2 minus del m upon del y, which is 4, right? This is simply 4. And do remember that we are computing in the clockwise direction, so there will be a negative sign associated at the front. Don't forget that. And obviously this is dx dy because I am on the xy plane. So this is simply minus 2, not minus 2, plus 2 surface dx dy. So basically what is it? This is simply the area of the surface dx dy, which is simply pi r square, which is pi into 2 square, which is 4 pi. So this will be simply 8 pi. 8 pi will be my answer to this question. Okay, so yeah, let's go to the next question. Next question, few key points. So I told you, right, Green's theorem provides a relationship between closed line integral and open surface integral. Open surface, so this surface, right, is open, right? This like I've gone through the contour in the clockwise direction, okay, and the surface is itself open. It is not enclosing area, but the curve is encircling a area. Okay, sorry, the surface is not enclosing a volume, the curve is encircling a area. So that is very important. Obviously I can go from 1 to 1, right? Only I can go from closed line to open surface and from closed surface to open volume. So yeah, that is what this gives. And like Green's theorem is valid when C is closed, M and N are differentiable and encircled by the curve C and is in a 2D plane. Okay, I've already told this, right? What things you need to check. And C must be simply connected curve. Now we understand about simply connected and doubly connected, right? So this, right, if I have been given a region which is like a annular region where, let's say, I have some cavity inside, right? So I'm only interested in this region. So here I'm going in anti-clockwise direction, here I'm going in clockwise direction. I don't know the direction, so computing the Green's theorem for this will be challenging. We'll come to this in the later stages of this lecture, don't worry. So for now, just understand that this is a doubly connected region, okay, doubly connected curve, okay, doubly and this is a simply connected curve because there is just a one crossover, right? There is no intersection here also, like even though there is no intersection, but like can you say the direction? No, right? You can't say the direction explicitly. So how to find the direction we'll understand towards the end of this lecture. So this is a simply connected region. Okay, simply connected region. So like let's do a question, right? Let's do few questions. From there we'll understand. This is a GATE 2016 question. So suppose C is a closed curve defined by x square plus y square 1 oriented in anti-clockwise direction. The value of this integration over the curve. So C is a circle, so it is a closed curve, and we have to evaluate this, right? A single line integration in the 2D. So your brain should click that this is telling about the Green's theorem. So obviously you will apply the Green's theorem, and you can see this is polynomial, so there is no issues about applying the Green's theorem. So I can directly compute m dx and n dy. So this is my m and this is my n. So del n upon del what? This is with respect to, this is y, so with respect to x. So this will be 2xy minus this will be with respect to y. This is again 2xy, and I am computing the this differentiation at the surface dx dy, which will be simply equals to 0. Anyways, this is an anti-clockwise direction, but anyways, this came out as 0, right? So like sometimes this also happens, they give this much simpler question, so answer will be 0. Now this also I think came on gate, I don't remember which year. Here they are asking you to compute the line integration, and you can see that this is a closed line integration, so that's a good thing. Again, you see polynomial, that's a good thing. This is in 2D, that's a good thing. So obviously you will use the Green's theorem. So if you use the Green's theorem, you can compute compute this integral. So this is my, if I just write f dot dl, what is my f dot dl? It is simply xy dx plus x square dy. Okay, so it will be m dx plus n dy. So again, if I differentiate this, this will be 2x. This will be 2x with respect to x, and this, if I differentiate this with respect to y, this will be x only, minus x. Again, in which direction is this? This is in the anti-clockwise direction, so this will have positive sense. Integrate this, okay, into dx dy. So this is just a what? Just a rectangular region. So limits are constant. Limits are very easy. So I can put the limits. Okay. X dx dy. My x is going from, if I just take a strip, right? If I just copy this region, it's like this is just cakewalk for you, right? So if my x is going from, can you delete this? X is going from okay, I will take a horizontal strip because I have dx first, so it doesn't matter anyways, this is just a rectangular region. So x is going from 1 by 3 to 2 by 3, 1 by 3 to 1 by root 3 to 2 by root 3, and y is going from what? Low to bottom, so bottom to top. So y will go from 1 to 3, 1 to 3. So it will be x square by 2, so 1 by 2 into 4 minus 3 by 3, so it will be 1 only. So 1 into 3 dy, it is 2 times 1 by 2, which is equals to 1. So 1 will be your answer. So option B will be your answer to this question. Like with Green's theorem, you can just solve your question like this, right? चुटकियों में सॉल्व कर सकते हो अगर लाइक पी वाई क्यूज बहुत ईजी आए थे. अब रिसेंटली लाइक द पेपर टफनेस हैज बिन in the tougher side, like it was good, paper difficulty was on the tougher side, but previously you could have solved questions like just like you don't need to think like in the previous lecture we were solving one question for like 20 minutes, but here it is taking you 20 seconds. So that is the difference using Green's theorem. So like again, if you have to compute now, this is in the 2D, but this is in what? This is in xz plane, right? I can observe this in 2D because here I have k cap, that is the z axis, and this is the x axis. So this is in the xz plane, that's good. This 2D, but here, right, like how to use the Green's theorem, So what you should do, like if you remember something, is that I go from x to y, then to z, then again I come back to x, okay? And all this is in the positive sense, right? This is in the positive sense. So if I am going from x to y, this is in the positive sense. So if I have xy plane, then what do I have? Then I do del, just hold on a second, let me just first compute this. So this is f dot dl c, so this will be equals to 3x plus 4z dx plus plus 2x minus 3z dz. Now which one to differentiate and which one to subtract? So first of all, they have told me in anti-clockwise direction. So let me just draw my curve. So this is my what I will draw. First I used to draw xy plane, then xz yz, then this will be zx, and z will be my z will be my x-axis. Just remember that z will be my x-axis because this was xy, so x was x-axis, yz, so y will be x-axis, the first variable will be the x-axis, and z will be my x-axis. Okay, so zx is my x-axis, so and this is in the anti-clockwise direction, ECW. This is in the positive because I'm going from z to x. If I'm going from z to x, this should be positive, which is correct. If I'm going from x to y, this should be positive, this should be in the anti-clockwise direction, which is again correct. Okay, so all these conventions I hope you're able to follow. If I'm going from x to y, it should be anti-clockwise. Yes, x was here, y was here, and I was going from x to y. Good. If I'm going from z to x, it should be in the anti-clockwise. I'm going from z to x, and yes, this is in the anti-clockwise direction. So whatever I have drawn here is correct. Whatever I have drawn here is correct. Okay. So next, when it was xy plane, I used to write del n upon del x. Basically, here there was some term with dy, but I am in zx plane. So here, right, the second term should be this term x, right? So I will just swap these two to convert this to my suitable format. So I'll copy this, swap this two, because dx should be last and dz should be first. Okay, so here obviously what I'll do, so now I can name this as m, this as n, and m is function of x, zx I can write zx, and n is function of zx. Like, why am I teaching all this? I could have simply taught you the formula, but I am teaching you, what if you forget the formula? Then how can you recall this in the examination? Or what if you forget the formula? So how can you go from the basics? That's why I'm teaching you this thing, right? So that is also important, because you will not be able to remember everything. Like in the next slide itself, I have the formulas written, right? For zx plane, for yz plane, all those things. But what if you forget that? Can you derive that? That is the more important part. Okay. So now you have written it like this. Now what I used to do, I used to differentiate this, right, and with respect to the other variable, that is with respect to z. Okay, so I will differentiate this with respect to z. So this will be converted into double integration surface, and this will be del n upon del z minus, as this is in the anti-clockwise direction, this will be the positive one, del m upon del x, and this will be dz dx. So this will be simply, what is del n upon del z? It is 4. Okay, it is 4 minus del m upon del x, it is 2. 4 minus 2 into dz dx. So this is 2 times area of the zx plane, which is simply a circle of radius what? Radius 2. So it will be pi r square. 2 times pi r square into 4, which will be 8 pi. So again, your answer will be 8 pi. So just keep this in mind. So in the next slide itself, I have all the formulas. Okay, I have all the formulas. But what if you forget the formula? What if you forget the formula? Can you derive it? That's how you derive. You just rewatch it, that section, you'll understand what I meant to say over there. Okay, just from the basic, the top formula, right? Top formula is this one. From this, can you derive the other two? That is the more important part. So basically, if I am xy plane, then I know this formula, del n upon del x minus del m upon del y. I remember this. This one you cannot forget. You cannot afford to forget. Okay, this is in the xy plane. And obviously, you will see, like, first I will differentiate this with respect to the opposite variable. With respect to the opposite variable, right? And this also same. I will differentiate this with respect to the opposite variable, partial differentiate. And here I will write the xy plane simply. So xy is xy. So you just understand the symmetry here. This is what? M as a function of xy, and this is also xy, right? So everywhere xy is present in sequential format. xy, xy, xy. Here also xy. Here also xy. Okay, so you just go according to the sequence. If you are in xy plane, then you will write first dx term, okay, then the dy term, and then you will differentiate with respect to x, and you will differentiate with respect to y the other term, the coefficient of the dy term, and you will differentiate with respect to y the other term, the coefficient of the dx term. Okay, and the same thing is happening over here also. If you are in yz plane, so you go along with that notation, right? What is the notation? It is x, y, z, then again you come back to zx, then again you come back to zx. So first I covered y, x, y, now we'll cover yz. So if you write yz over here, so everything should be matching according to yz. This is yz, this is yz, this is also yz, and this is also yz, and this is also yz. So all the things match according to yz, and obviously you will differentiate the opposite one. Here this is with respect to dz, you will differentiate with respect to dy, the n one. Okay, and like this. If this is zx, this is zx, this is zx, this is zx, and this is also zx, and this is also zx. So simple thing, right? I just taught you, and your c is in the anti-clockwise direction. C is in the anti-clockwise direction, then you follow. If it is in the clockwise, you just add a negative sign. Okay, so that's how to solve in different planes. But remember, all these are in 2D planes, right? 2D planes. So I will write different 2D planes. Okay, different 2D planes. So let's do few questions. Okay, let's do the question. You have to compute the closed line integration of this closed surface, right, of this function. So this one is like pretty simple only. Like what we can do, we can simply use the Green's theorem again. If we use the Green's theorem, what is f dot dl? What is my f dot dl? So my f dot dl is simply minus y by x square plus y square dx plus x dy by x square plus y square. Okay, along the surface which is dy. Okay, not surface, sorry, this is a closed line integration only. So now I can use the Green's theorem, right? I can simply use the Green's theorem. So what I can do, I can write this like this in the this in the anti-clockwise direction. So this will be positive. So this will be along the surface del x, like this with respect to differentiate this with respect to x. So this will be x square plus y square whole square. Okay, and now I'll differentiate the numerator, which will be x square plus y square minus, this is x, this is 2x minus 2x times x. Okay, and this will be minus, this will become plus, this will be x square plus y square whole square, and this is 1 into x square plus y square, and this is minus 2 y square. Okay, and if I write over here, this will be dx dy. Okay, so what can I write over here? This will be y square minus x square plus x square minus y square divided by x square plus y square whole square dx dy. So this will be simply equals to 0. Okay, so is this correct? This is not correct, right? This is not correct. Why is this not correct? Like I intentionally skipped. I think you also saw it, that this function, right, whatever function this is not continuous about this point. about inside the surface about the 0 comma 0 point. Okay, so what I will write, I have checked everything, but I haven't checked the continuity. So like we have to check that. Obviously we have to check that is it continuous or not. So I will write function may slash may not be continuous at 0 comma 0. Okay, it may or may not be continuous at 0 comma 0. So we have to check for continuity. Okay, we have to do that. So obviously Green's theorem may or may not be applicable. Okay, so to check for the continuity at 0 comma 0 point. So that we'll check for continuity. So what you can do, I told you right how to check for continuity for two variables. First you put the value of one variable. First you check limit of one variable, then you check the limit of the other variable, right? So because if you put x equal to 0 comma 0, this function will go to 0 by 0 format. So whenever you have rational function, be careful. So we'll say here rational function be careful. Okay, if you have a polynomial function, be happy because it will always be continuous. Okay, be happy. So obviously we have to check for continuity. So what I will do is that I will check my continuity limit as xy tending to 0 0 of what, this any function, right? I can take this now. What I will do, like anyways this one is also going 0 by 0, this one is also going 0 0 at 0 equals to 0. So let me just check for one thing. So I will write my f vector as fx I cap plus fy j cap plus fz k cap. So I will just check continuity for now fx. Okay, for now fx, because I don't have 3 dimensions. For now I will check for fx. So if I check for fx, this is limit. Now what I will do, how we used to compute the limit of two variables. First I will compute this for limit as y tends to 0. What is fx? fx is minus y upon x square plus y square. Okay, as y is tending to 0. So if y is tending to 0, this will be 0 upon x square, which is some finite. So this will be limit as s tending to 0, which is 0 itself. Okay, now let me compute the other one. This time I will tend my x towards 0. So if I tend my x towards 0 first, so now I will do this one, limit as x tends to 0 minus y x square plus y square. This is limit as y tends to 0 minus 1 upon y, which is minus infinity. That means limit does not exist, right? Because these two are not equal. This is some value k, okay, and this is some value k l, okay, and l is not equals to k. Hence limit does not exist. Okay, so function f is not continuous, hence Green's theorem So if you didn't understand this part, you have to go through this again. This part is very important. Green's theorem is not applicable. Like Stokes theorem is also not applicable. Okay, how can I write this? I don't have space. Okay, so like then how will you solve? Now this is a closed curve, and told you at the starting of the lecture of the vector integral calculus that we can break down a closed curve in 4 open curves, right? Open curves. So we can break this down in 4 open curves. So I haven't solved a question like that, so I was waiting for this question, right? So I can break this down into 4 curves. This is completely a one curve, single curve. I can break this down into 4 curves. This will be, let's name this curve as C1. Okay, let's name this curve as C2, C3 and C4. So obviously my this integration, right, close integration. So obviously when Green's theorem fails, then we have to solve using basics. So, and this will never fail. Okay, so this is f dot dl. This will be equals to summation of I equals to 1 to 4 integration of open curves f dot dl. Okay, so I have 4 curves, so I'll solve according to that, and this will be always valid. Okay, and obviously I'm not passing through x equal to 0 equals to y, right? This curve is not passing through that, but surface was. Curve was not, but surface was. That's why. So for C1, what is the main important point? For C1, I can observe, I will just make this more bigger, that my x is constant. So my y is constant, x is varying. So for C1, my y is minus 2. Hence obviously y is constant, y is never changing, dy will be 0. X is varying. Okay, x is going from, this is just a straight line, right? X is going from minus 2 to plus 2. Minus 2 to plus 2. So obviously dx will be non-zero. Okay, dx will be non-zero. Okay, so basically what can I say? That what can my integration be converted into? So my integration, right, only I will take the x component and not the y component, because dy is 0 anyways. So we'll take the x component. So let me just bring this back. Okay, f dot dx, this, let me bring this back. So obviously my dy is 0, so this one will get vanished, only dx will present, and y is what? Y is constant, y is minus 2. Okay, so I will replace this like this, C1 f dot dl, y is minus 2, so this is minus of minus 2 divided by x square plus y square divided by x square plus y square, which is minus 2 whole square, and dx, and x is varying from minus 2 to plus 2. So anyways, this is a even function, so obviously I can write 2 times 0 to 2. This is plus 2 is also outside, so this is 2 times 2 dx by x square plus 2 square, right? So what can I write? I can simply write that my formula, this is what formula? This is tan inverse x form, right? 2 times 2 tan inverse like 1 upon a, that is 2, times tan inverse x upon a, x upon 2, and my x is going from 0 to 2. So I have applied here even function rule, right? So like I will not explain all this we have covered in definite integration. So now this is x equals to 2, this is tan inverse 1, which is pi by 4. Tan inverse 1 is pi by 4, so this will be 2 times pi by 4, which will be pi by 2. Okay, so what is the next curve? Next curve is this, right? And this curve where my x is constant, x is plus 2. Okay, x is plus 2 and my y is varying this time. My y is varying. So I will write, I'll just copy and paste this thing. Curve 2. This time my x is constant, which is x equals to plus 2. Hence my dx will be 0. My x is not varying, but my y is going from minus 2 to plus 2. So dy will obviously be not equals to 0. Okay, hence here, right, which component I will take? I will take the dy component. Dx is 0, this one will get vanished, this one will remain. This is x dy and x is plus 2, so this will be plus 2 divided by y square by plus 2 whole square. Everything will be just similar, along similar lines. This will be y, okay, and this will be y by 2, and this will be simply what, pi by 4 only, right? Pi by 4, so this will be pi by 2 only, same thing only, nothing will change over here. Okay, now the next curve, what is the next curve? Next curve is my, here my y is constant again, y is plus 2, but my x is varying from plus 2 to minus 2. So I will copy this. Okay, everything will be same. Okay, you can save time. Okay, this didn't copy this. Okay, why it doesn't copy, I don't understand. Okay, this will be C3. My y will be plus 2. Okay, obviously my dy will be 0, but my x will vary from plus 2 to minus 2. This will be plus 2 minus, and this will be x square. This will be minus 2. Okay, basically what will happen if I just swap the limits? Okay, if I just swap the limits, this will become plus. Okay, I will just swap the limit, so a minus sign is there, so only a minus sign will be in front, everything else will be just same as it is, right? If I just take care of this will be x only. Okay, okay, just hold on a second, am I doing this correctly? If I just keep the minus sign in front, okay, I'm just reversing the limits and then I'm multiplying by 2. Is there anything I'm doing incorrect? That is what I'm thinking about. Let me keep it as it is. Okay, let me just change, let me not change the minus sign, right? Let me keep it as it is. Like I'm thinking I'm doing something different, right? Something different. So here what will this become? This will be positive only, because this should come, like I have computed it, like it's written like pi by 2, so that's what I'm thinking. This should come 2, so 2 times x upon a, just hold on, 2 times this, yeah, x upon a, so this will be 1 upon 2 tan inverse x by 2 going from plus 2 to minus 2. Okay, plus 2 to minus 2. Okay, here also I have a negative sign also. That is what I was thinking. I had a negative sign. This was, that's why you don't copy paste. Like you had here minus y. Okay, that is what I was thinking. I may have been doing some mistake, right? So I will just do that thing again. So here I had minus sign also, right? Don't forget the minus sign also. So this was already a minus sign. I had minus y over here. So if I just swap the limits and then I multiply by 2, use the even property integration, this will become plus. So this becomes plus. So this will become plus again. This will be plus pi by 2. Okay, this will be x by 2. Okay, this will not be y, this will be x. So that's why you don't copy paste. I am allowed to do copy paste because I have to save time, right? But you are not. You just use as much paper as possible. So let's come back to the fourth curve where this time my y is varying but my x is constant, that is minus 2. So I will again copy this one. this is fourth curve. So here my y is varying, so and my x is equals to -2. Okay, so dx is 0, but my y is going from +2 to -2, +2 to -2. Okay, so dy will not be equals to 0, but again there is no minus sign over here, and x is -2, so this will be -2 simply, and I'm going from +2 to minus. So again minus minus will become plus, and I have swapped the limits and I have used the even property. So this will be dy into y square, and this will be tan inverse y upon 2. So this will be pi by 2 again. Okay, so just let me check all the limits if I have placed. Okay, here I have done one mistake. This should be dy, right? This will not be dx, this should be dy. That is what I was thinking. Okay, this is along C2, this is along C3. Else the people who are just studying from notes, they will get confused. This is along C4. Okay, now you can simply add all this up, right? Add all this up. So we have already written that our closed line integration will be the summation of all these three, right? So what is the summation of all these three? It is simply, okay, it's simply pi by 2 plus pi by 2 plus pi by 2 plus pi by 2, that means 2 pi, complete 360 degrees. Okay, so the answer to this question will be simple 2 pi. Okay, so like this is one question. Like here also, what you can observe, here you can observe that again I have got a rational function, right? Rational function, and this is in 2D, and I have been asked to compute the closed line integral, because if you see the region, it is like common region between x plus -2 and this circle. So we'll see if this is closed surface or not. So I will say this is rational first of all. Okay, and let me trace the region. So if I trace the region, first of all I will draw the x equals to plus -2. This is what, x equals to -2. This is x equals to +2. This is y equals to +2. And this will be my y equals to -2, right? Y equals to -2. Now if I write this, right, x square plus y square in the clockwise direction. So this, right, is in the anti-clockwise direction. This is a square region, and this is in the anti-clockwise direction. So the region will be somewhat like this, right? They have mentioned this, but also another region is there. Okay, another curve is there, which is x square plus y square greater than equals to 1 in the clockwise direction. So let me just draw this. So this is in the clockwise direction, right? This is in the clockwise direction. So basically what surface is this talking about? It is talking about this surface, right? So I have a annular like region, so it is talking about this surface. I'll just copy this because this is important to me. I will paste this somewhere. Okay, for now I will paste this here only. Okay, and what is the region it is talking about? It is talking about, if I can, this region. It is talking about this region. Okay, so how to compute this integral, because this is a closed surface, obviously, because I have got a surface, right? Not closed surface, sorry. This is a closed curve, because this is also closed, this is also closed, and I have got a surface. Okay, I've got a surface. I can encircle a surface, but how to compute the integration with the help of Green's theorem? Can I compute it? I told you, right? Green's theorem is applicable only for simply connected curves. Only for simply connected. This is a doubly connected curve. Why? Because this has two equations, right? First one is the outside one and then the inside one. So what can we do? What can we do? What you can do? What you can do is, let me just copy this. Let me just reduce the size. Okay. Here, let me just reduce the size. And let me copy this again. Okay. Paste this over here. Okay, let me just paste this. Let me reduce the size of this. Let me just keep this here. Yeah. All these things here only. Here, and just move this here. What I can do is, I can do one thing. First of all, at 0 equals to 0, this is not continuous, and this is not 0 equals to 0 is not included, right? 0 equals to 0 is not included. You can see 0 equals to 0 is not included. Only this portion is included. Okay, so I should be happy, but again I am sad. Why am I sad? 0 equals to 0 not included. Okay, but what is the problem? The problem is this is doubly connected. Again I become sad, because I don't know how to solve doubly connected region. Okay, doubly connected region. So what I will do, I know how to use Green's theorem in simply connected, right, or singly connected region. What I will do, I will make this singly connected. What I will do, just above this, right, just above this x-axis, I will just break this. I'll just break this slightly. Okay, broken this. Now what I will do, I will break here also. Break here also, and instead of completing this, I will complete this curve, this path, right? I will complete this path. Let me just add this. Okay, and this. Okay, and here doing the same thing. This, just take note that I am not changing the directions also. The directions, whatever here, they are intact. And this, okay, and this will be as it is, as they were. Okay, so what do you observe? This is very small break, and the surface area that I am covering here, surface area that I am covering here, and surface area that I am covering here, the surface area are almost same. So instead of following two curves, I can follow these two curves. So this is the first curve and this is the second curve, right? And what you can observe, this is also in anti-clockwise direction, and this is also in anti-clockwise direction. So overall, whatever was the direction of the outer curve, right, it took the direction as it is. So if I just simply add these two, okay, if I compute this singular integration and this singular integration and add these two, I will get the same result. Okay, so what will happen if I just compute it for this C1, and if I compute, like, apply the Green's theorem for this C2, I will be simply able to compute this, right? I will be simply able to compute this. So what I can write, okay, this I have used this anyways. What I can write, my f dot dl, right? F dot dl is some mdx plus ndy. F dot dl is some not f, sorry, f dot dl is some mdx plus ndy, sorry, m, I will write, yeah, mxy dx dy. Okay, so basically what can we write? We can write it like this, that if I compute this, right, with respect to C1 curve, so let me name this as C1 curve and let me name this as C2 curve. Okay, C1, if I am computing this f dot dl with respect to C1, my function is not changed and mdx and dy will also be same. So obviously I can simply compute this, right? I can simply compute with respect to C1 this, and like if I want to compute this whole thing, right, if I want to compute this whole line integration f dot dl, this whole C, I can write it in terms of, okay, I will write here f dot dl plus C2 close curve f dot dl. Okay, then what I can do, these two, right, these two individually I can apply Green's theorem. These are just single curve only, I can apply Green's theorem. So I can write here, this is surface 1 del n upon del x minus del, and both of them are in anti-clockwise direction, so sign won't change. Dx dy, and the same thing I will copy this, reduce the size actually. This is so overall, right, I can write this in terms of one surface only. So what I am doing, I am just computing what, open surface integration, right? I can add these two and combine the whole surface. So I can combine this whole thing, right, as a single surface, which is del n upon del x minus del m upon del y, okay, and dx dy. Now even if you didn't understand, this is like a proof for from doubly connected how I go to singly connected. This is like an intuitive proof. If you don't understand, doesn't matter. What is important? The important point is that like if you have a doubly connected curves like this and the outside one is the anti-clockwise, so overall your direction will be anti-clockwise and your Green's theorem will not change. That is the important part that you have to take care of. Okay, that is the important part. Now simply we can compute this, right? So what is del n upon del x? I have already computed this, I think. So we have already computed this, right? Here, right, we have computed this. This was del n upon del x was, if you remember, yeah, it was like del n upon del x minus del m upon del y was equals to 0. So this answer will be anyways simply equals to 0. Because we already know, and we know that we are not including 0, 0 point is excluded, right? So it doesn't matter. Okay, it doesn't matter, it is excluded, hence the answer will be 0 to this question. Okay, so I have also made you made the short notes here basically. So if I just go through this once, just, yeah, here, right, here I have made the short notes. So basically if you see here that if I have the outer region as anti-clockwise, which is also known as positive sense, then your close curve integration will be this same only, right, in the positive sense. If my outer curve is clockwise, then this will also come with a negative sign. So that's how for a doubly connected, that's how careful you need to be, nothing else. So that's the thing. This is the thing that you need to keep in mind. So we can put this in the short notes. Okay, so this is a key point that you need to keep in mind, that always remember whatever the outer curve is, okay, you go along with that. Or how you convert this, that also I have explained, right? Just I have given you a intuitive proof. So this is the outer curve. Just hold on a second, let me check if everything is recording or not. So yeah, I told you, right, if you have a doubly connected region like this, and if the outer curve is anti-clockwise, so overall your Gain's theorem you will apply for anti-clockwise. You can apply, okay, don't worry. And for this, if my outer curve is negative sense, that is the clockwise, then I will apply in the negative direction, clockwise direction, right? It all depends on the outer curve. So let's solve this question. We have to evaluate this f dot dl, where f vector is equals to 2x plus y cube I cap plus y plus 2x cube j cap, and C encircles a region between circles of radius 1 and radius 2, and center of them are same 0, 0. Anyways, this is polynomial, so that is good. But they have given two circles, so this is like a annular region. So if this is a annular region, I can draw the regions. The first circle will be something like this, x square plus y square equals to 1, and the second circle will be x square plus y square equals to 2. So this is my second circle, x square plus not 2, x square plus y square equals to 4, and this is my first circle, x square plus y square equals to 1. And what area is it talking about? It is talking about this area, okay. And what has it said to us? It has said positive sense, right? Positive sense, or it could have said it as this in anti-clockwise direction, not in anti-clockwise, sorry, this in the, we write this here, we can make changes to the quotient, right? This in clockwise direction, and this I can actually, I can cross over this, doesn't matter, I write here anti-clockwise direction, okay. So like the curve's direction will be something like this. This will be in the, okay, not anti, sorry, this is in the, and that is fine. So this will be in the anti-clockwise direction, and this will be in the clockwise direction, okay. So overall I will choose only the outer surface area, so it will be positive only. So my closed line integration of f dot dl, I can write like this. This will be simply 2x plus y cube dx plus y plus 2x cube dy, okay. This is in 2D, the function is continuous, and I am talking about anti-clockwise, and it is obviously what, like I have converted this into a singly connected region. So this I can simply write in terms of formulae, in terms of Green theorem, okay. This will be plus, because the outer ring is positive, outer curve is basically anti-clockwise direction, del n upon del x. So del n upon del x is 6x square minus del m upon del y, which is 6y square, not 6y, sorry, this will be simply 3y square, okay. 6x minus 3y square, okay. So this is dx dy. Now how do you solve this? Now this is a bit difficult to solve this, right? What you have to do, you have to use polar transformations. So you use polar transformations, you are in 2D and your coordinates are also varying, right? They are in circles, so obviously with that you will understand this solving this simply is very difficult, and the region is also some weird shape, so I will use polar transformation. Okay, so obviously what you can write my x as rho cos phi. Obviously your rho is varying this time because I'm covering this whole region, right? So rho is changing here, rho is changing, rho is not constant, rho is changing. So x equals to rho cos phi, we'll use white color. Y equals to rho sin phi, and like how is my rho varying? Rho is varying from what? Not 0. Rho is varying from this radius to this radius, which is 1 to 2. Remember, radius is varying from 1 to 2, not 1 to 4, and not 0 to 4. That also you have to understand. 1 to 2, and my phi, obviously I am rotating over the whole circle, so it will vary from 0 to 2 pi, and obviously my dx dy will be replaced with rho d rho d phi. This is all cakewalk for you. Okay, so like I have already like I haven't drawn it visually, so I will just draw it and show you visually that how my rho is varying and phi is varying. If I write here, this is my phi, right? Somewhere in between, not phi, sorry, this is my rho and this is my phi. So you can directly observe that this is rho equals to 2 and this is rho equals to 1 and this is phi equals to 0, and obviously if I rotate full circle this will be phi equals to 2 pi. Okay, so this is how you convert. So let me just write this down. Rho will move from 1 to 2, 0 to 2 pi, and this will be converted into 6x square minus 3y square. So this will be 6 rho square cos square phi minus 3 rho square sin square phi, and this is rho d phi. So if you observe one thing, 3 rho square cos square phi minus 3 rho square sin square phi, it will be 3 rho square cos 2 phi, and here also I have a rho, so this will become 3 rho cube cos 2 phi, and this will be left only, this will be 3 rho square cos square phi, so this will be 3 rho cube cos square phi, and this is d rho d phi. Now if I compute this, I can compute this separately. So cos 2 phi will be 0 only, because integration of cos 2 phi over 0 to 2 pi will be 0. So this first term will be 0, plus this one will be 3 by 4 rho raised to power 4 going from 1 to 2. And what is the integration of cos square phi? So if you remember the formula, it was here, right? This is not, we can't do this with the formula, right? We can't do this with the formula because this is going from 0 to 2 pi. Okay, so what you can do, what I know, that my cos square pi will be something like this. It will be this, like I don't know the exact shape, but the negative will become positive and it will be like this, right? So if I am computing my area between 0 to pi by 2, this area and this area will be same, and this area will be same, and this area will be same. So basically I am computing over 0 to 2 pi. If I just compute over 0 to pi by 2 and multiply it by 4, you will get the same area what I was getting from 0 to pi by 2. So I can write here 0 to pi by 2, 4 times this cos square phi. d phi. So I'm just showing you the technique, right? You can solve it using that double angle formula also. So this will be 3 into 2 raised to power 4 minus 1. Now, if you remember the Wallis formula, what was the Wallis formula? In the top, it was if both of them are even, like sine power and cos power are even, then you use pi by 2. So pi by 2 you write first, and then k times pi by 2. So basically, like why is sine power even? You have sine raised to power 0, which is even, cos raised to power 2 is even. So you write pi by 2. Then what you used to write? You used to write here 1 less. So 1 less the power, which is 1. Obviously you don't have sign, you don't care about the sign. Then you write m plus n. 0 plus 2 is 2. Okay, and then you stop, because you stop until 2 or 1, until you get 2 or 1. So it will be this. So which will be equals to simply 3 into, this is 16, only this is like what is this, rho square rho cube, this is 16 minus 1, which is 15, into pi by 4. So this will be 45 pi by 4. Now if you are confused here, this is the answer. Basically this is the answer. So if you are confused at this case, right, if you are confused at this case, then just hold on a second. What I was talking, if you are confused, like in this, you can simply convert this into sine, like single power, right? What you can do, you know, cos 2 phi is cos square phi minus sine square phi. So what you do, you write 1 minus cos square phi. So this will be 2 cos square phi equals to cos 2 phi plus 1. I'm just writing in code language. Okay, so cos square phi will be cos 2 phi plus 1 divided by 2. So now you can replace this over here, right? So this integration will be 0, and this integration will be 2 pi times 1 by 2. So which will be, okay, which will be pi itself. 2 pi times 1, which is pi, because here if I see 4 times, this is pi by 4. So 4 times pi by 4 is pi itself. So we got the same answer. So you do it this way or this way, you will get the same answer only. Okay, so yeah, this will be your answer basically. So yeah, the answer to this question will be 45 pi by 4. So yeah, I'm just doing bit of symmetry. This is like cos square phi, and this is in phi direction. This is pi by 2. This is, but this is pi 8. Okay, so yeah, you can solve it like this. This is, what is this? This one. This will be, yeah, this will be 2 pi. So yeah, this is the answer to this question. So like the lecture has been finished. So this lecture is very important. If you are not able to understand anything, just go through this once again. I have broken down every point, okay, in very simple manner. So what things you need to keep in mind? So first thing is, in general, the questions will come from Green's theorem, Stokes theorem, or divergence theorem, Gauss divergence theorem. So for Green's theorem, what you have to understand, it gives the relationship between the closed line integration and the open surface integration. So if you have been asked to compute the closed line integration, you can convert this into something like this, which is much easier for you to compute, because if it is in 2D, you can easily compute without solving all those things, right? In the first lecture we solved, right? It was taking us too much time. So we can compute it like this. Now few conditions are there. First of all, function has to be continuous and differentiable within the surface. Next, we have taken anti-clockwise orientation. We are in 2D plane. Okay, so all these things you have to take in care. So after taking care, you can simply use all this, right? I have summarized also what you have to take care. So in general, you are given polynomial functions, Bindasi se, you can use Green's theorem. Okay, and if you have been given rational functions and your surface, your region is included, okay, region is included, then you have to take care, right? Then you have to check for continuity. If it is not continuous, you have to solve it basics. you are in bad luck. Okay, but if you have been given in 2D but they're in different planes, not in XY plane, then obviously I have told you how to remember, right? Go through that once again, repeat it once again, you will understand how to remember this. Okay, that's very important. Next, obviously, if we haven't given a doubly connected, not a simply connected, doubly connected region, then you have to be careful again. You have to be careful. Overall orientation will be orientation of the outer curve. Okay, that's how you remember orientation of the outer curve. And if you solve along with that, you will be able to understand. You will be able to simply, like, you can use the same formula: anti-clockwise plus clockwise minus for the outer curve. Okay, and you will get your answer. Okay, so yeah, I hope you understood this. If you didn't, you have to go through this again. This is a very, very important topic. You have to, no matter what, learn this very well. Okay, this is an easy topic and you can learn this, I hope. So I will start with Stokes theorem and Gauss divergence theorem in the next lecture, and then we will finish the vector calculus chapter. Thank you for watching, and I will see you in the next lecture. Hi everyone, and welcome back to PrepFusion. So today we'll start the lecture 4B of vector calculus. So what will we learn in this lecture? We'll learn about the Stokes theorem, inverse Stokes theorem, and the Gauss divergence theorem. So again, this is very, very important lecture, so you have to listen to me attentively. So you have to be very attentive during the previous lecture and this lecture, right? So these two lectures are most important, as most questions will come from these two lectures only in vector calculus, like in the vector integral part. So until now we have learned one theorem only, Green's theorem, which is also a great theorem. So what is Stokes theorem? Basically, Stokes theorem is the generalized version of Green's theorem. So it gives the relationship between closed line integration. Just hold on a second. Closed line integral and open surface integral. So if I have a closed line integral, right? Closed line integral, then I will be able to convert that into a open surface integral, and the conversion will bring like this, right? It will be equals to del cross f. So this f vector will be changed to del cross f, and I will be doing the dot product with the ds vector. So it is applicable only for open surfaces. Whenever there is open surfaces, then only I can apply it. Can be applied for both 2D and 3D. In Green's theorem, I could have only applied for 2D, but in Stokes theorem, I can also apply it for 3D. So that is the advantage of Stokes theorem. But what is the condition? Condition is again the function should be continuous and differentiable within the whole surface, right? Just like Green's theorem, it has to be continuous and differentiable. Just you, like, what should you be careful of? You should be careful of if you have been given a rational function, right? Rational function, then you check the continuity and differentiability of that function within the given surface, okay, of which the curve is encircling. So curve has to encircle the surface. All these things we know, like same as Green's theorem only, just the difference is this can be applied in 3D. Okay, so let's do one question and from there we'll understand. So here we have to compute the closed line integration along a region of circle, right? So basically this is covering a open surface, a curve which encircles a open surface, right? A open surface, okay, in positive sense, and we have been given this vector f, and we are observing that this is a 3D vector, so we won't be able to apply the Green's theorem. We have to go with Stokes theorem only. So else you could have simply apply like use this simple basics also that you use when your function is not continuous. Here I see this is a polynomial, so this will be continuous. So if I just draw the region, it's in the xy axis, xy, given a circle in the anti-clockwise direction, because this is in the positive sense, so this will be in the anti-clockwise direction. Okay, anti-clockwise direction. So like what we will do using Stokes theorem, what I can say is that I can convert this closed line integral into open surface integral by taking the curl of this field vector and doing the dot product of the surface ds, area vector basically. So what will be the del cross f? So del cross f will be, if I just compute this, this is 2x minus y, y minus z, minus y square z. So what will be this equals to? So if I computing for this first element, so this will be 2yz minus 2yz plus y. This will be 2yz plus y into I cap. Okay, then this will be, okay, this is also minus also, this will be minus also. Then this will be 0, this will be 0, then this will be 0 again, and this is minus 1. So this will be plus 1, right? Plus k cap. Okay, so let me just reduce the size of these things. Put this over here. So what I can write this as open surface integration, okay, along this surface S. This is the surface, right? This is the surface S of, what is this, 2x y minus 2yz into I cap plus k cap. Now what is the ds vector? What is the ds vector? This is the in the anti-clockwise direction. So what will happen? This will be outside coming towards me, so simply a dot. And if it is a dot, so this is simply what, k cap, right? K cap. So I will only have k cap over here, and obviously with k cap I will have what, dx dy, because this is in the xy plane. So this will be simply dx dy. So this will be simply s1 dx dy. So this will be what, area of this circle. So what is the area of the circle? This is a circle with radius 2, right? Radius 2. So this will be x square y square 2 square. This will be simply pi r square, which will be 4 pi simply. Okay, simply 4 pi, right? So you saw just how easy it was to compute this integral. So if you would have done a single line integral, right, we would have had to take what, this as rho cos phi, rho sin phi, and z would have been 0 anyways. So okay, this would have been gone, and we only left with this. So we can compute with that also. Like if you want to compute with basic thing, okay, what you could have done is that, so method 1 was Stokes theorem. Okay, and like in generally we try to use theorems only because that only helps us, but sometimes other methods also works. So if I use basics only, okay, what do I know? I know that my z is 0, okay, because this is in the region x square plus y square. So z is 0, right? Z equals to 0. So obviously I can convert this f dot dl equals to, this will be 2x minus y dx integration, okay, and here z is 0, here z is 0, this is gone anyways. So this is 2x minus, and what is y equals to? Y, now what I can do is convert this into in polar format. So here, right, I can write my x as 2 cos theta or cos phi. I can write my y as 2 sin phi, okay, and I can write my dx, all these things you already know, right? So I'll just reduce the size of all this, just hold on. Dx will be minus 2 sine phi to cos phi pi. So this will be simply, this will get converted into 2 cos phi. So this is 4 cos phi. And how is my phi varying? Phi is varying from 0 to 2 pi. Obviously I'm rotating over the whole circle. Minus y is 2 sine phi. And what is dx? Dx is minus 2 sine phi d phi. Okay, so here this will be like this will go from 0 to 2 pi. So this will be 0 to 2 pi 4 sine square phi 4 sine square phi d phi minus 8. I can write this as 2 sine phi cos phi, which will be sine 2 phi, and this will be 4 only d phi 0 to 2 pi. Okay, so anyways this will get cancelled, right? This will be 0. This will be 0. Now what is this? Again, right, we can use that funda that sine square phi, if I compute from 0 to pi by 2, and if I multiply that by 4, that will be simply 0 to 2 pi, right? It's same thing only. So I can convert this. If I multiply this by 4, this will become 16, and this will be pi by 2. This will be sine square phi d phi. Again, what will this become? So here this will become n minus 1, which is 1, divided by m plus n, which is 2, times pi by 2. And of course I have 16 over here. As both of the powers are even, this will be pi by 2 and not 1. So here this becomes 4 pi. So you can compute like this also. Okay, whichever way you find suitable, that you can compute, right? So you saw, like, we can use both methods. That's why you should be fundamentally strong. Whenever you ask to, you can use both methods, right? So if that method fails, you will use this method. So let's solve this question. Here you have been given a field, and you have been given this curve, and yc is the curve region bounded by the intersection of the planes y plus z equals to 2 and cylinder x square plus y square equals to 1. Now can you trace the curve for me? Like, we have done a question like this during our like a normal calculus chapter, right? During double integration. Okay, can you trace the curve for me? So basically my cylinder will be infinity, because this is like z from minus infinity to plus infinity. This is saying me that only, and this is saying me y plus z equals to 2. So this is yz plane. So here, right, it will be somewhat like this, y plus z equals to 2, and here x is varying from minus infinity to plus infinity. So I will be somewhat like this. Okay, and my cylinder will also be somewhat like this. So obviously I have to cut this top portion, right? They will cut this top portion, and my cylinder will be somewhat like this. Okay, this will be the region. Okay, this will be the intersection of the planes. Okay, so yeah, also one more thing I have to keep in mind. This is the intersection. C is the curve of the region obtained by intersection of these planes. So C is the curve obtained by intersection of this plane. So this, whatever plane I got here, that is the curve that they're interested in, over which I have to compute the single line integration, which is actually pretty difficult for me to compute, right? To get the equation of that curve, that is actually difficult. So what is happening is that I have a cylinder. Okay, the cylinder is, let me just draw the bottom of the cylinder. And this will be the top, right? Basically here this is like a closed curve, right? This is the curve that they are interested in. Okay, have they mentioned any direction? Okay, they haven't mentioned any direction. That is a bad thing. So I will by default choose the anti-clockwise direction. So this will be this positive z, and this is my curve C that they are interested in. So over this curve, right, obviously the equation of this curve at this point is y plus z should be equals to 2. Also okay, y plus z should be equals to 2, and along the edge, right, along the edge, okay, this is the plane, equation of the plane, right, and along the edge it has to satisfy this equation, x square plus y square. This curve has to satisfy this equation, right, x square plus y square equals to 1. So along that curve I have to equate that. Okay, so this is basically what, enclosing a surface. Okay, this is closed curve enclosing a surface. So can I apply Green's theorem? You can apply it, like you can do the single line integration. That will be again difficult, right? That will be again difficult. So because you have to compute this, like here z is also non-zero. So what you can do, you can apply the Stokes theorem. So you can compute the curl of this field. So we'll copy this, because every time I'm writing this is just daunting for me. So we'll copy this thing. Okay, so okay, let me check everything is recording, or this is recording, this is also recording, right? Yeah, this also, I just had to check whether everything is recording or not. So if I find the curl of this, because the important point is I know the equation of the curve, okay, but I don't know the what normal vector, right? That I don't know, so that I have to compute later on. But first let me do this. So I should have written here in anti-clockwise sense. That is wrong in my way. So if it is anti-clockwise in sense, right, so this will like go from x to y. Then like if it is anti-clockwise, this will go from x to y. I hope you understand this. X to y, that is anti-clockwise, right? So that's why this is going from x to y in anti-clockwise sense. Okay, I hope you got the point. So yeah, let me compute the curl first. So I just forgotten about the sense, so I had to mention the direction. So along the x component I have minus y square, y I have x square, and this is z square. Okay, so this will be, if I compute this, this will be 0 0, then this will be 0 0, and this will be 2x plus 2y. This will be 2 into x plus y k cap. Okay, so I have got the del cross f. Now what is my surface vector? Surface vector is n cap ds, right? And which plane I am in? Okay, this is not simple plane, right? Not simple plane, not a simple plane, not simple. Okay, so what I will do, I will use that projection method, right? Projection method. So obviously I have to write this phi. So what I will write my phi? Can you tell me? Like what is this equation of the surface? Equation of the surface f of x by z is what? Is equals to y plus z equals to 2. So this is y plus z minus 2. Now there are two options for me. I can write my phi of x y z as phi of x y z as, I can write it as, okay, just hold on, sorry, y plus f of x y z is this y plus z equals to 2, right? So I can write my phi of z as y plus z minus 2, or 2 minus y plus z. Okay, so what will I write now? If you notice the direction is in which way? Intuitively, if you say direction is in this direction, this is my n cap direction. So if you observe, this is a level curve. Level curve is what? Now level surface is y plus z. Y plus z, this region is y plus z greater than 2, and this region is y plus z less than 2. This region, okay, this particular region is not this way, y plus z greater than 2. Okay, so it is y plus z greater than 2, right? Y plus z greater than 2. And so obviously if it is y plus z greater than 2, so whatever phi I choose, right, I always get the direction as phi greater than 0. Phi greater than 0. Now if my phi is greater than 0, so here y plus z will be greater than 2. So this is correct. This is correct. So I will choose this. Okay, so like, why am I mentioning this point again repetitively? Few students may think that I am mentioning this like repetitively because I have like taught this previously also. Few students may have some doubt. That's why I want to clear this out, right? You shouldn't have doubt. How should you choose your phi? That is very important. So your phi will be this, right? Phi will be this, y plus z minus 2. So my en cap or n cap, anything you want to say, all those things are same only, will be grad of phi divided by magnitude of grad of phi. So grad of phi is j cap plus k cap divided by magnitude of grad of phi, which will be under root 2. Okay, so now we are ready to compute the surface integral. So this will be del cross f is 2 into x plus y. N cap is this I plus k by under root 2. But again, right, I don't know what is my ds. So for ds, I have to again hold on. So basically my ds will be what? Along which I am taking the projection. So ds I can write in 3 ways. Okay, just hold on. It can be dx dy divided by n cap dot k cap, right? So this is dx dy. N cap is j plus k, so it will be 1 by root 2. So it will be 1 by root 2. Okay, nothing will get cancelled over here. And this is dy dz. I will just reduce the size of this. Dy dz upon n cap dot I cap. So it is basically, again, if I do I cap, this will be 0, right? This will be dy dz upon 0. So obviously I will eliminate this. Okay, I will eliminate this. And next one is dx dz divided by n cap dot j cap, which is basically, again, fine. This will be dx dz divided by divided by 1 by root 2. Now can you tell me which plane you would want to take the projection by just seeing the surface? Let's go to the surface. Okay, let's go to this. Like, this is my surface, right? Which plane do I want to take the projection? If I like dy dz, what is it? I cannot take the projection along dy dz, dx dz. So dx dz is here, right, in this plane. So if I take the projection, now this is like a triangle or some shape. This is looking like a difficult thing for me, right? This is looking like a triangle, but I don't exactly, and I'm not able to exactly understand. But if I do along dy dz, right, xy plane, this is what? This will be what? This will be simply a circle. This will be simply a circle of x square plus y square equals to 1. That will be my projection, right? So I will choose this. This is the easier one. Okay, so basically the projection, if I just copy this figure, right, if I just copy this figure, like all these things should be cakewalk for you now, because like we have studied double integration in very details. So if I just project it, if I just bring my sun here, and if I project it on the xy plane, so this will be somewhat like this, right? So this will be just equation of circle. Was it equals to 1? Yeah, it was equals to 1, right? So this is my like projected dx dy area. Okay, so let's compute this. Here I have root 2 at the top and root 2 at the bottom, so root 2 gets cancelled out. And okay, sorry, I had x plus y plus k cap also, right? K cap also. So this had also k cap, right? Okay, this had also k cap, sorry. So along the surface, okay, so this will be my what, region R. So I have to compute this along the region R, sorry, not surface. I can name this anything, RS doesn't matter. So this will be 2x plus y, root 2 gets cancelled, dx dy. So now what you can do, you can simply convert this into polar again. Okay, you can do that because that will be much more suitable to me, or you can just directly compute it also, but directly computing it will be a bit difficult because along the curve is a bit difficult. So what I will take the polar transformations again. So this will be like x will be rho cos phi, y will be rho sin phi, because this time, right, this is not a circle, this is a surface, this is a disk, right, this is a disk. So your rho is varying from 0 to 1 and your phi will vary from 0 to 2 pi, and your dx dy will get converted into rho d phi. So this integration, double integration, this is simple double integration, right? This will be 2 rho cos phi plus rho sin phi. This will become rho square cos phi plus rho square sin phi d rho d phi. Rho is going from 0 to 1 and this is going from 0 to 2 pi. Okay, so anyways there is cos phi and sin phi. Okay, so this will be 0. Okay, this will be 0, like integration of 0. So you are doing this much hard work to finally get a 0 answer. So yeah, this happens sometimes. So answer will be 0. So like you saw, right, how many things we used in this like things. If your concept of curl is not good, you will not be able to do. If your concept of curve tracing is not good, you will not be able to understand which surface is this talking about. You will be confused with that itself. Then your concept of these things, right, projection method should be good. Then your concept of what, double integration should be good. So many things are getting used over here. So if your fundamentals are not cleared, you will not be able to solve these types of question, and this question will differentiate the rank. Okay, just be noteful of that. So let's solve another question. We have to evaluate f dot del of this where c is the square cut along the from the first quadrant of line x equals to 1, y equals to 1 in positive sense. So c is a square, right, in 2D plane. So this is like a 2D plane only, so we can use Green's theorem. We don't need to use Stokes always. So we can use GT. So what is GT? Basically this is polynomial, this is continuous, this is in 2D. So we can use GT, right? We can use GT. So let me just first draw the curve first. This is x, this is y, and they are talking about x equals to 1 and y equals to 1. So it will be simply like this, right? Square C is a square cut from the first quadrant. So this is the first quadrant, okay, and C is cut from here. So x equals to 1 and y equals to 1. This is not looking like a square though, so I will try to make it look like a square. Yeah, this is more like a square, and my curve is like this in the positive sense. So this will be in the anti-clockwise direction. This, and this. Okay, this is 1 comma 0. This is 1 comma 1. This is 0 comma 1. Okay, so like you can use the Green's theorem. So Green's theorem, you just, this is my curve, okay, and my surface is this. So this will be converted into double integration. First I will differentiate with respect to x, this will be y, minus differentiate with respect to y, this will become plus 2y dx dy. Okay, so this will be y dx dy. So I can take a strip, right? You just take a strip, okay, and you just compute this. So this will be like this is a square region, so this will go from 0 to 1, this will go from 0 to 1, both of them. So this will be 3 by 2, 1 minus 0 into 1 square minus 0. So this will be 3 by 2 itself. Okay, so answer will be 3 by 2. Now you can use Stokes also. It doesn't matter, you can use Stokes also. If you use Stokes, method 2 is Stokes theorem. You find del cross f, okay, and integrate this with ds. So what you'll observe is, whatever you get right, you will get this function only, right? This function, you will get this, you will come to this point. So basically Stokes theorem is basically a generalized version of Green's theorem. Okay, so I will just prove it in the next slides. So if you differentiate this, right, you will see that you are getting the same thing only. You are getting 3y over here. Okay, and like what is ds? Ds will be what? This is in the anti-clockwise direction. So direction of ds will be outwards. Let me take a different color. Outwards, which is in the positive k direction, right? So this will be k cap. So if I just compute that, this will come as 3y k cap. Okay, and this will be k cap dot dx dy. So you will get your answer as 3y dx dy, which is simply equals to 3 by 2. Same answer. Or what else? You don't want to use anything, right? You don't want to use anything. What you could have done is you could have broken it down into 4 curves, right? 4 open curves. So you could have written this as C1, C2, C3, C4. Here my dy is 0, okay, and y is also 0. Dx is non-zero, okay, dx is non-zero. Here my dx is 0 and x is 1. Here my again dy is 0 and y is 1. Here my dx is 0 and x is also 0. So if you just compute this into 4 terms, right, so your closed curve, like we have done this multiple times before, f dot dl will be divided into 4 paths, right? 4 open curves. Okay, so these also you can solve. So like let's come to this point, right? Basically Green's theorem as a special case of Stokes theorem. So here if I have a function, right, vector function mxyz, nxyz and pxyz, 3-dimensional. Now if this for some reason becomes just as a function of x and y, as a 2D function, so 2D function, so I am eliminating z, so my f I can write I cap plus n xy j cap. Okay, so then what we can do, then basically if I take the del cross f, right, so I want to compute the closed line integration. So I will compute the del cross f using the Stokes theorem, because Stokes theorem is anyways valid, right, for 2D as well as 3D. So it will be valid for 2D. So if I compute this, basically this will be I j k cap, this will be del x, del y and del z, and this will be what, this will be m here, this will be n here, and this will be 0, right, because it is not a, like, there is no z over here. So what I will do, I will just take this on the right hand side, just to the size. So this, if we compute this, like, this will be 0, again this will be 0 because there is no z over here. If I compute with respect to this is 0 anyways, and this is again 0. Now if I compute with respect to this will be del n by del x, this will be del m by del y. So this is del n by del x minus del m by del y, and all this, right, I have assumed in positive sense, okay, positive sense, in anti-clockwise direction. So here if I have a curve, okay, if I am computing the Stokes, like if I am applying the Stokes theorem in positive sense, then I can write the closed line integral of this m dx plus n dy will be a open surface integral of del n del x minus del m del y of dx dy. So this is the, like, proof, right, small proof of Stokes theorem. So I hope you understood this. Now if it is in the anti-clockwise direction, like this, right, here dx dy will be with respect to k cap, and this also has come up with respect to what, oh, I forgot to write the k cap also. Here there will be k cap also, this will come as k cap. So this will be, simply if I just write this, if I just copy this, delete the k caps, this will be my Green's theorem basically. Okay, this will be my Green's theorem. So this is the proof basically of this surface S. Okay, so this is surface. Okay, so this is about the Green's theorem proof basically. I hope you got the intuition why Green's theorem is basically a, like, minimized version of Stokes theorem. Okay, so generally we talk in 2D only, that's why we apply with 2D, like we apply Green's theorem. Now few key points, right, if I have r dot dr, that integration, closed line integration, will be 0 of any, like, if it is a conservative path, right, r is a conservative path. Why? Because what is your del cross r? It is what? It is 0. Why? Because, like, the fx is only function of x, fy is only function of y, fz is only function of z, so it will be irrotational. So this is 0 vector, and if this is 0, obviously the integration will be 0 by Stokes theorem, right, by Stokes theorem. Again, the del phi dot dr will be 0. Why? Because if I do del cross del phi, it will be again a 0 vector, right, it will be 0. Why is it the case? You can simply use this, del is outside, this will be del phi minus del square phi. This will be simply del square phi minus del square phi, which is 0, right? So this I can reduce the size. Okay, so this will be 0. Now like that's why this is 0. Now like what is the main point? Main point is if f is irrotational, obviously f is irrotational, then f dot dr will be 0, and if f dot dr is 0, then this is a conservative field. So I told you in the first lecture that what is a conservative field, where del cross f is 0, right? So it comes from the Stokes theorem, and the important point is if f is irrotational, then this will be 100% true. 100% true. Okay, if f is irrotational, then 100% my field will be conservative, that is the closed line integration will be 0. But the opposite may or may not be true, right? So I will write here, if I don't have space here, so what I will do, I will just keep this outside and keep this inside. Okay, we'll just change the directions. Fine. What I will do, this I will, okay, I will write this again. Sorry. So this, right, this is 100% true, but the opposite, converse, right, I will write here may or may not be true. Okay, so why is this the case? If f is conservative, the del cross f can be irrotational also, then also I can get a closed line integration 0. Okay, that may also happen. Okay, it isn't necessary to. So if my del cross f, the important point is, crux of this is, if my del cross f is not like it, there can be two cases, right? One is equals to 0 and another one is not equals to 0. Okay, so if it is equals to 0, then for sure I can say, like for sure I can say that my integration of c f dot dr equals to 0. But here, right, there can be two cases that, okay, I don't have space, I have to reduce the size. Let me reduce the size. I can say, let me delete this. Where are other colors, man? I am not able to identify other colors. I'm sad. So two things can happen. This closed line integral can go to 0, or it cannot go to 0. Okay, it's not necessary to, right? Even though it is rotational, then also the closed line integral can be 0. Okay, or it cannot be equals to 0. There are two options over here. But if the curl is 0, 100% this closed line integral will be 0. 100% my field will be conservative. So if you have understood that concept, let's apply that in a question. So tell me which of the following statements is or are correct. That means this is a MSQ question. MSQ. So if vector f is conservative in nature, then f is irrotational. If vector f is conservative, then it is telling me then f will be irrotational. Can I surely say that? Not sure, right? Not sure. Why? If f is conservative, that means this integration is 0. This integration is 0 in this or this case also. Now if I track back here, what do I see? Here, right, the curl of the f can be non-zero as well. If my integration is 0, it can be non-zero as well. So if it is non-zero, then it can be irrotational. It can be rotational as well. It can be irrotational as well. It can be rotational as well. So I cannot surely say that it will be irrotational. Okay, now next let's see the next option. If vector f is irrotational in nature, then f is conservative. If vector f is irrotational in nature, then f will be conservative. Yes, 100% true, because if it is irrotational, then I have only one option, that is it has to be conservative. So this is true, so option B will be correct. Now if del cross f is not equal to 0, then f is not conservative in nature. If del cross f is not equal to 0, then f is not conservative. No, right? It can be conservative also. The integration can be 0 or non-zero also. So this is again gone. Okay, again gone. I will cross this out. Let's see the last option. If del cross f equals to 0, that is if f is irrotational, then f is conservative in nature. Basically these two options are saying the same thing only, just with different language. So yeah, this is also true. Okay, so now these were the important points. If what is the summary? Summary is, if f is irrotational, f will be conservative. This the open line integral will be independent of the path C, only will be dependent on the endpoints. Only dependent on endpoints. Okay, and the closed line integral will be 0. Closed line integral will be 0. Okay, so this is more important. These are the things that is important. Okay, so yeah, that is about conservative fields and all those things. Now we will study a different thing. So you have to evaluate this, right? Del cross f ds, and f is this over the surface of hemisphere. This is a hemisphere, and this is an open surface, right? This is an open surface. This is like a bowl, like a inverted bowl. So the surface is this, and it is above xy plane, oriented in the positive direction. So it is in this direction. So this is in the positive, oriented in the positive direction. If it is in the clockwise direction, then this will be in this direction, right? In this direction. The surface is in this direction, right? Yeah, correct. The surface is in this direction. So here, can you compute this? Like you have to compute del cross f, then you have to do the ds, right? You have to take the dot of ds and integrate this open surface. This is an open surface, right? Now this surface, first of all, is very weird. Okay, because computing this n cap vector will be very difficult for me. If I just copy this, the a n cap will be somewhat like this, right? So first obviously I have to compute del cross f. Method 1 is you compute del cross f, this, then you have to find a n cap. Okay, then you have to do the surface integration over a weight surface. Okay, you have to find ds also. Okay, so a n cap will be some weird function. What is this surface? This surface is basically f of xyz equals to x square plus y square plus z square equals to 9, right? Equals to 9. Okay, so you have to compute all these things, right, over this weight surface. Then you will be able to find your integration, which will be very complex. I am very sad. Okay, is there any other simpler way? Okay, I am very sad. Complex, right? Complex. So let's do a like a bit of observation things. So if I give you this square box, okay, and I say that I want to compute the closed line integration over this curve, right? Closed line integration. Now what I can do is I can compute many closed line integrations like this. I can take small square boxes, okay, in both anti-clockwise direction like this, and I can take, like, if I add this closed line integration, I will be able to get back this whole surface itself, which many people call as rim. Okay, so basically why is that the case? Because if you see, let me take this curve, right? This curve in the anti-clockwise direction is C1. Okay, So let me take this curve as C1. Okay, I'm first talking about this curve. That just take notice of the arrows which are in the anti-clockwise direction. Don't notice these arrows, only notice these arrows. So these are in the anti-clockwise direction. So if these are in the anti-clockwise direction, that means I have got a closed line integration. Now if I do the integration of this, then what do I see? That this arrow is in the clockwise for this particular closed line integration, and this is cancelling this arrow. Similarly, again, if I take this curve, okay, this is in the clockwise for this one, and this is cancelling this one out. Similarly for this also. So these arrows are cancelling each other out. All the internal closed line integrations are cancelling each other out. Only the external integration is left out. But why is this interesting to me? So here, what I can do, I can apply the Stokes theorem here again. So this is what, right? This is simply a closed integration. This is covering a surface, correct? Again, this is also covering a surface. This is also covering a surface. So this whole thing is covering the ring itself, and this is the surface. This is surface, right? So like I can apply the inverse Stokes theorem. So if I break this integration into many small bits and pieces, I can observe that the internal integrations doesn't matter. I'm just computing the external integration itself, which is correct, because anyways at the end I'm computing the external integration curve. Okay, but why is this useful to me? Why is this useful to me? I will explain in a bit. Okay, let me just bring a bowl, or I will just use something, because else you will not be able to understand. Let me just bring a bowl, because for this concept to make you understand this concept, to explain you this concept, I will need a bowl. Just give me 1 minute. Okay, so I have bought this bowl. I hope you can see this. I will bring this more in front of the camera. Just hold on a second. Let me first start to explain this concept. So here, I want to compute this surface integration, right? So no, I want to compute this line integration, right? Line integration of this whole thing. Okay, of this thing only, line integration. So what I can do, I can break this down into a surface integration. How? Using Stokes theorem. How? So first of all, I will compute this closed line integration of this curves, right, in between these bowls. So I can compute some line here, then some line here, and like all these lines. So the internal lines will get cancelled. Now you might say, how does the top line get cancelled? The top line, you can observe that I am computing with respect to this side and this side, right? So the top lines will also get cancelled. So like one closed integration is along this direction and another one is along this direction. Both are opposite. So obviously they are getting cancelled. As this is a 2D surface, I won't be able to show it here. But here, right, I hope you are observing. Behind I have a in the clockwise direction, and in front I have an anti-clockwise direction. So these two curves are getting cancelled. Okay. So the internal curves are getting cancelled. So at the end, I'm only computing for the rim itself. So this individual things, right, f dot dr, individual things, what can I write? What can I write this individual things? I can write this individual things as using the Stokes theorem, because this is also a closed line integral. This is also a closed line integral. So what I can write here is that my f dot dr is this only, and I can write this as what I can write. This is like, let's say this is C1, right? This is C1, this is C2, this is C3, and so on. So I can write this as what? I can convert this into Stokes theorem. This is also a closed line integration, and this like I will assume that this is differentiable. This f vector is a differentiable continuous function. Okay, so I will assume that as this is a closed line function, I can apply the Stokes theorem. This will be del cross f s1 dot ds plus double integration of s2 del cross f dot ds and dot 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 dot. Okay, so it will be somewhat like this. So you can convert it into multiple surface integrations. Okay, open surface, these are all open surface, right? But this has direction is along the same one only. Here also I can break this down into multiple surface integration. So all of this at the end will be added to a single surface. What is it? Which is a surface of this itself, right? This itself, this square itself. I don't have space sadly, so somehow I have to manage this. This will be what, dot ds vector. So I will reduce the size. Yeah. So this is dot ds vector. So like that is what exactly I've written over here. But like this, you might say that, sir, this is like a Stokes theorem only. Yes, this is Stokes theorem only, but this is in the inverse direction, that is the opposite direction. That the important point is this surface, right? This surface is not this surface, this circular surface, right? It's not this circular surface. It's this what, paraboloid. It's this paraboloid. So if I am integrating del cross f over this surface, then I will get the rim, not a this closed curve, right? Not this closed curve. This is not enclosing this, sorry, not enclosing, this is not encircling any area, right? Not encircling this rim, right? This rim is just the outside. This rim is this thing, right? This thing, rim is this thing. Is this encircling any area? Currently no, right? This is like a hollow thing, right? This is not encircling any area. So yeah, you can say that yes, this is encircling any area. I do agree with that, but I'm taking the shape of paraboloid, right? I'm taking the shape of paraboloid, so this is like a hollow volume. Okay, hollow volume. So in general cases, we use this concept for hollow volumes only. So this is like a hollow volume. Hollow volume. Okay. So this is like an inverse Stokes theorem. Okay, just hold on a second. Yeah, this is like a inverse Stokes theorem, right? So this is hollow volume. So that is the main crux. So here also, for hemisphere also, you can apply the same thing, that your like this del cross f over the whole surface will be simply the closed line integration of this rim only. Okay, closed line integration of this rim only. So like how to use this concept. So this, right, this question we'll solve using this inverse Stokes theorem. So you'll use the method 2, which is basically the Stokes theorem applied in the opposite direction. Okay, applied in the opposite direction. So if I applied it in the opposite direction, so this del cross f dot ds will be converted into a single line integration of this in the xy plane. So this will be z equals to 0 and x square plus y square equals to 9. So this thing, right, I will copy this. Can I paste this actually? No, I cannot. Copy this surface. This, okay. This thing will be converted simply into a line integration. X, Y. And in generally they are in the this anti-clockwise direction only, although it like doesn't matter that much, but this will be in the anti-clockwise direction only. Okay, as am I going in the positive z direction, right? Positive z direction, you know. So as my en cap is somewhat going outward, right? That's why. So this is the equation of circle, which is x square plus y square equals to 9. So now I can simply compute this f dot dr, right, over the closed surface, not the closed surface, sorry, over the closed line, over the closed curve. So this will be what is f? F is this, right? If they have given us this, so f dot dr, this will be x square plus y minus 4. This will be this and this will be this. Just hold on a second. So I have to copy this f also, else I will forget this. Just hold on. So somewhere I have to reduce the size again. this will be x square plus y minus 4 dx plus 3xy dy plus 2xz plus z square dz, right? So now I want to compute this over the curve. So obviously what you can do, either you can simply like change your x and y, okay, in terms of that, okay, as z is 0, right? Z is 0 here. The important point is z is 0. Z is 0. So if z is 0, so this goes to 0 and dz also is 0, right? So this one goes to drain. Only we are left with this. So method 1 is, again, you use the polar coordinates. Okay, so what do? You write your x, okay, I go on somewhere else. You write your x equals to what? This will be simply 3 cos phi, right? 3 cos phi. So you write your x as 3 cos phi and your y, this is 9 square, right? Yeah. And your y as 3 sin phi, and your phi is going from 0 to 2 pi, and then you convert everything here and you compute the integration. Okay, so let's compute the integration. So this will be 3 cos, okay, this will be square, okay, this will be square, and this will also be square, okay, 3. So you compute this, is homework for you, you compute this. Okay, this one is homework for you, else like this lecture will go again long and I don't want that to happen. Like what else can you do? What else can you do? You can apply the what? Green's theorem. Can apply the Green's theorem. Okay, so basically what he can do is, this is 2-dimensional, this is continuous, okay, and you have been given a closed line integration. So you can again apply the Green's theorem. Okay, so basically it will be integration of the surface, differentiation of this with respect to x, this will be 3y minus differentiation of this with respect to y, this will be 1, and dx dy. Okay, so here, like, what is my surface? Just hold on. This will be integration of surface 3y dy dx minus dx dy, double integration of the surface. So this is area, that is fine, but what is this? So again, right, I have to use second polar transformation, cylindrical transformations. So if I just copy this, just reduce the size. So here I am talking about this surface. So my rho is going from 0 to 3 square, 3, and my phi will go from 0 to 2 pi. So dx dy will be changed to rho d phi. So this I can write like this. Okay, this will be, so y will be rho sin phi, so rho sin phi into rho d phi over from rho going from 0 to 3, and this is 0 to 2 pi, minus what? This is simply area. So this is pi r square, which is 9 pi. Okay, so I'll just reduce this size. This will come over here, and this I can further write. This will be pi cube by 3 will get cancelled, and okay, 0 to 2 pi is anyway 0, right? 0 to 2 pi is anyway 0, so this will be 0 minus 9 pi, so this will be minus 9 pi. Now you try to compute this here, right, with this, and you try to cross check that whether you're getting 9 pi or not. Okay, so yeah, this will be basically the answer to this question. So like, let me summarize about inverse Stokes theorem. So we use Stokes theorem in the opposite direction, but the important point is the pattern will come like this. So you have to compute del cross f surface integration. So whenever you have to compute this particular thing, okay, obviously you don't do del cross f, you compute the curl, then you do the surface integration. That will be very lengthy. You use the line integration. But here the important point is here, right, this is not encircling a surface, this is not encircling the surface, right, this is a rim only. So this is the rim of the hollow volume, right, hollow volume. So rim of this hollow volume, so rim of some hollow volume, okay, some hollow volume, some hollow volume. So basically, when to apply? Whenever you see hemisphere or paraboloid or square like structures, and you have to compute this, right? These two conditions are there, then you apply inverse Stokes theorem. Okay, that is basically the crux. So let's apply this in this question. So we have to compute del cross f dot ds of this vector, and the surface is this, right? Surface C is circle in xy plane bounding S as a surface. This, right? This is what? This is again a hemisphere in the xy plane. So xy plane is this is the surface, right? So this is simply like a hemisphere. So z is always positive. From here you can understand this is under root, so z will always be greater than 0. This is under root, and the output of square root function is always greater than 0. So z has to be greater than 0, and z has to follow this particular thing. Okay, so basically it can be greater than or equals to 0. So it is like a hemisphere itself. It is z square plus x square plus y square equals to 1, and z has to be greater than 0. So I am above the xy plane. So this thing equation has given us two information. So you have to be very good in curve tracing. Okay, so if I compute this further, this will be x square plus y square plus z square equals to 1, which is simply equation of sphere. But as my z is greater than 0 or equals to 0, so I will only have half of a sphere, which is hemisphere. Okay, so like you have to compute this del cross f along this surface, right, along this surface, like, which is very hectic for me. So you have to compute along this surface. Along this surface they have given you. So what we have done, we have computed along this surface only. I've shown you the along this surface. If I compute all of this surface integration, that will be just the closed line integral of this rim, right? So I will just write this as this thing along the surface del cross f dot ds will be converted into simply a closed line integration of f dot dr along the curve, not C, along the rim. Very important, along the rim dot dl. Okay, so what is this? What is this surface? This surface is simply x square plus y square, where z is 0, so that will be x square plus y square equals to 1. So if I just use this surface, to 1. So like, yeah, you can simply compute this. This will be, again, z will be 0, so this has gone. This is again, so in some 2D plane you can use the Green's theorem, or you can simply solve it. So your f dot dl will become, z is 0, right? Z is 0, so f dot dl will become y dot dx only, because dz is also 0, right? Dz is also 0 and z is also 0. Okay, so this closed integration I have to follow, and what is y? You can like use the polar transformation again, right? So like y is simply sine phi, okay, and what is dx? Dx will be minus sine phi, okay. So dx will be minus sine phi. Just hold on, is this okay? Sorry, this is not y, this is x. I'm sorry, this is x. Okay, I mean some different. This is x y. I meant x dy. So like y will be sine phi, x will be cos phi, dx will be minus sine phi, and dy will be cos phi. Sorry, this is d phi also. D phi, right? So I will just reduce this also. So x will be cos phi, this will be cos phi d phi from 0 to 2 pi. Phi is going from 0 to 2 pi, right? So this is again 4 times pi by 2 cos square phi d phi. This will be equals to this is again even, right? Both are even, so pi by 2 will come obviously into this will be 1 divided by 2, and obviously I have here 4, so this will be pi, okay. So pi will be your answer. Or what you could have done, you could have applied Green's theorem also, because this is just a like this is also a 2D plane, right? This is also a 2D plane. So like this is method 1. Method 2 is GT, our savior, okay. So if GT is our savior, what do you do? So you have to compute x dy, right? So this is a closed surface, closed curve integration, closed line integration. This you can write like this: c 0 dx plus x dy, okay. So now you can convert it into a open surface. So this I will differentiate with respect to x minus 0 dx dy. So integration of dx dy. So what is the area of this surface? Area of this surface is simply pi r square, which is pi into 1 square, which is simply pi. So pi will be answer. You can cross verify from this, okay. So yeah, this is how you solve using inverse Stokes theorem. So whatever you have listening to me, so you just, if you are not able to understand, you have to quickly recap, right? You have to revise again these things, because I have explained this in every step in detail, right? You have to go revise and rewatch the lecture again if you are not able to understand this concept. So that was it for the inverse Stokes theorem. And now we'll understand a basic point about differential coefficients. So if you have been given a curve like this, okay, and you have to evaluate between this path, right? You have to evaluate between this path, okay. This is not a closed line integration, not a closed line integration. So this is not closed, so no GT for us. I am set. Okay, no GT. So that so obviously we won't be able to apply the Gauss theorem, so we have to solve it simply only, right? Simple only. So I cannot obviously check for conserved net intensity also. So if I compute the curl of this, what is the curl of this? Is the curl 0 or non-zero? If I just compute the curl, like, because they have asked us to find the integration between a weird path, which is very difficult for me to compute. So if I compute del cross f, what do I see? I see, I have to write this again, right? That is a pain for me. Del x, del y, del z. This will be x component, which is okay. What is x component here? Which is y, right? And y component is, so like your f, first of all your f vector is yi cap plus x j cap. That's why the j cap component came with dy and I cap component came with dx. So this will be y and x, and this is 0. So if I compute this, right, this will be, if I cover this up, this will be 1, this will be 1, and this will go to 0, right? So it is 0, so obviously it is a conservative field. Conservative field, okay? So if it is a conservative field, that means whichever path I choose, it doesn't matter. Whichever path I choose, it doesn't matter. So if I have chosen this straight line, it wouldn't have matter, right? From here to here, instead of going from here to here in cross couple path. So if I choose straight line, this will be what? This will be simply like x is going from 0 to 1 and y is going from 0 to 1. So this equation of, what is the equation of curve? It will be anything, right? This equation of curve will be anything, and if you compute this, okay, the result will come out to be something like this. So you write y equals to mx, just hold on, y, what I can write, just I can satisfy it. Basically I am writing, right, y minus y2 minus y1 x2 minus x1 will be equals to m, which if I multiply this with x, okay, if I just multiply this with x, this will not be equals to y, because I have to add the y intercept as well. So this I can write it like this. I'm just thinking, what can I do if I want to write the y intercept? Okay, if I just put this point y1 x1, so I will be able to get c, right? So plus c, and if I just put y1 x1, c will be equals to y1 minus y2 minus x1. Okay, this is my c. So now if you just like replace this, right, over there, if you just replace this, what will happen is that, like what do you have to compute? You have to compute y dx, right? So basically my dy will be equals to m dx, and m is equals to this, right, the slope basically. So m is equals to y2 minus y1 divided by x2 minus x1. So now if I compute this integration of y dx, so I have to compute y dx, so y will be mx plus c dx, and my dy is m dx, and this is x m dx. So, and x is going from x1 to x2, x1 to x2. So this I can compute. You can watch it in 2x, okay, if you want to calculate it yourself. So this will be mx square by 2 m x square by 2 and plus cx plus, this is plus or minus, this is plus only, this is plus, so this will be again m x square by 2 it is going from x1 to x2. So if you compute this, right, if you compute this, what you will get? You will get x2 y2 minus x1 y1, okay, and you will get this beautiful result. So why is this? Why am I getting so beautiful result? Because what I could have done, I could have written this function, right? What I have to compute? I have to compute this, right? To compute this I could have simply written like this, like x dy plus y dx. Can I write it like this? D of xy. Can I write it like this? The short answer is yes, because this is a conservative field. So this is also known as a differential coefficient. So first I will differentiate with respect to x. I will keep y in the outside, chain rule. Then I will differentiate with respect to y, and I will keep x outside. So y dx plus x dy. So this is x1 y1 to x2 y2. Okay, so like you will get the same answer, x2 y2 minus x1 y1. Okay, so it is independent of path obviously, and you can write it like this. So every conservative field, right, every conservative field can be written as a gradient of a scalar point function, basically in terms of differential coefficients. So d of xy can be written like this, d of y upon x can be written like this, d of x upon y can be written like this. Here what I have done, I have just simply applied the quotient rule, differentiate with respect to x. Okay, like this will be what, x square, the denominator square, x dy. Okay, first then I will keep this outside and I will differentiate this, the numerator, and then I will do a subtraction. I will keep the numerator and then I will differentiate the denominator. The same thing I have applied here. Okay, so let's just do an example over here. So here I have to evaluate f dot dr. So what you can do, you can simply use parametrics. So method 1, simply use parametrics, right? Convert all of this into a single function. What do you have to compute? You have to compute f dot dr over this open curve. So obviously I won't be able to apply any theorems. So you will write 2xyz integration dx plus x squared z square dy plus x square y dz. Okay, so this you have to compute. So like this is very difficult, right? 3 different variables, all these things. So what you can do, you can compute everything into a single variable only, right? Y minus 0, 1 minus 0. So I hope you are pro at this right now. Z minus 0 and 1 minus 0 equals to t. Then you write this, then you compute f dot dr, you will get your answer. Okay, and what is the method 2? Method 2 is like, this is your homework, right? This you have to compute. You have to do this hard work, else you will not get a good rank. Trust me, मेरा कसम है, good rank अच्छा rank नहीं आएगा अगर solve नहीं करोगे तो. So method, what is method 2? Method 2 is you can use that differential coefficient concept. So like how to use that concept? So like how to identify that? What you can observe here is that if I write it in terms of f dot dr, right? If I write it in terms of f dot dr here, I will write it in terms of a single integration only. Okay, not 2 integrations, single integration only. This will be dz. This is plus, this is plus. What am I observing is, if I take like this function here, right, I have differentiation of x square. Here, right, I have differentiation of y. Y is not here, y is not present. That is, I have differentiated y. Here, right, I have these two. Okay, x square is present in these two, but here the differentiation is present. So x square is present here and here, but the differentiation of x square is present in the third one. Okay, then again z is present here, z is present here, but the differentiation of z is present over here. Similarly, y is present over here, but the differentiation of y is present. So obviously my differential coefficient will be what, the common of this, or like the union of these three. It will be d of x square, y will also be there, and z will also be there. You just differentiate this, right? You will see you are getting this only. And how am I moving? I'm moving from 0, 0, 0 to 1, 1, 1. So this will be simply 1 square into 1 into 1, because that will be 0 only. So this will be 1 itself. You will see, you will cross verify, you will get your answer as 1. Okay, that is how you solve. So here also, if you want to solve this, like you can observe, right? You can observe, if I do f dot dr, okay, I'm not even seeing the question. I'm doing f dot dr of the open curve, this will be y square plus 2x. Whenever the curve is given weird or something, you just try to check for conservativeness, and if it is conservative, then you will be simply able to convert this into differential coefficients and your solution will be very easy. Plus 2xy plus x square dy. Okay, so you have dy here also, that is differentiation of y, differentiation of x, and differentiation of z, right? All these things you have. Okay, so you are applying the chain rule only. You have differentiation of x, so you have differentiated with respect to x. So this will be what? If I differentiate this with respect to x, I will get 2x. Okay, and okay, this I will get 2x, and this will be y. Just hold on. So this will be 2x and y. Just hold on, rain is coming.
Yeah, sorry for the interruption. Actually, rain came over and I had to pick up the clothes because those were drying up outside. So here the important point is I have x square over here, and I have the differentiation of it, and I have y with it, right? So differentiation of x square is 2x, and I have y, so y should be present, and I have y square over here, and I have the differentiation of this y, and dy is also present, and I have 2 here, right? 2y and x is square. So x will be with y square and y will be with x square. So this I can write like this: d of x square y plus y square x. Can I write it like this? Just check. If I differentiate this first term, it will be 2x into dx, and y is anyways constant, that will be outside. And if I differentiate this term, it will be 2y. Okay, just hold on. If I differentiate this, right, with respect to x, whole thing with respect to x, this will be what? 2x y dx plus, and differentiating with respect to x, this will be y square, and obviously dx is there. And if I differentiate this with respect to y, the same thing, just in this will be x square instead of y square. So yes, we are getting the same thing only, right? As I told you, that's how you back calculate. So you see, here I have x square, here I have x square, and this is the differentiation of this. Okay, and obviously y is present with it, so y will be present with x square. Okay, y will be present with x square, and here I have y square, and I can see I have 2y present over here, differentiation of y, and obviously I have dy present over here, and this is dx, right? So this is how you identify. So obviously this is a conservative field, and how is it moving? My x is going from 3, 0 to 0, 3. Okay, so this will be, so here either one of them is 0 on both limits, so the answer will be 0. Okay, the answer will be simply 0. So that was hard work. So like you can check for the conservativeness whenever you are doing these kind of things, right? You always check for conservativeness. But even if you are able to convert this in differential coefficients, that means it is conservative. Okay, so let's come to the last theorem, that is the Gauss's divergence theorem. So what is the Gauss divergence theorem? So the Gauss divergence theorem gives the relation between closed surface integral and volume integral. So it gives the relation between closed surface integral and volume integral. It is applicable only for closed surface having volume integral, right? It is applicable only for closed surface having volume integral. So it is applicable only for closed surface, okay, where I am able to enclose a volume, and it gives the relationship between the closed surface integral and volume integral. And the important point is it is only valid for continuous and differentiable in volume V. So it has to be continuous and differentiable in volume V. And obviously dV is a scalar, right? dV is a scalar, so this thing also has to be a scalar. And which operator with del gives me scalar? It is the what? Divergence operator, right? Divergence operator. That's why we take the divergence. Okay, this is how you remember. This is a scalar. So obviously this also has to be a scalar, right? This also has to be a scalar. There is no dot over here. There is no dot. Okay.
So like the important points, same thing. Obviously, if it has to be continuous and differentiable in volume V, then only you will be able to apply. And obviously, it has to be a closed surface, right? If it is closed surface, it will enclose a volume V, and you can convert. And what is dV? dV is simply dx, dy, dz. Okay, it doesn't have any direction, but n cap is basically the direction of the ds, right? This will be ds bar a n cap. So a n cap is the direction. A n cap, n cap, all these things are same only. So let's solve few questions. So this is a GATE 2017 question. So here I have to compute the surface integral f dot n ds over the surface S of the sphere x square plus y square plus z square equals to 9. Okay, of this. So I have to compute the surface integral over a sphere. So sphere is a closed surface, right? Closed surface. Surface. So, and this is a polynomial. This is a polynomial. Polynomial. So with your eyes closed, use the Gauss divergence theorem. So this f dot n ds over a closed surface will get converted into del dot v. So what is del dot v? This will be 1 plus 0 plus 1. This will be 2. Okay, and this will be dv. So or dx, dy, dz, whatever you want to write. So simply this will be 2 times v, which is the volume of the sphere, which is 2 times 4 pi by 3 r cube. R cube. So r is 3. 3 square is 9. So r is 3. It will be 3 cube. So it will be simply 9 times 436 times 272 pi. Okay. So this will be your answer. This will be your answer. Like I have been given another question. So I have to compute this over surface, over a surface x dy dz, y dx dz, and z dx dy. Okay. And surface of cylinder x square plus z square equals to 4. So like what is this? This is like in the direction like what is f? So like this is written like this, that f dot ds equals to this thing, right? F dot ds equals to this thing. So they have given me the f dot ds this time, and it is a surface of cylinder, and all these are polynomial, and it is a surface of cylinder from y equals to 0 to 1. So it is a closed surface, cylinder, closed surface. So closed surface. So obviously I can write my f. What will be my f equals to? F equals to x dot I, because dy dz will be in the I cap direction, plus y dot j plus z dot k, right? Zk, and it is as it is in the closed like closed surface. So like even though I don't need to draw the surface, you can do it by yourself, but let's still draw it. X y, and this is what? X square plus z square equals to 4. So this will be a circle of radius 2 in the xz plane, and I am going from y equals to 0 to y equals to 0 to y equals to 1. Okay, so this will be y equals to 0 to y equals to 1 cylinder. So even though this is not that accurate, but still just take my word that this is the cylinder itself. So this is a closed surface, right? So like what I can do, I can take the divergence of this. This will be what? 3, because it's just a r vector. So 3 integration along the volume dv. So this will be 3 times v. So which is simply 3 times the volume of this. What is the volume of this? Pi r square, which is, okay, this is not 1, this is actually 4. Pi r square. So pi r square, h is 1. Okay, y from y equals to 0 to y equals to 1. So this will be 12 pi. Okay, so 12 pi will be your answer. So like the divergence question, right, are very simple. Okay, Gauss divergence theorem is very simple. Okay, you should be happy if some question came from Gauss divergence theorem. So again, right, this question, so you have to compute this del cross f dot ds along the surface of a sphere. This is a closed surface and you have to compute del cross f dot ds. So what you can do, either you can do del cross f, then you can compute the surface integration, or you can use a divergence theorem. So if you use a divergence theorem, so what you have to do, you have to find the triple integration along the volume of the sphere of del dot del cross f. Now do we know a property? Do we know a property? The property is basically this will be 0. This will be 0, right? I have already told you just I think in like before 10-15 minutes, right? This will be 0. So like answer will be 0. This is the answer. So here I've written this as key points. So position vector, if you have given position vector x I cap y j cap, then obviously it will be 3v. The answer will be 3v because your del dot r equals to 3 and your del dot del cross f equals to 0. Simply you will take the dot with this, then you will take the dot with this, right? Simply what will happen, this will be del dot f of this minus del square of f. This will be del square of f itself, so del square of f, so this will be 0. Okay, I'll just reduce the size. Okay, that is how you solve. Okay, so let's solve this question. Now this question, right, this question is very interesting. They have given totally like a paragraph which is like pretty daunting to me. So they have given a vector field is defined like this. Okay, keep this in mind, this is rational, so we have to be careful now. Rational function, rational, so I should be worried, right? I should be worried. I have been given rational function. So I, j, k are unit vectors along axis of right-handed rectangular Cartesian coordinate system. The surface integral of this. Okay, I have to compute the surface integral of this. Okay, why ds is an elementary surface area vector, which you already know. They are giving us information which you already know. Okay, evaluated over the inner and outer surfaces of spherical shell formed by two concentric spheres. So this is a gate question. I have forgotten which year gate question is this. This is a gate question. Okay, I will write the question here later on. Over the inner and outer surfaces of a spherical shell formed by two concentric spheres with origin as center and internal and external radii as 1 and 2. So basically, if I draw the region, sorry for the noise due to train, x, y. So I have a sphere here, okay, of radii 1, then I have a sphere here of radii 2. Okay, sphere of radii 1. So this equation will be x square plus y square plus z square equals to 1, and this equation is x square plus y square plus z square equals to 4, right? 2 square. So obviously they are talking about the volume. So this is the volume, right? This is the volume. They're talking about the volume of this. Okay, so let me just use some different color. This is not that prominent. They're talking about the volume of this shell region, right? This is shell. Okay, now obviously 0, 0 is not included, and my function is discontinuous at 0, 0 only. So I can say my closed surface is continuous, not closed surface, sorry, my f vector, right, field vector is continuous over the given closed surface. So I can use the Gauss divergence theorem. Now, can you say to me what is this written over here? What is this written? If you observe this carefully, this is xi cap plus yj cap plus zk cap. Denominator is same. So the numerator is what? Numerator is r vector. What is the denominator? So I have square root also, but I have raised to power 3 also. So x square plus y square plus z square whole under root is r, but it is raised to power 3 also. This will be r cube also. Okay, this will be r cube also. So what I have to do? So my f vector is like this. So I want to compute this f s over this closed surface, because this is a closed surface, right? Spherical shell, this is a closed surface. Okay, because this is enclosing a volume. Okay, hollow volume, not a hollow volume, sorry, yeah, hollow volume basically. So now I have to compute this, right? So what I can write? I can write this as del dot f dv. So let me compute the divergence of this. So if I write this here, right? So this one I will write like xi cap only. So f vector I can write xi cap plus yj cap plus zk cap upon r cube. So now if I compute the divergence, so obviously I have to take the differentiation of this, right? So if I take the differentiation of this, what will happen? What will happen? This numerator will be whole squared. So now I want to compute del f upon del x. So it will be so I want to compute not del f upon del x, it will be del f upon del fx, right? Fx is this. So I just want to compute the x component. So the denominator will go r raised to power 6. Okay, because the denominator gets squared. Next I will first differentiate the numerator. Okay, this will be only 1 into r cube minus then differentiation of the this denominator. So what is it? So it is under root x square plus y square plus z square. If I differentiate this with respect to x, it will be 1 by 2 into like what it will be 1 by 2 r, right? 1 by 2 r. Okay, so let me just show for one, then I will explain. So what I am differentiating, I am differentiating this, right? X square plus y square plus z square 1 by this, yeah, on 3 by 2, right? 3 by 2, because this is, yeah, this is 3 by 2. So r is x square plus y square plus z square 1 by 2 raised to the 1 by 2, basically under root x square plus y square plus z square. Now if I differentiate this with respect to x, right? Okay, even if you like partial differentiation, right? Differentiate this with respect to x, this will be like 3 by 2 will come in front times x square plus y square plus z square 3 by 2 minus 1, which is 1 by 2, and then the inside function, then the chain rule comes up, right? This will be 2x. So this 2 will get cancelled, and I will have x times what is this? What is this? This is r, right? R is this. R is this. So this will be x3 will be still remain, and this will be 3xr. Okay, so I will just write it like this. This will be 3xr. So I hope you understood this point. This will be 3xr, and anyways I have also this x from the numerator. Like, I hope you know what quotient rule is. I'm just simply applying the quotient rule. So you just compute for yourself. You will be able to find this one out, right? Then if I write f del fy upon del y, okay, this will be the same thing only. 1 then r cube minus, here instead of x there will be 3y square r divided by r raised to power 6, and similarly my del f upon del z will also be same, right? Del f z upon del z equals to r cube minus 3 z square r divided by r raised to power 6. Now what is the divergence? Divergence is basically the summation of all these three, right? So if I add these three, what I will get, so del dot f vector will just be the summation of this. So here I will have 3r cube minus, I can take minus 3 common, okay, and this will be x square plus, okay, this, what is this? Just hold on a second. Also r is there, right? R is also there. Plus z square. Now can you tell me what is this? Like, let me just write here, right? What is r, else students will get confused. R is what? R is x square plus y square plus z square raised to power 1 by 2, right? That is what I have defined my r. Basically raised to power 1 by 2 is my r. That's why I have written r cube over here. So this is what? This is r square. So this is r square, and in the bottom I have r raised to power 6. So this will go to 0, right? This will be r square 3r cube minus 3r into r square divided by r raised to power 6. So this will be 0. So del dot f will be 0. So our this surface integration, right, this will be simply 0. Okay, so I will put a question mark over here and I will copy this. Answer will be 0. So like this complicated question and the answer is simple 0. So sometimes they frighten you with this type of question, right? These type of words, 50% things you already know, they only just mentioned for frightening you, making the question much more longer, so that you read the question for more longer and you get frightened. Like the answer was simple 0. Okay, I hope you got the point how to do this differentiation. If you didn't got the point, you just write this r in terms of x square plus y square plus z square, then you do the differentiation. But it is very important to differentiate it like this, because this will save you time. So that's why I solve it like this. So let's go to the next question. Now the next question is f dot ds. I have to compute f dot ds over a surface. To compute f dot ds over a surface, okay, where f is this vector surface enclosing the volume bounded by x equal to 0, y equal to 0, z equals 0, and x plus y equals to 3. So this is again like a triangular region, right? So and this is what this is, like this is yz plane, xz plane, and xy plane. So first of all, let me plot this. This is a triangular region. If z is 0, then x plus y equals to 3. So x plus y equals to 3. So line will be somewhat like this. Okay, and then if x is 0, not x is 0, yeah, if x is 0, then z plus y equals to 3, and if y is 0, x plus z equals to 3. So these three equations I get, and I can plot it here, right? So somewhere in between, all of them are non-zero. All of them are non-zero. So I got this region. Also I have this region, right? X equals to 0 region. This not x equal to 0, sorry, this is z equals to 0 region, and like this is the xy plane. Now when my x is 0, then I get the zy plane. So this will be z equals to 0 region, and this will be my y equals to 0 region. Okay, so let me color this differently so that you will be able to understand this. Running out of colors. This is z equals to 0, x equals to 0, and y equals to 0. Okay, so these three are the cases. So now if you want to solve it, so this is like a triangular region, and here these are also triangular, right? So this is like a like not a cuboid but triangular cuboid, like that. So we have to compute the surface integration, and this is a closed surface. If this is a closed surface, then I can do the volume integration. So I can write from from Gauss's divergence theorem, that closed surface integration of f dot ds equals to volume integration of del dot v dv. This will be simply v, this will be 4x minus 2x, and we have dx, dy, dz. Now I observe here, like here x is present. So if I like along which plane I should take the projection. So what do I want? I want to do minimal effort with x. So what I will do, I will keep this x here, right? I will try to integrate x at the last step. If I want to integrate x at the last step, then I need to have dy dz over here, right? Now along which direction I should take the projection. So basically what I want to eliminate is, like, x is here, right? X is with this dx, so I don't want to solve for x. I want to solve for x here, right, at the outside integral, okay, at the outermost integral. So what I will do, either I will take the projection about the y-axis or about the z-axis, so that I can take the strip along z or y, okay, so that I can write the limits of z or y. So what I will do, I will just copy this thing, okay, we'll delete this. So in generally what we do, we take the strip along the z direction. So if I just take the sun along the z direction, then what will I get? Basically I will get this triangle. So this triangle, can you tell me the what is the equation of this triangle? Can you tell me that? The equation of this triangle, I told you at the start of the question, but it will be x plus y equals to 3. Okay, so obviously I will take a strip over here, vertical strip, but now do listen to me carefully. I have a shape over here also. If you are not able to identify, this is a 3D shape also. So obviously my z will touch at z equals to 0 plane, and then will touch this shape, right? Then will touch this shape. So it will touch here z equals to 0, this strip along the z direction, and it will touch this surface, right? This surface. So if it is touching this surface here, what is the equation of z? This z equals to 0. Here what is the equation? Equation is x plus y plus z equals to 3. So this will be z equals to 3 minus x plus y. So very important to note here. Obviously we now I can take, I want to write my limits with respect to y, because I want to solve for x later on. So I will write this. Again I will take a vertical strip. This will be y equals to 0 to y equals to 3 minus x, and my x is going from x equals to 0 to x equals to 3. So I hope all these things you are expert at, so I don't need to explain this much further. So this will be what? So this will be 0 to 3, 0 to 3 minus x, 0 to 3 minus x plus y, and here I have 2x. So 2x can come directly, 2 can come outside, and x come directly come here, and this will be dz, dy and dx. So this will be 2, 0 to 3, x, 0 to 3 minus x, 3 minus x plus y. So this will be 3 minus x minus y dy dx. So this will be 2, 3 x, and this will be 3 into basically 3 into 3 minus x, right? So this will be 3 into 3 minus x, and this will be minus x into 3 minus x. this will be y square by 2, right? Y square by 2, integration of this will be y square by 2, which will be minus 3x square by 2. Okay, so this outside 2 is there, 0 to 3. So like let me write this overall. This will be 9 minus 3x minus 3x plus x square, and if I write this, right, this will be minus 9 by 2 minus x square by 2, and this is minus 2 into 3 into x. 2 will get cancelled. This will be minus plus 3 times x and dx. So this 3x and this 3x will get cancelled. I will have this 3x present over here, and this will be 9 by 2, and x square is anyways there. So 2. So what I can do, I can take this 2 inside also, but that's fine. So this x into 9 by 2 minus 3x, and this will be plus x square by 2 dx. I can take the 2 inside just to make things more neat and clean. This will be 9x minus 6x square plus x square dx. So this will be 9 by 2 into 3 square minus 2 into, okay, this is also I had x square, right? So this will be minus 5x square itself minus 5 by 3 into 3 cube. So this will be equals to 81 by 2 minus 27 into 5 into 27, just 135. Also, okay, 3 is getting cancelled, right? Okay, 3 is getting cancelled, so this will 3 squared. So 5 times 9 is 45. So this will be minus 9 by 2. Okay, so this will be the answer to this question, is minus 9 by 2, so minus 4.5 basically. So this will be the answer to this question, minus 4.5. okay, so let's go to the next question. So next question is, we have been given a like we have to compute the surface integration again. Okay, surface integration again of this vector along the volume enclosing a x square plus y square plus z square equals to 1 and z greater than equals to 0 plane. Basically it is talking about the hemisphere, right? Hemisphere. So like we can't use inverse Stokes because this is not like a single line integration, right? This is not like del cross f or something like that. This is not del cross f, right? Not del cross f. This is simple f. So we have to use our divergence theorem only, Gauss's divergence theorem only. So the surface is what? Surface is basically hemisphere. Surface is hemisphere. Okay, this is z greater than 0 plane. Okay, so again what I can do, I can write this double integration as f dot ds equals to triple integration del dot f, right, dv. So what is del dot f? It is this is 0, this is 0, this is 0, and this is not 0. Okay, this is not 0. I was expecting this also to be 0, would have been so much more easier. So now this is 2 zy square dx dy dz. Okay, now along the hemisphere, right, along the hemisphere. So now this is a what I can do, I can take this vertical strip again and compute. But if I take this strip, right, if I use the projection method, the difficult thing will be that the equation of this line will be very like difficult, right? It will be complex, under root square root under root that thing, so which will become very complex. So what I will do, I will take the polar transformations, I will take the spherical transformations. So what I will do, I will write my x as r sin theta cos phi, y as r sin theta sin phi, z as r cos theta. Okay, and my I can write my dx, dy and dz as r square sin phi dr d theta, so dr d theta d phi. Okay, so yeah, all these things I can do. And like if I take the surface, right, if I take the surface, basically what are the ranges? Ranges is r is going from 0 to what, 1. R is going from 0 to 1. My theta is going from 0 to pi by 2, 0 to pi by 2. My phi is going from rotating holes, right, 0 to 2 pi. So range of r will be 0 to 1, 0 to pi by 2, 0 to 2 pi. Okay, so if I compute, if I exchange this, right, this will be 2z, like this will be very difficult, so just be with me right now. This will be 2z, so this will be 2 times r cos theta. Like everything will be independent now, all the limits will be independent. That's a good thing, right? 0 to 1, 0 to pi by 2, 0 to 2 pi. Y square is, again, it's like scary thing, r sin theta sin phi. Don't get scared, just move forward. Okay, just move forward. This is r square sin sin phi, right? R square sin phi, and this will be dr d theta d phi. So this, like, now let me just write this, and like this will become separable, right? Separable format. So this will be very easy for us to compute the integration. Let me just write it in proper format. So 2 will be outside, 2 will be here. Okay, and here r is there, r square, then r square, so total r raised to power 5 I have. This is the first thing. Next, here I have cos theta, here I have sin theta, and yeah, that's pretty much it. So this will be cos theta into sin square theta. Next, this is sin square phi, and here I also have sin phi. So this will be okay, have I made a mistake? Yeah, actually, just I also forgot the formula sometimes. This is sin theta, right? I just gone through my notes. This will be sin theta. Sometimes I also tend to forget the formulas. So this will be sin theta. So this will get converted into cube. So that's why you should remember the formulas daily. That is the more important part. Okay, revision is the most important part. So this is sin cube theta, and this is sin square phi. Okay, and we have dr d theta d phi. So now I can compute them separately. So I can compute 0 to 1 r raised to power 5 dr. I can compute 0 to pi by 2 sin this is what? This is simply cos theta into sin cube theta. So this I can compute, right? Okay, this I can compute with the Wallis formula. 1 is odd, so this will, anyways, 1 will come, k will be 1, and another formula I will write. And this is 0 to 2 pi sin square phi. So I can write this as, again I can write this using Wallis formula, like with the symmetry, right? This will be pi by 2 sine square phi d phi. Okay, so this will be 2 by 6 into 1 into this will be what? This will be 1 into 2 into 1 divided by 4 into 2. Give this a better into 4 into this is what? This will be 1 into 2 into pi by 2. So overall what will this become? This will be 1 by 3. Here 1 to 8 it get cancel, this 4 will get cancel. 1 by 3 into pi by 4, which is pi by 12. So I know this is daunting for you. If it is daunting, it is daunting for me also. But the thing is, you have to revise, and if you like, you have to go slow through this. Okay, and like if you are not able to understand, rewatch this, try again, because all these concepts has been taught already in details. That's why I'm going so fast now, because I don't want to waste time again. So but if you are not able to grasp this, what you have to do, you have to go through the integral calculus lectures again. Okay, revise those again. Those are very important for you. So with this question, like, don't worry, this much difficulty won't come in examination. I'm 100% sure. If this much difficulty comes, this is the highest level of difficulty. So I have taught you from the lowest to the highest. Okay, but like in generally you saw, right, the gate exam questions you will be able to solve. That I solved also in front of you. But these are bit different questions which are bit difficult for you to solve. Okay, so yeah, that's it for vector calculus. So we have finished vector calculus, and next we'll study a light topic, that is a differential equation. That will be very easier for you, and you will blaze through that. Thank you, and I will see you in the next lecture.